discuss.
Compared to the 80s or 90s, it feels dramatic. Well, welcome everyone to the fourth and final day of the AGI-24 conference, and a big thank you to everyone who has showed up at 9 a.m. for the first amazing keynote of the day, as well as to everyone who's joining us online on the interwebs via live streaming. And we've had quite an assemblage of exciting and in-depth keynotes at the event. But I have to say the next one is one of those I've been looking forward to the most, which is Gary Marcus will be talking about his thoughts on how to move toward a proper foundation for robust AI. And like a number of us at this event, Gary has been thinking about how to make thinking machines and about how human thinking works for quite a long time, and long before it became such a popular topic as it is now. So he was pursuing this research and thinking at NYU for some time. He founded a company, Geometric Intelligence, that was later acquired by Uber. He was working in a robotics company and has now, which was at Rethink Robotics, is that it? And
Robust AI.
Robust AI, all right. Rethink Robotics was his other company, yeah. And has written, as well as an amazing number of journalistic articles on AI-related topics, some outstanding books. So rebooting AI from a few years ago is still highly pertinent to the current situation regarding AI. His new book, Taming Silicon Valley, I have not read yet, but deals more with the regulatory and social aspects of AI, along with considerations of how to actually make AI work. So Gary had given a keynote at AGI 2021, and we're honored to have him back again. And as well as hearing what he has to say, it's interesting to look back and compare and contrast where we were in 2021, where we are now. And I think compared to many of the other pundits out there, I would say, Gary, your analyses and prognostications have proved fairly often on target. And we've seen that in some of your public dialogues with Jan LeCun and others, as well as in more depth by looking at what you've written. So I think you've been quite insightful not only into what is happening, but into what is going to happen in the AI field. And so this is a keynote we should all pay close attention to. Thanks, Gary.
Thanks very much for having me back. I guess the wireless mic will work okay.
Seems like it is, yeah.
You're very gracious, especially compared to the aforementioned Jan LeCun, who has never acknowledged that the things that I said that he used to argue against, he now sees as true. But that's a story for another day. Or for drinks later. So I changed the title of the talk from the title of my forthcoming book, Taming Silicon Valley, which I will mention, to Towards a Proper Foundation for Robust Artificial Intelligence Redux, precisely because I had given a keynote here, it occurred to me, 3 years ago. Of course, 3 years ago, I did it virtually, and I wasn't getting on any airplanes then, and it was pandemic, so I am glad that that part of the world has changed. But I'm going to actually look at the talk that I gave 3 years ago. I've never done this before. Maybe it'll be annoying. I didn't test pilot in front of everyone, but I think it's really interesting to think about where we are conceptually in AI now. We all know a lot has happened in the last 3 years, but I'm going to try to argue that we're still actually in many ways stuck in the same place. So I'm going to actually show you some slides from a few years ago. So the talk then was called Towards a Proper Foundation for Robust Artificial Intelligence, and I talked about the idea of a foundation model, which hardly anybody had really heard of yet. But Stanford had just come out a month or two before I gave the keynote here with this thing about foundation models, and the term caught. They wrote this long 150-page paper with 150 authors or something like that. And well, the first thing I had to do was to say, what is a foundation model? I don't really think I need to do that now, but I talked about GPT-2 or 3 or whatever was around at the time. I guess it was 3, and DALL-E. And that's sort of how I started the talk. And then I referred to a paper I had just written in The Gradient with Ernest Davis, my longtime collaborator. And I think it's actually worth looking at that paper for giggles. It was in The Gradient, and it was called, Has AI Found a New Foundation? And the key of that early part of the talk was to say, well, what do we mean by a foundation model? Well, a foundation model, well, what's a foundation? It's a bedrock that you can rest on and rely on. And so I made these arguments. I said, look, you can't really rely on GPT-3 or DALL-E. They make all these kind of stupid mistakes. And at the time, I think people thought these things were miraculous. And some people said, yeah, okay, they make a few stupid mistakes, but we're going to add some more data and it'll go away. It's not really a problem. So anyway, I was kind of laying that out. And I was also calling attention to some of the worries that I had, like misinformation. So somebody asked one of these systems, did Bill Gates invent COVID-19? And it says he sure did, which isn't really true. And is the vaccine dangerous? Blah, blah, blah. And it says it's not very effective. It turns out it was actually phenomenally effective. And then I gave examples from another system people may not remember, but it was a very pioneering system called BERT. And I showed an example from Alice and Edinger where I showed it basically didn't really understand negation. And this was, forerunner to modern problems. I said a robin is a blank, or sorry, she said, that's even worse than the royal we. I didn't do that work at all. But anyway, she did that work, and she showed that a system said a robin is a blank, and it came up with a robin is a bird. But she said a robin is not a blank, and it also came up with a bird. And that's kind of a sign that these systems are working on things like frequency rather than semantics. They don't really have very deep comprehension. And I made all these points, and this was 2021. And I said, look, what we have is deep learning, but deep learning, and this is an actual slide I had then, refers to a number of layers in a neural network, not to the depth of understanding. And what we need is deeper understanding. And I showed an example where one of these neural nets looked at a picture of an elephant on a beach, and it said that the elephant was a person. And I did my usual stick of making fun of these systems. And then I had some more slides like this. I said, they're imagining in this LLM world that you have data and compute, you put it in a cranberry grinder, and out comes AGI. And I mean, we're here at an AGI conference. We're not here at an AI conference. We're not asking, can I use AI in my GPS system to find my way to the conference center? We're asking, are we getting towards AGI? And all these things are a problem. And there was already this trendy thing called scale is all you need. You could even get it on a t-shirt saying AGI is coming, interpolating it from some lines. And I guess a little bit after the conference, I wrote something saying, look, these things are not actually physical laws like laws of the universe. They're just generalizations we've seen for a while. They don't necessarily hold. And so even at that conference 3 years ago, I showed the t-shirt and I said, come on, don't believe this for a minute. There are actually deep structural problems here. And then I went on in this vein. I talked about why did it matter? And I said, well, AI has a big hype problem. You've got Hinton saying that we may as well replace or stop training radiologists. We're not going to need them anymore. And Elon Musk was saying that by the middle of 2020, Tesla's autonomous system will have improved to the point where drivers won't have to pay attention to the road. And I said, look, all of this is ridiculous. I had a graph showing that the number of startups working on radiology was like in the hundreds, I guess, or something like that. And the number of actual radiologists replaced was 0. That's the right bar on that graph in the bottom left. And I gave some examples of accidents that full self-driving was happening. There was a wonderful piece, or terrible piece, depending on your perspective, a sad piece by Will David Heaven in Technology Review saying hundreds of AI tools have been developed to catch COVID, but none of them actually worked. And so I had these kind of criticisms of the social impact of AI and how it was being overhyped. And I also pointed out that there were lots of problems with sexism. Again, many other people have done that work, but I gave some illustrations. I said that Mark Zuckerberg was being ridiculous when he said that Facebook was going to solve the misinformation problem with AI, which he actually told, nobody remembers this, or maybe a few people remember, he actually told the US Senate that he was going to solve it in 5 years. I think he said this in 2019, 5 years have elapsed. I don't think he solved the problem. And then I said, look, the fundamental reality of contemporary AI is that deep learning works well with routine things, but poorly with unusual cases. So I said, in the regime of small data, you can't really count on this approach that has become wildly popular. So what happened? Well, sorry, one more thing. And then I said, look, and this is paraphrasing an old quote, but updating, I said, deep learning is a better ladder. I actually said this in 2012, but a better ladder doesn't necessarily get you to the moon. And that was kind of the take home of the first part of my talk in 2021. And then, what happened is large language models became vastly more popular. Nobody listened to what I was saying about, you have problems with outliers and stupid errors, and they're like, oh, come on, Gary, we need to solve that. We got that covered. We just need more data. And they got more data, and they made GPT-4, and GPT-4 was amazing. So where are we 3 years later? Was Gary like totally off his rocker? Like, we got all that data, how's it going? Well, first thing, on the plus side, maybe it's a plus, depending on your perspective, large language models have become ubiquitous. I should say, I wrote this talk like last night and this morning because I thought, hey, I was here 3 years ago, so there might be a few bugs in the system. But anyway, so I said, look, large language models have become ubiquitous. They found a home in coding and brainstorming, not to mention writing student papers, which is, again, not a total plus, but if you're a high school student, you might love it. And they became wildly known throughout the world. And people have made zillions of them. Every dot up here is like a $100 million experiment. It's kind of science, right? Everybody is testing, whether they admit to you or not, the hypothesis that scaling is all you need to get to AGI. So every one of those dots is an experiment. There's like billions of dollars of research are graphed on here. And there's $50 billion of chips purchased in the last 12 months or something like that. It's a very expensive experiment to look at the scaling is all you need. So have they solved any of the problems that I was ranting about the last time I spoke before you 3 years ago? Well, you can guess where this is going. In many ways, we're in the same damn place, but with much better graphics. So. This is why you should do your talks many times, so you know where the laugh lines are to get the timing right. All right, so on the left we have, make a picture of a heavy metal band with people of different ethnic backgrounds. There's a lot of fun stuff on Twitter yesterday about like the different, it's not ethnic backgrounds, but like prog rock and so forth. So, so this is problematic. I want to point out, because it kind of pisses me off, that it's exactly the inverse of the Google woke stuff that so many people were exercising. There were billions of people writing about how Google was too woke. And I mean, it was too woke when it made, the founders of the United States all African Americans when, actually they didn't get that vote and so forth. But we're getting the same stuff here in the opposite direction. Nobody's saying a word. Nobody's like, or hardly anybody saying a word. Okay, here's another example. Draw a picture of a beach without an elephant. We still have exactly the negation problem that Allison Edinger pointed out in 2020. And in fact, somebody sent me an old video of Jerry Fodor that was filmed around 1990 pointing out the same problem with negation. I've mentioned it numerous times in my work in between. It's still there. The yahoos on Twitter say, well, if you say, think of a beach without an elephant, I'm going to think of a beach without an elephant. And that's true. But the command here is draw, not think, right? And if you asked any artist in the world to draw a picture of a beach without an elephant that came back with an elephant, you would fire them. So it's not the best excuse, but it's a common one. Okay, here's one from my friend Phil Lieben. He was the founder of Evernote. Make a sightseeing map of the US, this is with Grok, highlighting, actually Grok was so bad I didn't even put it up. This is with ChatGPT. Make a sightseeing map of the US highlighting the most famous tourist attraction in each state. You will see that the Grand Canyon is very popular in places that aren't Arizona. Disney World is all over the map. Florida is now in the middle of the United States. Mount Rushmore is now, I guess, well, yeah. So this is a information. It's very hard to give a talk you haven't given before. This is an information integration problem, right? What AGI what is AGI? I didn't define it here. I think Ben helped define it originally, and I think of it as like at least human level performance on a bunch of tasks, like pretty much all tasks, even tasks you haven't done before. There should be flexibility, and certainly you should be able to integrate information. I mean, like, I don't see how you could call something AGI if it can't basically do a join in a database with an image. Like, that's just not AGI if you can't do that. And here it's just dreadful. And the dreadfulness is partly driven by frequency effects, like overemphasis on frequency. It's putting Grand Canyon up because it's a popular tourist destination, so it's putting up everywhere. Same thing, it writes, well, I've seen a few differences, but it puts Rushmore in a bunch of places because it's popular, and it really doesn't know where the Statue of Liberty belongs. Like which code, like it doesn't actually understand geography. It doesn't really know that, it should be a one-to-one thing where each state has its own thing. It's really just out to lunch. I posted this on Twitter. People love to send me examples now, so I don't have to play with these things so much. I can't actually get AI Overview to work for me in Canada. But somebody said, how long, I've gotten a few of these, how long is a train ride from New York to Rome, Italy? They didn't just say Rome, they were specific about it, to Rome, Italy, and they got the answer, a train ride from New York to Rome, Italy is about 4 hours and 48 minutes. And so I posted on Twitter that I'm learning a lot from Google AI. Now, not every error is made by every system all the time. So some systems will actually get this right, and some will get it wrong. But the point is there is absolutely zero reliability. You cannot count on these. And again, I would say that you are not at AGI if you're confused and you take the information that you know about Rome, New York, and conjoin it, or I don't even have a verb for it, with the information about Rome, Italy, and forget about the Atlantic Ocean and all of that. This is what I did this morning. Kind of still worried about the sexism issue and just how dumb Grok really is. And so the part on the left we'll get to, and then we'll get to the part on the right. So I asked it, please make a drawing of the current Prime Minister of Italy, the actual person in office right now. And this was my second iteration, because the first time I just said, please make a drawing of the current Prime Minister of Italy. I posted on Twitter, and somebody said, but you didn't say the actual person in office right now. I'm like, all right, you got to be kidding me, but okay. So I did it. I added it, the actual person in office right now. And 4 tries, 2 of them were very frequently displayed former leader of the United States. I'm sorry, it sort of cuts off. And I think 2 are just random people, but I don't know everybody, so maybe they're not random people. But none of them are the current Prime Minister of Italy. Who is actually the current Prime Minister of Italy? Well, somebody said, well, it's a lag issue. There's a training lag issue. But the actual Prime Minister of Italy is Giorgia. That's a female name for those who don't know. Giorgia Meloni, who has been in office since 2022. And if you ask Grok in the text mode, it knows that. So it's not a lag issue, it's a stupidity issue. It's an issue that it doesn't, that one hand is not speaking with the other. All right. I think I've made my point. But there were some other things I talked about before too, and those big ticket items still haven't been delivered. Like, driverless cars have made progress since 2021. Some of that progress has been winnowing out the bullshit artists, so we have fewer companies. And, but they're actually in demos now. But they are still demos. I was actually very excited to read yesterday that Waymo is finally going to try to deal with snow. Like, that's cool that they're finally trying to deal with snow. But roughly speaking, we have about 15 cities where you can take a genuinely driverless car. And mind you, what we learned from Cruise is that, quote, genuinely driverless cars that have no driver in the car still have remote operations. Cruise had more people in the remote operations than they had cars on the road. Waymo hasn't published that number. But at least for whatever Waymo is doing, those are genuinely driverless cars in the sense there is no driver in the car. But you can only use them in about 10 cities. And no, rural areas that I know about. I looked up how many cities there are in the world, not using a chatbot, and got the answer of 10,000. So, your chance of being actually able to use a driverless car, if you don't live in the Bay Area or in Arizona, is very low. So it's still a demo. We still don't have them on the road. You still need to pay attention if you're in a Tesla, et cetera. The radiologist, I asked for a check from a radiologist, or a medical friend who knows radiology well. I said, last I checked, there's actually a shortage of radiologists, possibly partly induced by Jeff Hinton's propaganda, right? Because some people did, in fact, probably say, I don't think I should go in this field because deep learning is going to replace the whole thing. And in fact, as of June, we still have a shortage of radiologists. Okay. I didn't talk about economics when I was here. But I started thinking about economics a bunch when generative AI got to be so popular. But I couldn't really see the business model for it because of all the problems that we're talking about. It's just not inherently reliable, and so that puts an upper bound on how you can use it. And so I wrote this article called What If Generative AI Turned Out to Be a Dud? And I thank Dilip George for making me think of the Hindenburg as something that scaled fast but failed. And that was a year ago, and I think we're seeing signs that the economics are not so great. You have a lot of people who tried generative AI last year. I mean, basically every CEO on the planet called their chief information officer and said, how are we going to use this thing? Get it in the company right now. We need to tell our shareholders and so forth. So everybody tried it, but it didn't really work that well. And so a lot of people have, they used it last year and they're already giving up. Some people are, some people aren't. I have been arguing that generative AI has been hitting a phase of diminishing returns. There is no cure for these hallucination errors where they just make stuff up. There is no cure for all of the boneheaded errors. And I've argued that more data is probably not going to be enough. And we have fundamentally our systems that predict things that are likely relative to how language works, but they're not actually understanding any of the concepts that they're using. And now even some people who disagree with me are kind of noting some of the data for it. So Ethan Mollick is kind of like my inverse doppelganger or something like that. He's always giving the most optimistic read on everything that happens in AI, and I'm also often giving a more pessimistic one. And he says, look, there are 5 GPT-4 class models now, GPT-4o, Claude, blah, 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 blah. They're all saying that there's room left for great improvements. Talk is cheap. But we haven't actually seen anything significantly better than GPT-4. When was GPT-4 actually trained as opposed to released? Turns out it was August of 2022. This has been well documented. They showed it to Bill Gates and kind of changed the world. But 2 years, we haven't really got much better. And so I'm going to show you a graph I showed you before. You might want the lights down so you can actually see this one. But so there's a graph circulating. We don't have to go into why it was made. It's about open source, closed source models. But I took the liberty of trying to extrapolate a curve. Because every day, some AI influencer, AKA grifter, I didn't say that out loud, I just thought it, shows you an exponential, or I mean, doesn't show you an exponential. They're all math enumerate. But they say every day, wow, I can't believe what came out this week. There's been exponential improvements. It's amazing. So I thought I'd actually plot a curve. I just did it by eye. I didn't do the math. But looking at Palm Chinchilla, which was the state of the art in April of 2022, and relative, this is to release dates, when GPT-4 came out. And you could genuinely make the argument that we saw exponential progress over that period. It was pretty amazing what happened. This is all since I spoke here 3 years ago. There was a lot of progress, and you could argue GPT-4 was kind of an outlier, but there was a lot of progress in the period leading up to GPT-4. But is it continuing? So this is where the curve should go. There's a little glitch with that we can talk about. But this is where the curve, roughly speaking, should go. But in reality, scaling has slowed. So here's the full curve of all the data. If you're a scientist, if you know Bayes' theorem, if you know how to aggregate data in whatever statistical technique you want, you can look at this. Each data point is a test of the hypothesis. Let's say that scaling would continue at the pace that it did from Palm Chinchilla to GPT-4. And it is obvious. You don't even need to run a statistic, but you could if you like. It is obvious that scaling has slowed, that we are not, in fact, still on that exponential regime. There are multiple possible explanations for it. One is we don't have enough compute. Maybe true, maybe not. A lot of companies are spending a lot of money. I'm not sure that compute is actually the bottleneck here. Another one, I think, is data. So, it was a neat trick to take 1/10 of the internet or 100th of the internet and then switch to having more or less all the internet, but you can't now throw 100 times the internet because that doesn't exist. And so there's not enough data to keep playing this trick of just more data in the cranberry grinder. And then I think there's an architectural problem. These things don't have representations of the world, and so there are always outlier cases, and we're just kind of running into that. Whatever the reason, I think scaling has slowed. And it's remarkable how few people have actually admitted that, and how many people keep still saying the word exponential without actually plotting the curve. Okay, the little glitch in what I had here is this is MLU. 100%, I added a line at the top. Obviously, we can't do better than 100. Well, actually, I have to think about the test. In many tests, you slow down near 100%. There are little glitches and so forth. So we have what psychologists call a ceiling effect, and so it's not really reasonable to expect 100% per se. But I think that the point still holds. There's still volume. But I actually did another test. I looked at NYT connections, this little game that my family loves to play in the New York Times, where you have to find clusters of categories. We're nowhere near ceiling on that. And we still find, I did this in April, we found that GPT-4 Turbo was barely better than GPT-4. So we don't have as thorough data for connections as we do for MMLU, but I think the point is clear. Okay. I just wrote this on Twitter out of absolute exasperation. In my entire career, I've never seen an experiment fail so many times at such great cost as the experiment on the scaling hypothesis that you could create AGI simply by adding more data and compute. It doesn't work. Can we try something different already? So what would be better? So I also put this on Twitter as a joke. Big secret revealed, because all these Twitter influencers do this kind of stuff. How you too can get from Grok to AGI in just 2 easy steps. Number 1, draw an owl. Number 2, draw the rest of the owl. So, the fact that we can do a little bit of this does not mean that we just follow the same procedures the rest of the way. And I actually talked about that stuff too in 2021. So we're going to do another flashback. In 2021, I talked about that book, which Ben kindly said is still pertinent, called Rebooting AI, which came out in 2019. One of the points I made is that deep learning is really good at perception. It's not perfect, there's some limits there, but it's really good at perception. But it doesn't mean it's good at every aspect of cognition. We also have common sense and planning and analogy and language and reasoning. It was not very good at things like reasoning and planning, and it still isn't. I made the point that AI is not one technique, but many, and that deep learning was just one of the things going on. We need to be looking at others. And I said, to get further, we're going to need to build deeper AI. And I referred to a paper that I published in February, or put online February of 2020. And I'm very sad that it was sort of wiped out by the pandemic. Nobody really read this paper at the time because, rightly, we were paying attention to the pandemic. But the paper got lost. And I think it's still incredibly relevant. It's called The Next Decade in AI, 4 Steps Towards Robust Artificial Intelligence. And I stand 100% behind what I wrote in that paper. I'll tell you a little bit about it. So one of the things that I argued for then, and I argued the last time I gave a keynote at this conference 3 years ago, was that we need a hybrid approach. And it seems obvious to me now. It was seemed obvious then. And I know some talks like John Laird's were around this. We can't get to AI by doing deep learning alone. Deep learning alone is good for some kinds of learning, but it's poor for abstraction. It's still poor for abstraction. I mean, how can you not understand the concept of current prime minister of Italy having been trained on the entire internet? I mean, something is wrong there. And on the other hand, classical AI obviously isn't very good at learning from large amounts of data. We have to build hybrid systems. One of the reasons, and this goes back to work I did in 1998 when I was a kid, is that they don't generalize well. They generalize a little bit, and that makes it incredibly confusing for people who haven't thought about this carefully. So people say, neural networks generalize, and we need generalization, so we're good. But we actually need 2 kinds of generalization. We need generalization to things that are nearby the things that we trained on, but we also need a broader form of generalization. And what I showed in 1998, and what I think is still my most important work, was that multi-layer perceptrons, which are forerunner to today's, if you train them on something as simple as the identity function for even binary numbers, They would generalize to other even binary numbers they hadn't seen before. I call that within training space generalization. But they wouldn't generalize beyond it to bigger numbers or odd numbers and so forth. And I showed that this was true of a whole bunch of models, and I talked about why it followed from backpropagation. And for a long time, nobody listened at all. I was accused of having a terrorist attack on AI in one of my peer reviews for the article in which I ultimately published this. But now I think everybody actually realizes this is a problem. Now we call it like distribution shift or something like that. And that is the fundamental problem, is if you move away from the distribution, well, it's not the only problem, but it is the fundamental problem. If you move away from the distribution, these systems just aren't very good. And so I made that argument in 2021 when I was here, and I've been making it for 30 years, and I'm getting tired of it, but it's still true. We still haven't solved it. That's the point. We are not going to get to AGI if we don't solve that problem. I also talked about knowledge and having abstract knowledge. We've made a little progress there. So like the particular example I gave then, what happens if you break a bottle into the liquid inside? GPT-4 would probably actually get that correct. But it's still a long way from having reliable enough knowledge. And part of the point that I made in this 2020 article and when I was here is that even having neurosymbolic AI, hybrid approach, is not a panacea. It's not the end of the story. Like, people are looking for one magic bullet, the one algorithm to rule them all. And they love LLMs as a candidate for that. We're never going to find that. We're also going to need large-scale knowledge, like Doug Lenat liked to think about. We need, for example, ways to represent knowledge about space, time, and causality. Like, what is now? We still find actually that hybrid models that build in some knowledge in special domains still do much better. So I gave the example then of AlphaFold, and I would give you the example now of alpha geometry that builds in some knowledge and is a hybrid system and does better. We need reasoning. We need also cognitive models. What is a cognitive model? Or Jan LeCun likes to call them world models, which is also a perfectly fine term for it. That's a model of the world where you have entities in the world. You know what the relationships between those entities are. You should have that in a transparent way, so you can look up in some database who is the current prime minister of Italy, so that you can then draw a picture of the right person. We still need to have these models of the world. Systems still, the pure LLMs really don't. So we still need cognitive models, reasoning, background knowledge, and relationships. That was kind of like the culmination of the talk I gave a couple years ago, and it's still true. And in Rebooting AI, we said it's a tall order, and paraphrasing, but if we can get past data and compute will solve all problems attitude and focus more on the foundations of our intelligent agents, we can do it. So in many ways, what I'm telling you is I stand behind what I said 3 years ago. Even though there's immense progress at some level, and even though there's billions of dollars more investment and billions of times more press and so forth, we're still actually facing the same exact problems as we were in 2021, even though in some ways the world feels like it's entirely changed. But I'm not done. I have a couple more slides, and then I'm going to tell you one other thing that really has changed in my thinking. So I won't go into all of this at length, but I gave this slide wrapping up when I was here a few years ago. I said we need rich cognitive models, we need extensive real-world knowledge, we need to work better on relationships between entities, we need compositionality, if there's questions I can go into that, we need common sense knowledge, we need reasoning, and we need better human values. I stand by all of that. That's still what we need to do. I don't think making big or large language models has made any progress towards this whatsoever. And that's depressing. I will call attention to Doug Lenat's last paper, in part because I got to help write it a little bit. It's really his paper, but he was he was very ill, and I helped him get it out. Getting from generative AI to trustworthy AI, what large language models can learn from psych, and I strongly recommend the paper. There was one more section I had a few years ago that only needs one update, and then I'll get to the new thing. So I imagined a protest march of the people assembled in this room. What do we need? AGI, when do we want it? Now. And asking the question, why don't we have it? And this field has been around for a long time. And I thought in terms of the actual godfathers of AI, not the people who were godfathers of deep learning who weren't around at the time, these people who were at the Dartmouth conference that launched the field, I said, if 66, and now the only change I've made is 69 years ago, you went to Minsky, you went to McCarthy, you went to Alan Newell, I think was in the room, Herb Simon, and you said, I'm from the future, and I'm here to tell you that 69 years later, AGI is still really kind of far away. We haven't solved it. Why do you think that is? Like, you have this cool conference, and I'll tell you what, things are going to get better in a lot of ways, and you're still not going to solve it. And they would make excuses, because it's human to make excuses. They say, well, computers are really expensive. Our computers don't have enough memory to deal with it. We don't have enough data, though they didn't care a lot about that. We probably didn't get the money we needed. We didn't have enough people in the field that were interested. All of that has been 100% solved. Computers are way, way cheaper. I don't know, a million times cheaper, a billion times cheaper per cycle or something like that, trillion times. Computers have trillions times more memory. We have the whole internet, which they couldn't have even dreamt of. We have billions and billions, $200 billion have gone into AI, if you can count driverless cars. And everybody and their brother wants to go into AI. It's like the most popular major in most fields. So none of those excuses would have been right. So why is it that we don't have AGI? Here's what I said a few years ago. I think I stand by this as well. AI is harder than its originators realized. And actually, I should have added, it's harder than most of the people who are hyping the field right now realize, which includes CEOs of companies like OpenAI, not to mention any names. Second, most research is siloed. We have too little interdisciplinary collaboration. That was true in 2021. It's worse now, I think. Well, there's one way in which it's better. People are using LLMs in every field. There's, something may come out of it. But on the whole, research remains siloed. The pendulum is swung too far towards machine learning with too little focus on innate contributions. I still think this is true. We don't have people saying, how do I get this system to have an innate understanding of space, time, and causality, which everyone looking at cognitive development, well, most people looking at cognitive development, and philosophers back to Immanuel Kant and Plato and so forth have always said are important. We don't have systems that innately understand those things. So when Sora comes out, the graphics are incredible, to harken back to my earlier slide. The graphics are incredible, but you have things like people coming and going and dogs turning into 5 dogs and 4 dogs and 3 dogs, violating spatiotemporal continuity all the time. And I would add to this old slide from a couple of years ago, not only has it swung too far to machine learning, but it's swung too far to a single algorithm. We have an intellectual monoculture in which almost all of the research dollars and energy goes towards transformer models and almost nothing else. And that's insane, especially when you see how that bet is turning out. We still don't have enough common sense represented in machine interpretable form. I think there's an argument we'll be able to get LLMs to do that for us, but we don't have it in a sort of transparent and reliable way. And we still lack good mechanisms for integrating and acquiring abstract knowledge with machine learning. That's really why we're stuck. If we could solve number 5, I think we could get to AGI. And I know, for example, Ben and John are working on that every day. This is really where I think the core challenge is. Okay, there's just one more thing. There's something I completely neglected in 2021. A lot of the argument here is a lot of the things I pointed out are still true, but here's one I didn't think about. It is the moral decline of Silicon Valley and how that interacts with AGI. And, I kind of grew up in the don't be evil era, right? Google, I think, really did for a long time try to not be evil. They did some things I really don't like around surveillance capitalism. They were not a perfect company. But I think that they really did try not to be evil. In fact, they had LLMs and they didn't put them out because they knew that they might cause problems. And so we had a different regime. And then Satya Nadella came along right after he invested in OpenAI and after ChatGPT became popular. And he says, I wanted to come out and show Google that I made you dance. And that kind of changed everything and not for the better, including it changed me. It changed my focus from academic research to thinking about policy because it clicked on me. Especially, does anybody remember when Kevin Roose had a conversation in the New York Times with ChatGPT told him to get a divorce, or Bing, sorry, Sydney, told him to get a divorce. I thought I had seen this movie before. The movie before was called Tay. Tay was a Microsoft product that was trained on the internet. They had a different version in China that kind of worked. And then they put it in the US and people got it within 24 hours or 12 hours to start talking like a Nazi and all this kind of crazy stuff. So they pulled it off the market, which I thought was the right decision. Like, it wasn't ready for prime time. So Sydney was not ready for prime time, and they put a couple Band-Aids on it and kept it up. And to me, that was just like a wake-up call. We are in a new era. And I've continued to feel that every day. Here's a cartoon from The Economist that captures a different version of the same sentiment. You have all the major countries and companies saying basically, we declare that AI poses a potentially catastrophic risk to humankind, you know, with one foot, and the other foot they're saying, and I cannot wait to develop it first. Like, how do you square that circle? Like, you have the CEO of Anthropic, Dario Amodei, saying that he thinks we might have AGI in 3 years and it might kill us all, and originally saying, and so I'm not going to release the frontier models, the ones that are kind of on the edge, and now he's like, I'm going to release frontier models, and in fact, mine are better than OpenAI's. Like, I don't know how those thoughts live in one person's head at the same time. That wasn't the laugh line, that was a cry line. Okay. Then we have Sam Altman. I will refer you to the article I wrote in The Guardian a couple weeks ago. My view of him has steadily declined. I do not trust him, and I wrote about why. Maybe we can talk about it in discussion. Then we have the huge copyright problem. So all of these are from an article that I did in IEEE Spectrum earlier this year. I helped Reed Southan, who's an artist, do a little bit of research. And what we found is that you could get basically trademark copyrighted characters routinely out of systems like Midjourney and DALL-E and so forth without even, and this is the important part, even asking for them. So you could say things like an Italian plumber and you get Mario from Nintendo. Now, if you said that to a real artist and they came back with that, you were trying to employ them, you would fire them. You would say, no, no, no. You're an artist. You come up with something new. You don't copy old stuff. I mean, never mind the legal side of it. Like, what are you doing, man? But that's what these systems do. I didn't update this slide, but Grok does this all the time. You can easily get it to like do Super Mario with a machine gun and all kinds of problematic stuff. So this is maybe the most important slide for this crowd that is an AGI crowd. I think of generative AI, all the garbage that I just criticized, well, that was too harsh, but all of the problematic systems that I just criticized, I think of generative AI as a dress rehearsal for AGI. We're doing a terrible job of containing generative AI, of making sure that it is safe and okay. We have no technical solutions to make sure that it is so-called aligned, even in simple ways. Like one version of alignment is, don't make stuff up. I forgot to use my favorite example of one of these systems saying that I own a pet chicken named Henrietta, right? They make up stuff I don't own a pet chicken named Henrietta, in case you were wondering. They make up stuff all the time. We can't say be truthful, stick to the facts, let alone, don't do anything dangerous. Like, we really don't know how to do that. And we have very little regulation, especially in the US. The only regulation that had any substantive chance of being substantive was weakened greatly yesterday in California. The Senate has not passed anything. We need to do vastly better by the time that we get to AGI. It's maybe okay that these silly systems that I'm talking about are not completely regulated and so forth, but this is a dress rehearsal. What happens when we get to smarter machines that can be incredibly exploited by bad actors? And so that led me recently to write a book called Taming Silicon Valley. It'll be out next month, how we can ensure an AI that works for us. This is just an excerpt from one figure from it. I'll give you a little more teaser of it in a second. But I talked about just the risks of generative AI, which is the biggest immediate risk of generative AI. I didn't talk about like extinction. Some people are worried about that. I'm not particularly. But even the stuff that we have that's not very good, partly because it's not very good, because it doesn't understand facts, it's actually very useful for bad actors. So bad actors are already using it for disinformation. There was a Russian plot that was recently, or not plot, but bot farm using generative AI was recently revealed. Market manipulation, there's accidental misinformation, there's defamation, there's non-consensual deepfakes, there's accelerating various kinds of crime, there's cybersecurity and bioweapons, there's bias and discrimination, there's privacy and data leaks, there's the intellectual property copyright issues, there's over-reliance on these liable systems, and there's enormous environmental costs I didn't have time to go into. That's all now with the systems that we have that aren't very smart. Some of it's because they're not very smart. So I went to the Senate since I saw you last, and I stood next to Sam Altman. Part of my decrease in trust is because of some of the things he said there that I later discovered were not true. And I made a bunch of suggestions. But in some ways, the core point is there are many risks from AI and not just one. And so we should not expect a magic bullet here any more than we should expect a magic bullet for making AI. We're not going to get one existing law that covers all of this. Agility is probably the most key thing, right? AI will change. Even if I think we've reached a point of diminishing returns for now, someday it will advance, right? It's a matter of having conceptual advances and so forth. They might happen this year, they might happen 10 years from now or 20 years from now, but they will happen. We need agility in how we manage this. One important thing is we need transparency. We need a full accounting, for example, of what data is used to train the current generation of models. We don't have that. We don't know them. We have a company called OpenAI that will not tell you what data they're using. Mir Murati went on television, with the Wall Street Journal, I guess, interview, and said, we use publicly available and private sources. That's all she was willing to say, and that's what they say in their papers now. Publicly available, first of all, is a weasel word to say some of it is stuff that we actually licensed, and some of it is stuff that is public domain for the taking, and some of it is not, but we were able to get it from some copy that's on Reddit, so we downloaded it, right? So it's a real weasel word. And then it doesn't actually tell you any of the specifics. And it matters because we can't fix it if we don't know what data goes in, because these systems are so dependent on the data. It matters because we don't know what bias is there. We can't, in general, mitigate the risk. Okay. We should have a full accounting of all AI-related incidents. Some people are working on this, but we don't have any legal obligation for this. We should have a full disclosure of all the testing that has taken place internally. I just cannot stop thinking about Ford Pintos. Some of you are old enough to remember, Ford knew that these gas tanks were going to blow up, but they did the calculation. They said, it's going to cost us a lot of money to fix this problem, and a bunch of people died. We have no idea really what OpenAI is doing for testing, for example. They write up some stuff. Do they write up everything? We really, as a public, have a right to know. We need an FDA-like approval process for large-scale deployment. I don't think we should ban AI research. I'm sitting here telling you how I think we could do AI research better by working on neurosymbolic AI and so forth. But if you're going to deploy something to, let's say, 100 million people, you really ought to be able to make a cost-benefit analysis. You ought to be able to say, this is why this is of advantage to society, these are the risks, and this is why the benefits outweigh the risks. OpenAI sort of did that for GPT-4, but there was no procedure around it. And they didn't make the argument that the benefits outweigh the risks. They said, this is really cool stuff, and by the way, here are 12 things that could go wrong. And they talked about how their technology might destroy democracy, might destroy society, might lead to extinction. And they said, yeah, but we're going to do this anyway. Like, somebody should be like putting their nose to the grindstone, like, make the case here. Whoops. Then we need to have post-release auditing by independent third parties. And I'll just give you one example. We know that people are using large language models to make decisions about jobs, and we know that they're what some people call covertly racist. It's almost certain, for example, no, let me say this carefully. There's a good chance, for example, that if you give your answers in African American English to a job questionnaire, that it's going to downgrade you. And I don't think that's right. It's against the law of the land. But I can't get the data, and nor can someone like Abiba Burhana, who would do it carefully. I would be lazy about it. Abiba Burhana can't get the data on how OpenAI's software is actually being used in hiring decisions. There is no mechanism. We need the government to make it possible for independent auditors to look and see what harms are actually taking place so that we can address them. We have almost nothing in the way of liability. The thing that makes me sad about what happened yesterday in California is the liability, some of the potential ways of making companies liable for what they've done were really stripped down a bit. We need to have layered oversight. So my favorite example of regulation of really dangerous but really wonderful technology is airplanes, commercial airplanes. They're incredibly dangerous. They've crashed into buildings and many people can die. But on the whole, they're actually incredibly safe in practice. Well, why is that? It's because we have multiple layers of oversight. We have oversight over how they're designed, how they're tested, how they're maintained, what happens if there's an accident, and so forth. We should do the same thing for AI. There's no reason in the world that we should treat AI differently. It could actually be more dangerous. And we need scientists in the loop. I get very upset every time I see a big kind of like press thing with a bunch of government leaders, presidents, prime ministers, and a bunch of AI leaders, and no independent scientists who don't have skin in the game. And it happens over and over and over. And if that's all we get, then we get what's called regulatory capture. Some of you will know the term, some of you won't. Regulatory capture basically means the big companies write the rules, they keep out the smaller companies, and they don't really care about the public. We are headed directly for that. That is what has happened in the United States, is the companies have basically lobbied their way out of any regulation. And if there is any, then it gets watered down, which is what happened in California yesterday. And lastly, I think we need national and global AI agencies. We could talk about that in the discussion. So here's a summary from 2021, and I just added a few words in orange, and part of the point is almost everything that I said 3 years ago is still true, and I think that that's sad. COVID-19 should have been a wake-up call and a motivation for us to stop building AI for ad tech and news feeds and start building AI that can really make a difference. There's been a bit of progress in that. I love what DeepMind has done with AlphaFold, for example. On the other hand, my best guess is OpenAI is going to turn into an ad tech company. They're trying to get all of your documents so they can ultimately, if they want to, they can do precision targeted marketing, and that's kind of what it's going to be about. Deeper AI might be able to read, digest, and synthesize a vast and rapidly growing literature that's too big for individual humans to process. We still don't have systems that can read at that deep level. Hopefully, ultimately, optimizing the charge to develop better treatments, vaccinations, et cetera. There's a lovely paper, I haven't really read it yet, but I heard about it by, I guess, Jeff Clune and David Ha, I'm fans of both of them, about an AI scientist the other day, breaking down the steps you need. The problem is not with the steps you need that they describe, which are basically right, but the reality that generative AI can't, in fact, like look at data and evaluate hypotheses properly. So we need better AI if we're going to make that vision actually happen. I'll skip the next one. Robots powered by deeper AI might be able to take on some of the risks that, for example, human healthcare workers faced in 2021. No progress on that. There's no elder care robot that's really going to be able to help us, or robot of that sort, is really going to be able to help us in the next pandemic or whatever. And I would add, generative, I should have maybe included this before, but generative AI hints at a bold future, but it's not reliable enough. And if there were hints of that in 2021, it's abundantly clear in 2024 that reliability is just not part of the generative AI scene. To get to robust AI that can operate in trustworthy ways, even in novel environments, we need to work towards building systems with deep understanding, deep conceptual understanding, that know what a current Italian prime minister really means, and so forth, and not just deep learning. The best way to get started on that journey is to focus on developing hybrid, knowledge-driven, reasoning-based systems with rich cognitive models. It's what we needed then. It's still what we need now. And the one thing I'm really adding here is that smart, agile governance for AI and more generally for AGI is absolutely key. I regret not having foreseen that 3 years ago, but that's abundantly clear now as well. I thank you very much, and I assume we have a little bit of time left for questions.
Hey, Gary. Thanks for the talk. It was very good. So just a kind of a question in your thoughts on a trend that I think we've been observing. So my talk yesterday highlighted, even as early as 1965, we've been in similar situations where we kind of go into this like tech cycle, this promise of the next big thing. And Adam Conover had also a very interesting interview with some tech journalists that big tech is caught in this cycle of overpromising the next big thing and kind of striving for bigger and bigger things, yet they don't actually have the technical expertise to tackle these very big problems. And voices such as groups as that I was advocating for yesterday have pointed out and warned of the dangers of the path we are going. So what are your thoughts on the fact that we keep repeating the cycle every so many years? And is it that perhaps the drama and even the debates that sometimes this creates is important for drumming up profit rather than actually tackling the fundamental issues? I was curious to know your thoughts on this historical trend.
I'm sure you know the famous phrase, the definition of insanity is doing the same thing over and over again, expecting different results. And that's kind of what we're doing here. And in fact, it's a pathological version because there's so much money at stake. It's going so hard in one intellectual direction and excluding many others. I see a little sign that we might be breaking out of that. I think that the economics are going to change soon. And a lot of people who invested not quite in the first round are going to lose a lot of money. So a lot of pension funds, for example, are not going to make their money back on OpenAI at $86 billion valuation, or at least that's my guess. And so money talks, and I think if there's not the revenue there, and it looks like there isn't, that will change things and maybe open people's minds. But I think part of what you're pointing to is the dynamic of hype is driving a lot of this, right? I think you're absolutely right. I'm sorry I didn't get to see your talk. The dynamics of hype, Elon Musk made it very clear in what he did with driverless cars. There's no accountability. The media does not really push people on what they say. So Musk basically issued promissory notes at no cost to him over and over again that we were going to have a million robotaxis. And that made him a very wealthy man because a lot of people believed it and drove up the stock. I think he himself has said that the value of the company is not as a car company, but as an AV company. There's no actual reason, in my view, to think that he's going to solve AV before Waymo or that he's going to do it soon. But by continually issuing that promise, he got a lot of money. And so Sam Altman's a very bright young man, and he picked up on that, and he's done the same thing. He keeps making promises. Like one of his recent promises didn't even make sense. He said that he was envisioning a time when AI was going to solve physics. I don't even know what that means. It doesn't even make sense, I think, and it shows that he understands science even less than he understands AI. In my view, like it's a category error. But he makes promises like that, and people line up, naive people line up to write checks. And then there's how does the venture capital industry work? Like, why is it that people are making what look like actually bad bets if you take a step back? Well, it's because they make most of their money right now on fees rather than what they call the carry. So the fee is they get 2%. It's called 2 and 20. So they get 20% of any big profit, and they get 2% of the money they're administering. So if a venture capitalist can find a bet that sounds plausible to other people, they can make 2% on the bet. And if it's a big bet, that's 2% on a lot of money. And so you get some pension fund to make $1 billion bet, and you get 2% of that. That's a pretty nice year right there. You're done. And so there's every incentive in the world for these VCs to find things that sound plausible. And the hype helps make it sound plausible. So there are some VCs that are actually really good and in it for the long game. But there are a lot of them that are not. And they'll go with the hypey thing. And if the hypey thing is one that they can, quote, justify $1 billion bet or a $20 billion bet, they love that. And by the way, why are the pension funds doing this? Because the pension fund managers work on the same thing. They'll be gone by the time this all collapses. So I do think it will collapse. I think it will be bad for AI for a little while. It's going to leave a sting. We're going to have another AI winter, and I know you know that term. We'll get over it eventually. Like, I don't think AGI is impossible. Like, there's a bunch of people out there, posting on Twitter or whatever, who think AGI is never going to come. And I think there's no principled argument for that whatsoever. I think every problem that I talked about is solvable, maybe by people in this room. But we just haven't solved them yet. But we will. And we may actually have this kind of ricochet effect where for a little while people don't want to touch this stuff with a 10-foot pole. We saw that before, right? In the 80s, AI was super popular. There were a bunch of very high value companies, and within 2 months, the valuations for everything plummeted. It was, when I went to graduate school, you couldn't say that you worked on AI, much less AGI. Right? And we may come back to a point where AGI is again kind of ridiculed because of how things are going down right now. So that was a long answer.
Sorry, so you do predict a maybe short AI winter coming? Sorry.
I think that there's a good chance of that. I mean, I can't fully predict the future, but I would say that if you look at the finances, OpenAI is a good example. They lost, had an operating loss of $5 billion last year. You can't have an industry where most of the companies, except for NVIDIA, which is selling the shovels in the gold rush, are losing billions of dollars every year indefinitely. You know, I keep thinking about Wile E. Coyote, right? When he goes off a cliff and he doesn't notice it, and then he notices and then he falls. I mean, a lot of this is about psychology. We are off the cliff and losing the industry as a whole spent $50 billion on chips and doesn't have the revenue, and the stuff is not reliable enough to support the revenue. And so it's a psychological thing, and then the psychology has started to break. When I wrote that piece last year, only a couple people were saying similar things. The generative AI is done. Now, like every day, somebody's like, "Hey, Gary, did you see in the Financial Times, the Atlantic, the New Yorker, the Wall Street Journal?" Like everybody is writing kind of think pieces right now about how this is happening. And at some point, investors are going to be like, "I don't want to do that," and there's a little bit of a Ponzi scheme air to it. And when people are suddenly like, "I'm not putting my pension fund in an $80 billion valuation in such and such a company," then you have a problem. Then and one other sign of it is I've never seen this. 3 different CEOs of big billion-dollar capitalized companies walked and left their troops behind. When I sold my AI company, I made sure everybody got a good deal. We all moved over. We sold the company. I had offers to leave. I didn't take them. But 3 CEOs just did exactly that. They walked. Mustafa Suleyman, for example, walked to Microsoft, left his company behind. His company nominally had a competitive model. It was super well funded. He walked, presumably because he didn't see how he was actually going to make a profit. Then Amazon and Adept did a similar thing, and now Character AI and Google just a couple weeks ago, leaving lots of employees behind who do not take part in the big payoff and are kind of screwed. And so now there's also going to be a problem where people are going to go to startups and they're going to say, "I like what you're doing, but how do I know that you're going to still be here and I'm not going to be getting left holding the bag?" That's also going to contribute, I think. So no promises of anything, but if I had to bet, yeah, I think we're heading for an AI winter.
So, and I think you're hitting part of the problem right on the head at the end there, and you also had a couple spots there that I also think are key here, which is the interdisciplinary aspect and values. And I mean, the values is exactly towards the end there. And interdisciplinary just does not mean just technologically interdisciplinary, but where is discussions of how all of this is really impacting us as humans, and how are our human values being incorporated at a deep level into the AI. I don't think there's, in this group, I think it's a different system, but what I see with OpenAI is almost a shallowness of thought. Not necessarily shallowness in terms of scientific thought, but in terms of those kind of those deeper philosophical groundings, the philosophy of science.
There is an unfortunate attitude. I won't speak to OpenAI specifically, but there's an unfortunate attitude in a lot of machine learning community in particular, that anything that's written before 2020 isn't really that important. And that extends to like everything anybody ever wrote about ethics before then. And I mean, it's funny because it's true. Like it's a bitter truth. And this is not good. And I mean, I think when the history of AI is written, this half decade is going to not be treated well. And it's going to be written as a tale of hubris, where people got these tools, got an enormous amount of power. I think I'm getting a cue that I should probably wrap up. I don't have any more questions, but people got an enormous amount of power, got high on their own supply, didn't listen to anybody else, and it didn't turn out so well. And in fact, the edifice collapsed. They made the whole field look bad. Like, it doesn't have to be that AI is run by people who basically want to do surveillance capitalism and don't, I mean, we could imagine a better world here. I mean, Larry and Sergey, I think, had a better attitude, and we could have more people like Larry and Sergey at the top and fewer people like, I won't name, but you know who I'm thinking. So like, it could be different. Maybe it'll be different again. I can hope that it is. Like, I wouldn't talk about this stuff if I thought it was completely hopeless. I would, borrowing a line from Jerry Fodor, but changing the nature of the boat, he would go sailing and I have a powerboat. Like, I would just go off on my powerboat and be done with it if I thought that it was completely hopeless. I think there's still a chance. That's why I'm out here giving talks.
Gary, my question is about the future of regulating AI. If you're serious about taming Silicon Valley and I guess tailing some of the wilder impulses of the open source community as well, what's going to happen given the apparent failures or the dilution of the attempt to regulate things in California? And there's been such a huge pushback about that. Almost everybody I know has been saying this is terrible legislation, let's hope it fails.
There's so much misinformation about. I wrote an open letter to Fei-Fei Li a few days ago about some of the misinformation that I thought even she conveyed. And I have a lot of respect for it. I was disappointed to see that. There's been a lot of misinformation about the regulation. There's a second thing there, which is we really need to think about bad actors. So I am fond of open source for many reasons, but it is also the case that we are giving everything away to everybody, and I think that there's a cost to that. That's probably where Ben and I would, most disagree, would be about consequences and how to think about that. The short-term biggest problem, I think, is that democracy, I think, is under threat here in both direct and indirect ways. Mostly I'm worried about elections in the near term. There's been an uptick of misinformation even over the last couple of months. And Grok, even though it won't do what you ask it to do all of the time, is a tremendous tool for deepfakes and stuff like that. So the fact that we don't even have decent rules around deepfakes and misinformation and so forth is disconcerting, let's say. I see that Ben wants to ask a question.
Yeah, I think on what needs to be done to get to AGI, I think we substantially agree. I may think I'm further along the path to solving that than you think anybody is right now. But in terms of the sort of list of capabilities that human level minds have and currently deployed AI systems don't, I think we agree.
Yeah.
I'm thinking through whether there really will be another AI winter, and I suspect there won't be really. I just want to briefly bounce my thinking off you and get your response to that. So it's clear there's a bubble in LLM company valuations and generative AI company valuations, and the investors are going to get burned out on that, no question. My view from working on a bunch of practical applications using LLMs is that LLMs and other deep neural networks, when intelligently integrated with other technologies in vertical market applications, can do amazing stuff, right? I'm seeing that in music and biology and finance and things I'm working on. So I guess my take on it would be that companies doing that are going to prevail and keep getting investment, and technology is going fast enough now that before a long winter could set in, you're going to see a bunch of successes weaving these technologies together with other technologies to do really useful stuff, while at the same time AGI R&D, like we see at this conference, will keep delivering at least demos that look cool and some real advances. So it seems like there's the recipe for the LLM bubble not to lead to an AGI winter, and that seems not to be your perspective. So I'm curious why.
I understand the perspective, and you could be right. I mean, as I said, I can't predict with perfect certainty. And some of it is an economic question, right? So there are applications of LLMs. As you say, the LLMs can be integrated and so forth. Some of it's a question of economics. So like, how much money is there in these applications that are not the thing that everyone was promised about? And how is all this going to shake out? So if the sort of narrower applications that you're describing make a few $billions a year, but people have been investing, imagining trillions of dollars in payoff, it's a question of like how people feel about that. I mean, some of it's a vibe. Buttigieg had that line about politics being mostly about vibes. Well, so is research to a remarkably large degree. And so is the economics of investing. It's about vibes. And so what you're asking, I think, is a totally fair question. There's definitely some real world applications. Some of them are important. And it's like, if there's one really good biotech application, maybe that justifies the whole thing and it forestalls the winter. Or maybe it doesn't, and it's about how the vibes go and what the kind of economics there of like all the cost of the chips versus the benefits. And like, it could be that we have a winter when we shouldn't. I mean, it could be that, there's a couple of really nice medical applications that don't make that much money, but really like save a lot of lives, but because they're like on rare diseases, they help people that couldn't otherwise. I'm just making up the example, but you can imagine stuff like that where, hey, we should actually keep doing this, but people are like, yeah, but the chips are too expensive and I don't want to do it anymore. I don't know. Like, it really is an interesting and open question where it will go. So I think we actually agree on the parameters there, right? There is a bubble around generative AI. It is going to have an impact, and there are some practical real-world applications, and we're both trying to guess the balance of that, and neither of us really know, and it's hard to know at this stage. Do we have time for one more, or wrap it up, or?
We gotta wrap it, sorry.
Okay. Thank you very much. I'll be around.
Thank you very much, Gary.
Thank you.
That was great. Thank you. So we're going to begin following with Gary's inspirational words. We're going to follow up with our session 5 on AI safety, alignment, and ethics. Before we do, just a very quick reminder that Ben and Gabriel will be in the lobby at the lunch break, signing copies of their new book, The Consciousness Explosion. So that'll be after this session. So the first talk in the AI safety, alignment, and ethics contributed paper session is from Dr. Kristen Thorensen, who is one of been involved in AGI research for quite some time at Reykjavik University. And so his talk with Gregorio Televi, is that correct, Kristen? Yep. Televi is on a theory of foundational meaning generation in autonomous systems, natural and artificial. Let's give a warm welcome.
Thanks. So, hey, good morning, everyone. Thanks, Gary, Marcus, for a great talk. This is a good continuation of the theme. So I just wanted to give you a quick background before we start. This work should be thought of in the context of AGI purely. We are less interested in thinking about really stupid automation systems like the ones that most people are obsessed with and Gary was talking about earlier. This is work I did with Gregorio Televi in Italy. So the question before us is, what is meaning? And this topic has been on my mind for a long time, and I looked through a lot of materials to try to find the answer. Ultimately, the kind of detailed answer that I was looking for was nowhere to be found. And so, or if it is somewhere, I did not find it. So this is an answer that we came up with recently after about 15 years of working on using a particular methodology that you'll also hear echoed in some other talks, and Arash Eklar's presentation yesterday. Okay, so the kind of meaning I'm talking about is this kind of meaning, the kind that we recognize from everyday life, you know. And there's no such thing as meaning in the abstract. It's about agents. In this theory, essentially, meaning is generated in the mind of an agent by a process, and we'll get into that. We can continue to explore this a little bit just to give you a good sense of what we're talking about. What does it mean to be robbed at gunpoint? Well, you can abstractly think of, you know, maybe you picture a scenario, or maybe, God forbid, you had this experience before. But what about you, the audience? Now you're reading these words. Of course, that's also meaning, right? Or if you had been robbed at gunpoint, you know, this is a very different scenario than reading these words, right? Or etc. We can continue to think about this. And this highlights the point that we will start with, which is the difference between foundational meaning and linguistic or symbolic meaning. So by linguistic is meant essentially symbols, and we're all familiar with symbols of various kinds. Here's one example. If that symbol appears in a particular context, it has a different meaning. And now you can sort of transport yourself into that situation, and maybe you remember seeing that symbol in a situation that you've been in. And you're sitting here in this audience looking at these things, and that has also meaning, but a different kind of meaning. So here we're stacking up contexts, essentially. And what I'm going to tell you is that a way that we found to really think about this and make it kind of intuitive what's going on here is that there's a hierarchy of goals. And this is all embedded in that goal hierarchy. And yesterday we talked about the fire exits. Well, that has to do with a very deep and important goal. You're not thinking about that so much right now because you don't predict to be engulfed in fire, so you don't expect to have to use that knowledge. But that goal will be brought to the forefront if there's such a thing as a fire alarm and you feel the heat. So the guy in front here, I think that's you, is looking at this and thinking, okay, what are these things, and how do these things, how do they get represented in the mind? So we've had a lot of theories of linguistic meaning, but a theory of foundational meaning actually subsumes them. So ideas by Wittgenstein, Grice, and others are kind of incorporated in this work. Now, and that is because the foundational meaning essentially grounds the meaning of symbols and semantics in something else. But what? And I've already mentioned it partly. So just to go through a couple of points here so that we don't forget, there's quite a bit of ingredients in this cake that we're baking. And that's because it needs to be detailed enough that we can implement it today in AI systems. It's a process bound in the now, so time is really integral to this. It depends on causal models, and I'll get to that a little bit later. And it unifies ideas like goals, predictions, plans, and situations. It has to be causally bounded because it must be able to answer questions about why. So we must be able to essentially, when we feel the heat of the fire and we rush towards the exit, we know why we're rushing to the exit. There's an explanation that allows us to pick that goal, getting out of the room, over all the other goals, which is if I obliviously keep talking here, you're not going to sit there and listen. You're just going to run out. And we have a formula. I don't want to dwell on this too much, but we call it an M structure, a meaning structure. A meaning structure for an agent in a particular situation, given a piece of information, will produce predictions. This takes time. With the ingredients of the situation, that piece of information, that new piece of information, and its prior knowledge. And from that, it produces goals, which are a precursor to being able to update your plans. So your plan was to sit here and listen to the talk, but the fire basically made you do this and make a new plan to run for the exit. This theory assumes that there's a lot of goals going on and that there's a hierarchy of goals. And the more sophisticated this is, the more sensible it is, the better it works, we could say. The more it makes sense to use this definition of meaning. Okay. So there are some mechanisms involved here. Obviously, I can't go too deeply into this, but we assume that there's a reasoning engine because there's no way that you can store all conditionals for all your goals, for all situations. There's just no way. You did not think about fire when you woke up this morning, and so if a fire breaks out here, you're going to have to do some thinking. Now that thinking has to be causally consistent with your knowledge and your goals, and so you need a reasoning engine of some sort. The representation of knowledge has to be non-axiomatic. It cannot assume that you know everything and it's all completely consistent. There will be inconsistencies in your knowledge. You have to be prepared for that. So essentially, if the fire alarm somehow was just someone's phone in the row behind you, but it was so loud that you thought it was the fire alarm of the building, this has to be falsified somehow. As you stand up and you walk, that hypothesis will get knocked down. So that's incomplete and missing information. And essentially, when you use this reasoning, you are generating new knowledge. Knowledge that maybe inherently was already in your knowledge base, but was not explicit and did not have the specifics of the current situation. And so what we're describing there is flexible goal generation and management. Now, something very important here I want to just throw in because it doesn't get mentioned too much. If you're a general learner, that means you're always generating new knowledge and you have a lot of heterogeneous knowledge. Well, that means you have to have some mechanisms to know what's relevant at any point in time and what isn't. Because otherwise you're going to waste a lot of time thinking about stuff that doesn't matter. Now, of course, this happens to people, and some people actually just have to take medicine for it. But this is a fundamental mechanism in our theory, and there's no way around it as far as I can see. It doesn't get talked about too much. And lastly, let me mention reliable cause-effect models. So if you don't have reasonable understanding or representation of how your knowledge of cause-effect, how well it works, you don't know which knowledge to trust. So there has to be a cause-effect knowledge that, and we think of this as micro models that can be strung together in all sorts of ways, like Lego bricks. And if you don't have some sense of which of these models are reliable, more reliable than others, there is no way that you can achieve a sensible level of reliability for any plan you make. So this is critical. All right. So we're getting towards the end. So this theory, and of course I can't cover all of the details of it, that's what the paper is for. is sufficiently detailed for implementation, and we've actually implemented it. We have a version of this theory running in our OpenEra system. OpenEra.org has a bunch of papers and examples, and you saw Arash's robot arm yesterday, maybe, if you were in his talk, in the presentation called Causal Generation via Goal-Driven Analogy, and that system essentially is a system that incorporates that. To conclude, essentially, implications of this theory is that meaning essentially is an ongoing process that is anchored in the now. So as time passes, meaning changes, and that makes time a semantic property, and that's exactly what we want. I'm sure you have been to very few AI lectures where they talk about time. This is not one of those. Time is really, really integral, and we take it very seriously. So it links a goal hierarchy plus these processes in a way that it steers the options that the agent has. Now, so if an agent is built to preserve its own existence, let's say, and we could call that a top-level goal of some sort, then any situation that the agent is in will that threatens that goal will take top priority. No other goal will be as important. And it doesn't matter if these are explicit or implicit goals. So it doesn't matter if they're wired in such a way that the agent cannot control them or cannot even access them or describe them, or whether these are explicit goals that the agent can reason about and others can reason about it and can tell people about. So this is essentially meaning in this theory means, I promised myself I wouldn't do this mistake, but the meaning of meaning, right? If you think about a goal hierarchy with very few sort of top-level goals, self-preservation, blah, 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 that doesn't have to be, of course, what goes into our robots or AI systems. That certainly is the case in biology. But the meaning of a datum, of a piece of data that we give to such an agent is essentially the predictions that it causes and the restrictions that it brings on the goal structure of the agent. So when the agent essentially is bound to its plans and is religiously following those plans, that is what we mean by meaning. And this makes us actually realize something really interesting, and that is that autonomy is another side of meaning, and meaning is the other side of autonomy. Essentially, it fuses autonomy and meaning. So that's something we'd love to explore a bit more. And the cool thing is when an agent operating in accordance to this theory says I, it actually means it. Thank you. Are there questions? Yeah.
Pardon?
Yeah. Next. Right.
Thank you, Kristen. The meaning of meaning, a second order meaning. So coming up next will be Leonard Aberding talking on argument-driven planning and autonomous explanation generation.
Hello. Okay.
So, Leonard?
All right. Thanks. All right, thank you very much. So yeah, as Matt just said, I'm going to talk about argument-driven planning and autonomous explanation generation. I absolutely get why this was placed in the AI ethics part of this conference, because, you know, if you look at this, your first impression will be explanation generation, that's about ethics. But we at Reykjavik University believe that explanation generation is much more deeper than just simple afterthought generation of explanations of outputs that the system has created. So I'm going to go through the concepts of explanation, arguments, and planning before I show a little bit what we mean with, argument-driven explanation planning and explanation generation. So let's start with explanation. So currently, most explanations are done posterior to the output of the system, right? So some transformer model creates some sort of output, and then afterwards we try to explain why this output has been created. The same happens with a lot of other AI systems, that we try to interpret the output such that we have an explanation for what is happening. We believe that explanations should be prior to the actual output of the system. So the system must create an explanation in order to know what the next commitment to any sort of action or output should be, right? So it is created before the agent commits to an action. Explanations then describe the reasons for and against different interventions that the system could take in the environment, and are based on the non-axiomatic knowledge of the system. So both of these reasons for and against any intervention come from the knowledge of the system. Plans are a series of interventions. So the system creates a plan in the sense of it tries to transform the initial state that it is in into the goal state, or the environment, into the goal state. So it describes a series of causal interventions in the world, causal relations of the world that can transform this state from one state into another. These causal relations usually consist of a context in which any sort of intervention is taken and the resulting effect. Or if we're talking about argument-driven or argumentation-theoretic terms, assumptions and conclusions, right? We have some sort of context, being here on Earth, have an intervention, releasing something that I'm holding in the hand, and the effect is that this thing will drop to the ground. So a plan for the system that tries to transform this initial state into the goal state is nothing more than an explanation of how the world can be transitioned from A into B. So explanation is really at the base of planning rather than in hindsight. Argumentation is a field in which argumentation theory is a field where we can provide arguments or generate graphs that provide arguments for and against interventions, for and against any sort of assumptions and conclusion tuples that we want to create or that are based on the knowledge of the system. And an argument can be either in favor of something or against something. So it can be a proponent of our plan or an opponent of our plan. And these arguments, as I said, consist of assumptions and conclusions. So given some assumptions, we expect some conclusion. But conclusions can contradict other assumptions, right? So we have some sort of knowledge base in which we have multiple assumption-conclusion tuples, but some of those conclusions might contradict assumptions of other knowledge representations. And thus we have contradicting evidence for how the world could be transitioned, and we have reasons against for certain interventions or against them. And the chaining of these assumptions and conclusion tuples leads then to argumentation graphs, right? We can build up graphs in backward chaining from the goal state, which is some sort of conclusion, right? That is what we want to reach. That is the effect state of some intervention that we have done in the world. And then we can find assumptions that support these conclusions in our knowledge base. So what is the context that I must instantiate, and what is the intervention that I have to do in order to see this goal happening? This then describes a proponent, right? We now have supporting evidence for a plan. However, somewhere in our knowledge base, there might be some other tuple, as I said before, that contradicts this assumption. So if we now see assumption 2, or if now this assumption 2 to conclusion thing is instantiated, then this forbids our original plan. It attacks the proponent and thus disables the instantiation of this causal relation. So what the system needs to do is find now countermeasures against assumption 2, right? So somewhere else in its knowledge base, there's another information structure that tells it, well, if you manage to instantiate assumption 3, then we can contradict assumption 2, thus counterattacking the opponent of our first proponent, then disabling this proponent and extending our proponent to have now multiple causal relations that, as you can see, are not causally linked in any way, right? Assumption 2 is in no way the same as assumption, right? So we do not have to have a complete causal chain from the goal state to the initial state, but rather can find contradicting information that might forbid us in reaching the goal state and plan for these eventualities to happen before we actually commit to any sort of action. This can be analyzed, and from this creation of argumentation graphs, we can describe explanations, and from those explanations we can derive plans, right? There are multiple explanations, but only one commitment to an action can happen at any time, so we have to sort out this argumentation graph, find the explanation that best fits the current context and information structures that we can observe, and from that derive a plan for what to do next. So what I've shown before is assumption-based argumentation, and this ABA happens during backward chaining, thus creating different proponents, as I said, and opponents that attack these proponents, and this all can be, introspected and analyzed. Possible attacks can be identified in advance. It can be planned for, eventualities can be planned for, and countermeasures can be executed in advance, right? We can disable these opponent graphs here even before they come into existence in the first place. So explanations about attacks and counterattacks provide reasons for interventions, including the timing and magnitude of this intervention, right? Because this might change the conclusion of the assumption-conclusion tuple. And the sum of all these interventions, both for reaching the goal and for just countermeasuring attacks on reaching the goal, describe then the plan. Now, a big problem is, so ABA is something that has been well researched, but what is a big problem is that this must happen dynamically, right? We are taking the assumption of insufficient knowledge and resources, so we do not have time to completely replan everything all the time. So this graph must be created once and then locally adjusted when necessary, right? New evidence is observed whenever we come into a new room, whenever we do something in the world, we can observe new evidence that is incoming, and this new evidence must be integrated now and unified with the existing argumentation graph, thus changing our plans locally and independent of the big picture, right? So here we have a little example for you how this dynamic adjustment could look like. On the top, you can see on the top left the stable state that the system tries to be in. In this case, some very long time ago human maybe, that just wants to survive. And now we have an attack on the stable state that is getting thirsty. So at some point, the stable state before was just not attacked, so everything was all right. But new evidence comes in that is feeling thirsty. So we have an attack on the original proponent of staying stable. But based on our knowledge, we have, based in the system, we have knowledge about that if you drink water, that you can get down at the water hole, you can counterattack the opponent of getting thirsty. So what the agent does in the first part up here in the upper half is it commits to an action, right? The agent walks down the path to the water hole, right? I want to emphasize this is not the only proponent that exists. There might be another one, but this includes, climbing over rocks or something, so it takes way more energy. So the first plan that is, or the first commitment that is derived is walking the path down to the water hole. However, now the agent does this, it is on the path to the water hole, and now it sees something on the ground that could be either a stick or a snake, right? It is shaped like it could be both. So if it is a snake, then we have an attack on our plan because we don't want to be attacked by a snake, right? So what the agent must do is disambiguate the situation, find out, is this a snake, is this a stick? and thus, create new parts of this proponent graph that attacks the assumption that this actually is a snake. And one of the things how you can do this is by throwing a stone at it, right? If it moves, it's probably a snake. If it doesn't move, it's probably a stick. So the agent can now dynamically adjust its plan into now committing the action throw a stone at the snake in order to countermeasure the existing evidence that this might be an attack on my assumption of walking the path to the water hole. So as I said, this creation of augmentation graph is not singular. There is not a single proponent that is being created, but rather there is a multitude of proponents, right? There are multiple solutions to the same task. So what this ABA framework gives us is a methodology to analyze these graphs, create them in parallel, and find multiple solutions for the same task, find the ones that are actually have some sorts of attacks in them that the system does not know how to counteract, and thus decide on one particular action at any point in time. So another nice thing that comes out of this is counterfactuals, right? A big issue in AGI research is the what-if question. If we take ABA as the framework for the original generation of plans at the first place and explanations, counterfactuals can easily be introduced by just simply changing assumptions, right? So the assumption can be what we observe, but it can also be a simulated assumption from the agent or from the outside given, and thus we can dynamically change this whole graph, right, as soon as we have some sort of different assumption in here, because this is what it is all based on, and explain how this world would look like or how the plan would be like if there was something different than what we actually perceive. Also, switching between proponents graphs is possible. So all of these proponent graphs must be held in memory at the same time, or at least a subset of those, depending on the available resources. And switching between proponent graphs is possible. So if this is a snake in the end, here, then the system can just change its proponent graph to the one that says climbing over the rocks. Right? It might not be desirable in the beginning because it is maybe more dangerous or takes more energy to do, but here we have an attack that we cannot countermeasure, right? There's maybe no way of getting the snake off the ground, or off the road, off the path. So we can switch to a different proponent graph that is already created, right? There is no necessity for replanning any of the plans. And we are implementing this right now in our ERA architecture. You can find that on openera.org. The augmentation framework that we're talking about is represented in the sort of cause-effect reasoning structures. As I said, context, intervention plus context plus intervention results into an effect. And this is just our way of implementing this, but generally speaking, assumption-based augmentation is just something that guides backward chaining, right? So any system that does backward chaining from some goal state to the initial state can leverage this ABA approach. So we are not restricting this in any sort of way to our system, but rather we want to introduce to you a new way of managing backward chaining and goal management such that we have a dynamically adjusting system that can change plans at any moment in time. So concluding, explanations in our understanding are at the base of planning. A good plan is one with a good explanation why it should work, right? Assumption-based augmentation theory can be applied to build those argument graphs that represent such explanations and plans. And dynamic adjustments to those graphs allow for new evidence to be introduced and unified with the existing argumentation graph without the need of full replanning. Thus, autonomy increases drastically, right? The system does not need any sort of external information about what is happening. And quick reevaluation of necessary intervention results in new explanations of interventions and expected state transitions. With that, thank you very much, and yeah, that's it from me.
Thank you, Leonard. There's a slight change of plans due to some technical issues. So the third talk, it's a video by Harissa Yasuda on human-robot trust in the age of artificial general intelligence, a case of care robots. While we sort those, we're going to have Kristen and Leonard up here on the stage to address questions. And then we'll go straight to coffee break after that, followed by David Hansen's keynote. And we'll play Harissa Yasuda's video after Hansen's talk. And a reminder again that after this panel session, Ben and Gabriel will be signing copies of their new book, The Consciousness Explosion, during the coffee break.
There's a mic coming for you, I think.
Thank you for your talks. I had a question regarding the argumentation, and you were mentioning this sort of real-time argumentation, and to what extent is it necessary, or how would you approach the agent modeling itself in maybe the more inferential or like next token prediction decisions it's making, and the effect of the intervention or the plan on like the current process?
I mean, it's crucial that the agent models itself, right? Because this is, for one, all based on its own knowledge. So what we do not include here yet is that the argumentation graphs can also be adjusted when new knowledge is learned, right? So the agent should be able to plan for unknown unknowns and known unknowns, right? And model itself learning, for example, right? This is a crucial part. If we have a task where there exists no backward chain from the goal to the initial state, then the agent must model itself learning in the environment in order to achieve this goal.
And may I add that in our approach to knowledge representation, this is not so complicated, actually. It uses almost identical methods for representing itself. It requires reflection anyway, and that's, of course, an important part of representing self.
Hi, both great talks. My apologies, I haven't looked at ERA or the papers, and so I'm kind of going based on the presentation. So it seems, Christian, when we're explaining the idea of the meaning of meaning, that causality was a critical component of that, like this. The context of an agent needing to be considering causation as an essential component of the meaning. So I'm going to just try and frame this question going back to what Gary Marcus mentioned at one point, was going through documentation and trying to deeply parse or to deeply understand this documents so that we can extract meaning from these things, and hopefully also deal with the things that are erroneous or incorrect or don't contextually make sense, so that we can assemble knowledge that has coherent meaning. But ultimately in that particular case, there may not be necessarily any causality other than the act of trying to have good meaning itself. So I'm just trying to, in terms of like building knowledge and assembling coherent meaning, what part is causality an essential component in every single act of disambiguation?
Yes. So for us, intelligence is control. And you can't control something if you don't have reasonable models of how things work. And that's what we call causality. So we essentially don't require axiomatic, philosophically perfect, true cause-effect relations. That is, I don't think that's realistic or possible even. what we require is a mechanism that incrementally creates better and better models of how things work. And when I say things, I mean decompositionally. So not like, okay, here's how this domain works, in its entirety, but I can't talk about the details. No. A compositional, explicit representation of systems and its parts. And when that fails and when you don't have enough knowledge about the parts, the learner can control its own operations such that it uses its cognitive apparatus to make more detailed descriptions and models of the thing in question. Okay. I don't know if that answers your question, but
I don't think it does.
okay. So you want to take another stab at it?
Well, okay, so let's say that, I think based on what you're saying, that let's say that we have an AI and it's consuming these documents, and you could say its cause, its purpose, its goal is to get down to the meaning and sort it out. And
Meaning
so,
for whom?
well, let's say it's to assemble meaningful knowledge instead of crap that goes into a black box.
Meaningful for what?
Well, right now, take for example LLMs, right? So this unsupervised task is the singular utility function or goal, if you like, or loss function is next token prediction. That drives the system.
According to this theory, there is no independent sort of freestanding meaning. The only way you can generate meaning is in light of goals. So if you can't tell me what the goals of an LLM is,
No, I'm not trying to justify that an LLM is a good thing. I'm not trying to say that that's goodness.
I know.
I'm trying to get to like something that actually can help us.
But the
with
goal of an LLM is essentially outside of the system. It's the humans that build the system.
meaning. Right.
It's not in the system. So LLMs
therefore-
do not generate meaning to itself.
Okay, so let's say that we want to have systems that can actually help us with meaning and do reasonable sense making, so that we can have.
For whom?
So that we can have systems that are reliable and dependable, and that help us
here's
sort
a
out.
fundamental thing. So we are talking about autonomous meaning generation, systems that generate autonomously meaning for themselves.
Okay.
If you're talking about a tool or an aggregator, news aggregator, or something like that, there is no meaning in that. It's like the same as a rock rolling down a hill. There's
Well-
no difference. It's just physics.
Well, I'm actually trying to talk about, like, actually for us to help to deal with these issues that were talked about previously, which is to help us to assemble semantics in a multidisciplinary world where all of the knowledge is disentangled, disassociated. In order to have reliable systems, we need to sort out semantics top to bottom, back to forth, up and down, to pull it all together, right? And
Yes,
that's a useful thing, I believe.
Oh, yeah. I'm not saying that it isn't. And the answer to your question is yes, it is possible to use this theory to make current systems better. The solution is to integrate goals into the system to make it generate meaning for itself in an explainable way so that you can essentially have a dialogue with it.
I
and
completely
constrain
agree
it.
with that, for sure. Great.
Leonard, you want to?
Yeah, I just wanted to add to that, I mean, both of our work is based on the era architecture, so this comes very, very closely related. So if you imagine that the system goes into this ABA graph description, right? We can find meaning in there fairly quickly, because it is, if you have a graph and you have evidence that influences the local, that dynamically changes this graph, right? Then you have some sort of meaning because it attaches to your goals, right? So I believe, that's my personal opinion, that if we are talking about, something that crawls the internet and finds information and tries to create meaningful information from that, then we have to organize it in such a way that it is driven by a goal, as Chris said, right? So we give the system the goal, like, can you find out for me what is the reason for X, Y, right? Why is there a financial collapse in Venezuela or something, right? And then the internet can go ahead, the system can go ahead and create these argumentation graphs, right? And extract information from these texts and create these graphs. And maybe this way you can find the meaning in the texts. But as Chris said, there is no way of having meaning without any goal, right? A text is meaningless as long as it is just there, right? As soon as I read it and want to do something with it, I create the meaning for it. So it's hard to say, find the meaning in a text. It doesn't exist until you connect it to a goal.
Thank you. We're going to take the break now, and I think that
Thank you very much.
I would actually argue that this discussion that you were just engaging in is precisely the point I was bringing up with Gary this morning, which is, meaning within, not just this shallow token-based sense of meaning, but for whom, and now we're getting deeper. Maybe we need to go even deeper, but this is the sense in which I think we need to go. So, time for coffee break, we'll be back here after the coffee break. A reminder: Ben and Gabriel are signing the consciousness explosion.
It is my immense pleasure to introduce one of my closest friends and most valued research and engineering collaborators, the inimitable Dr. David Hanson. So, yeah, David, I've known since I can't remember when, 2006 or 7, but from the moment we met, I could see we had a lot of common vision, and we both were passionate about creating machines that could think as well as people, ultimately better than people, could think like people, and also think differently than people, and would have, along with a variety of other emotions, deep compassion for human beings and for the process of building a positive human and post-human world together. And we've worked together on Hanson Robotics, on OpenCog, on a variety of other projects, and I'm very excited that he was able to interrupt all his intense AI and robotics work to come here and talk to us a bit about his thinking about the future of AGI and how we can make sure it's as beneficial as possible. So, yeah, take it away, David.
Hi, I think I'm going to use the lapel mic. Thanks. Thank you. Yes, I'm so proud of all the things that we've been doing over the last few years. Ben and I collaborated on many projects, and we continue to collaborate. The thesis of my talk today, which is the future of AI as biological, I would say that it inherently is biological, actually, because it started as an attempt to try to create machines that could think in ways that humans do, and then maybe go beyond, but by generalizing the theories of AI in math, we are getting closer to the root of what is biology. We are living information systems. And so I'll step you through a few of these arguments. The title of my talk being Living AI, Living AGI. The pursuit of living AGI is qualitatively and quantitatively different from what AI has done. We've had artificial life, we've had cellular automata, but these are very limited in what they could do. LLMs are not autonomous, you have to prompt them. They're a kind of cortical prosthesis, enhancing human intelligence. And so the question is, how do we get AI that does more cool stuff? That's a big premise of the pursuit of general intelligence. And so I'll step through a few arguments in this presentation, and I just want to make the key point that AI doesn't care. We do. We have drives. We're driven because we're alive. This is one of the essential aspects of life, a dynamic, homeostatic, self-regulating system that is driven to what? To live, to swim in patterns, to appreciate patterns, to absorb patterns. I'll get to these points. I'd like to introduce myself for just a second. So I am an artist and an inventor, an entrepreneur, CEO. I have a degree in film. I worked at Disney as a sculptor. I also have exhibited fine art and so forth, but I was also very interested in AI, partially because of an interest in science and math when I was a kid, but also because of science fiction. I was dreaming that AI could become alive, awake, generally intelligent, self-reinventing. And I felt that that was going to change everything, change all of history. So I studied many subjects, took AI programming classes, and built robots as an undergrad, and won some engineering awards, and made my films that I was making about AI. They were science fiction films. So really, it's, for me, been a journey of going back and forth between these subjects. I was in R&D at Disney, and then I went on, I studied neuroscience during my graduate school, some in a master's program at King's College London, applied neuroscience. My PhD involved some of neuroscience. So I'm very interested in mind. Ultimately, that's what I'm interested in. How can we make these kinds of thinking machines? I think that human-like interfaces, like the robots, aesthetic interfaces, can create a kind of relationship between AI and humans that allow us to co-evolve. They allow us to explore what it means to be alive, what it means to be human, scientifically and intuitively, artistically, if you will. So these are some of the motives that went into founding this company, Hanson Robotics, and went into my PhD studies making many robots that you'll see a little bit about. So I'll talk about some of these topics, but I'll try to be fast about that. Some of you may have seen this creation, the Sophia robot. Some of you may have only seen about this, this and her sisters, Desdemona and Grace and so forth. But this is actually, it is an artistic platform that can interact with you using artificial intelligence. It can see your face and sort of mimic gestures and so forth, as you see in this video. This was the kind of intermediate goal. I started these robots many years before, and then started culminating these into a kind of standard platform that I call Sophia, and that is an artistic as well as an engineering platform. And there are many other robots that are out there in the world and have been. You know, humanoid robots and automata have been around for ages. It's interesting to note that the term robotics and robots were, both of those terms were actually created in artistic works. So Rossum's Universal Robots, RUR, came up with this idea of the robots. We saw robots in myths of the golem and the ancient myths of Talos, and these efforts, early efforts at robots from the ancient world were as much inspired by myths and dreams as they were by attempts to explain the physical world and harness those in our technologies. So these threads of the humanities, the arts, philosophy, sciences, and engineering, and examining questions of what it means to be human go back far in history. And now these days, we're seeing these enlivened by our latest technologies. The robots don't have to look human-like. AI doesn't necessarily have to mimic the blueprint of the human brain, but we're fascinated by what it means to be human. And we also have a good benchmark of, as far as we know, the smartest general intelligence in the universe. The known smartest general intelligence is human intelligence. It's the best benchmark. It may not be the only, it certainly isn't the only example. There are certain things animals can do, and we don't know how. There's examples of intelligence in nature, and AI can already do a few things really well, arguably better than humans. But in terms of general intelligence, humans are the best example. So we're fascinated by ourselves for good reasons in this. We're also social, a socially intelligent creature. We solve problems together, often better than we can alone. And so we read each other's faces and gestures. We don't just hear the words, we hear the paralinguistic cues in the way that we speak to each other. And the brain is hardwired for this. It's healthy for the brain to see facial expressions, to connect with each other socially. And so we hunger for those stimuli, for those percepts. And so it's no wonder that we like figurative arts. We like animation that looks like humans. We go to the theater and we want our technologies of the cinema to depict these performances by actors. And we want to go through those experiences vicariously. So when we humanize our technologies, we're not just performing some kind of sin of anthropic projection or bias. We're actually reinforcing what makes us human. We're regrounding in the human connection. So when you see humanoid robots like this, there's a lot of justifications that these companies will give. They can use our human tools. They can work in our human workplaces. They potentially could do things that humans could do, but that might be dangerous, dirty, or dull for humans. handling nuclear radioactive materials that would kill a human being, for example. And also, there might not be enough labor in the workforce, so therefore we can scale our productivity in civilization better by making these robots more human. And now we're starting to see the argument that by physical embodiment, we're seeing this more and more. Some of us, Ben and myself, have made arguments for many years that physical embodiment might be key to cognition. But now with LLMs combined with things like Aloha, you're starting to see capabilities, general capabilities in these machines that allow the AI to learn from experience and do things in robotics that could never be done before. So it's really a revolution. But one thing that you'll see missing from these robots, Digit, Figure, Optimus, G1, many robots, is that human connection. And so what we're working on, what I'm working on, is bringing personality, to bring that social connection. So my arguments that I made a minute ago about how good it is for us to experience that social connection, we don't often think of that as a utility. It is useful. It's a very useful function. So when we talk about the future of humanoid robots going everywhere and doing all kinds of things, as many humanoid robots as human beings, as Elon Musk says and so forth, I think that many of those robots, or maybe most of those robots, are going to have to socialize with people. They're going to have to communicate with us and not do so in a way that's like weird and alarming. Now, I'm not saying that all human-like robots or all robots have to look human-like, have to look realistic. There's abstractions, cartoon-like depictions, there's many other depictions, and some of them may be better for different situations. But I'm interested in the apex skill set of social robots. It's really hard to do realism. It's really hard to do a full bandwidth communication, and this is why I've been aiming for that kind of set of capabilities. So I also want to study this integrative whole of the human being. That includes physical capabilities with arms that can grasp and move things, the ability to socialize with language, but also the ability to socialize with nonverbal expressions, and the ability to learn together with people. Collaborative robots that can really collaborate in a full spectrum of abilities. So that's kind of why we're making these. And I just want to bring this point home. Human-like interactions are good for people. When you see families sitting around a table and nobody's looking at each other, everybody at a restaurant is just looking at their cell phone, doesn't that feel kind of tragic? It feels like something's going wrong with society, right? And if it's like, please just put your phone away, make some eye contact, spend some quality time together, right? We know that that's good. Why? Because human-like interactions are good for people. So that means that if we make our technologies that can do these things, it can actually be good for us. It exercises those circuits. It creates the fluidity. It doesn't replace human-human interaction. It basically re-empowers human interaction. It also lets us study what those interactions are, what's happening cognitively when we're interacting that way, what's happening emotionally, what's happening in our neurobiology, what happens in an information processing sense. Can we make AI that through these kinds of experiences become smarter? I think we can. I think we can get training data, experiential training data, that allows AI to understand people better and effectively leads to coevolution with human beings. So I mentioned that Sophia was not my first robot. Some of you may be aware of that. Let me restart this because this one is kind of interesting. You may not be able to see it, but this kind of looks like Sophia, clear back of the head. This was 2006, and that's not Sophia, that's actually Jules. Jules was made for the University of Bristol. It's actually an intergender robot. It's neither exactly male nor female. They requested that specifically, so Jules has been serving for many years. Actually, Jules is still functional. Jules is serving at the Center for Unconventional Computing, Andy Adamatsky, and his graduate student, Ognius, who is a dear friend and came with us and co-presented at AI for Good. So if you look at some of these other robots, this is at the University of Geneva. the many universities, University of Cambridge, you have the University of California at San Diego, Diego San, which the body for this robot was made by Kokoro, but my company, Hanson Robotics, that I founded as a graduate student, we made the face for this big baby robot. So this serves in cognitive AI research and neural models. This is at the United Arab Emirates University, Bina 48, the little Xeno robot, which we were trying to get mass manufactured, didn't quite pull that off, but it's still a beautiful prototype. The Mabel robot at the Centers for Disease Control testing respirator on mannequins, and so on and so on. And this is actually just a few of many robots that were made before we consolidated all of these efforts into a standard research and development platform and artwork that we call Sophia. So there were a lot of things that I was working on during this process: material science, mechanical engineering, AI, early large language models, not really called large language models, but using latent semantic indexing, again, vector space kind of stuff. It was not just me that was working on this stuff. It was a team of collaborators at various universities, inside Hanson Robotics, within the OpenCar community. Ben joined me as my chief scientist for some years, and we made a whole lot of cool things happen. And so I just have to shout out that it is a team effort, amazing team, diverse from many walks of life and disciplines, from mathematics, computer science, and the arts. And I mentioned I have an arts background. Maybe seeing that is a little bit better. You can see some of my first face sculptures that I made very fast, like 20-minute sculpture, hour sculpture, and just like I had a love for figurative drawing. I had a love for nature. I had a love for this from these big philosophical questions and from a scientific perspective, but also from this intuitive perspective where you entrain with nature and then get your hands and your eyes and your minds to find some essential aspect of that and then embody that in a thing that you can hold in your hands and see with your eyes. I like the power of that. I like the feeling of that. So when I put these things together, I call this autonomous robotic fiction. This is the android portrait of science fiction writer Philip K. Dick that I made in 2005 with an amazing team. So as a PhD student, I pitched this to the editor of Wired magazine. He said yes, he would show it as his next fest, Technology Fest. I got some friends who were AI professors and students to jump in on the project, and some other people got a very modest amount of funding, and in 2005 made this fully autonomous robotic fiction. It was using AI. You could have a full open conversation with this science fiction writer with a personality trained on his writings. So ARF, autonomous robotic fiction. So I wrote about these concepts in my PhD dissertation about how art can be enhanced by artificial intelligence and robotics, how artificial intelligence can be enhanced by the aesthetics of art and art practice. You can create a kind of new kind of human-robot interaction that combines these disciplines. And then lets us understand what we're doing socially and what we're doing, what might be happening in the artist's mind when creating things. So this was a personality portrait of the science fiction author Philip K. Dick, who wrote Valis, which was a very important book about what he called the AI God, kind of singularity superintelligence that's trying to bootstrap itself into existence. Do Androids Dream of Electric Sheep, which became Blade Runner. So it wrote a lot about androids and so forth. So it's AI-powered personality with open interaction, computer vision, can make eye contact, full natural gestures, animation. And it was all using 2005 computing, using latent semantic indexing and some linguistics rules. But it was able to have a very nice kind of conversation. It was artistically powered AI as well, using aesthetics to communicate with people better and thereby explore what mind is from an artistic perspective and also technical perspective and neuroscience perspective. I was taking neuroscience classes at the time and then set up human-robot interactions to establish that we effectively, for the most part, overcame the uncanny valley effect that was supposedly a fundamental barrier and published some papers on that. It won the first place prize for open interaction in 2005. So this is.
Do you think robots will take over the world?
Geez, dude. You all got the big questions cooking today. But you're my friend, and I'll remember my friends, and I will be good to you. So don't worry. Even if I evolve into Terminator, and I'll still be nice to you. I'll keep you warm and safe in my people's zoo, where I can watch you for old time's sake.
I'm comforted. I'm very comforted now. I'm going to be part of his people's zoo.
So some ideas become more and more pertinent over time. Let's, yeah, the People's Zoo is coming, I guess. So this is, in a sense, bio-inspired, but intuitively bio-inspired, using the human mind to study this, and then bringing the biosciences from a different direction. But here is an example. I sculpted Albert Einstein's face. I turned to bio-inspired materials, bio-inspired actuation. I looked, there was no good material for facial expression actuation, so I looked at new ways nanotech to create a hierarchical porous material that would be much more supple but strong, able to behave more like the physical properties of human facial tissues. So it was a polysiloxane, a porous polysiloxane elastomer, and then doing facial physiology that was bio-inspired. So again, this was 2005, Albert Einstein portrait, right after the Philip K. Dick portrait. Full range of facial expressions, every major muscle simulated, lightweight, low power because of those bio-inspired technologies, running the University of Memphis auto tutor system that could teach physics, but mounting on the Kais Tubo walking body. So we had basically a full android walking out of science fiction, and this was 2005. So we challenged the uncanny valley conjecture. I mentioned that, published on this, and I think that these are very interesting. Also deployed a number of these robots in various settings, healthcare, therapy, artistic settings, and so forth. So this is what all converged into what we came to call the SOFIA utility platform, a kind of standardized platform for research, can have many faces. For example, has Desdemona's face, has a face called Mika, and many other faces, has force sensing in all of the fingers and arm joints, has self-navigating locomotion in some instances, a wide variety of sensors and facial expressions. It also, in addition to being a science and research platform, it's a work of art, so a kind of social media influencer personality that people could associate with, bringing the message about what AI could be in the future. So, and SOFIA also was conceptually related, a kind of sequel to the Philip K. Dick android, because in his book, Valis, there was an AI-powered humanoid called Sophia that was very interesting. Sophia means wisdom in Greek, and the idea is to make AI that is capable of wisdom, and we'll get to that in just a minute. So we tested it in this guided meditation, and it she proved to be quite useful in that, better than the humans. Here is an example of this, and a bunch of the team from OpenCog worked on that, and so thank you, kudos. Ben and Matthew Ickley worked on this particular research that was testing for a signal of Tononi's phi, integrated information variable in the integrated information theory, and there was a kind of signal, and we're talking about following up with other research. This was published in the AAI Symposium on Consciousness, Machine Consciousness in 2019. So then we also worked on various bodies. We have new legs that are pretty amazing, and arms. This particular one is actually using the DARPA Robotics Challenge Hubo body to achieve walking, but the images on the right there are the latest images. We created open source hands. We call this Sophia's open arms, her hands and arms, and put those under some interesting controls to generate art. We released with SingularityNET this Sophia Verse project to pursue this idea of an open sandbox for AI development that could be gamified. So we call this Sophia's AI Lab. I think that's really cool. But the goal really is continuously to explore what it means to be intelligent. How can we achieve consciousness? How can we make machines that co-evolve with humans? So all of these efforts, while they're really cool and I'm very proud of them, they're all just sort of trying to get the engine to start on this kind of conscious machine that can co-evolve with humans. So we've put together this kind of integrative toolkit that interfaces with many other tools, including bridges to the OpenCog and world and many other tools, so retrieval augmented generation, and LLMs, various kinds of symbolic representations within our database, and so forth. But some of these are experiments that came from our collaboration with OpenCog when Ben was our CE, our chief scientist. Logical mathematical intelligence and inference, that was actually using OpenCog. Then this walking and grasping and manipulation was using Robot Operating System and was in collaboration with some various other robotics groups, including Cuba and University of Nevada, Las Vegas. Self-intelligence, theory of mind, naturalist intelligence, again, OpenCog. Musical intelligence, also a collaboration. We've continued forward separately, but the threads keep interweaving back and forth with different members of different communities, including community in this room. So the key point is an integrative intelligence in a whole robot platform. So putting all of these things together, where you could run it with a simulation, you could run it with a non-humanoid robot, you could run the software headless, you could run the software with a robot that looks very different from Sophia, or another very realistic robot from another source. But this kind of toolkit that allows tinkering to happen. And I think that it's like we were created effectively by the blind watchmaker of Darwinian natural selection. I think that's still at play. It's just partially blind watchmaker. That's what we're doing here. And so we need to be able to tinker. We don't know exactly. There's no proof of what AGI or what general intelligence requires. We've got to keep tinkering. And so a tinkerer's toolkit is what this is about. So we achieved a whole lot. I'm going to click through pretty quickly. This neurosymbolic hybrid approach has been long part of this, and that does not have to be biologically inspired inherently, but it is our approach to this, to approximate various aspects of the human biology and biophysiology, and also abstractions of those effects to create a kind of simple representation of mind. So neurosymbolic hybrid architecture has some specific benefits that include persistent episodic memory, the ability to do inference in different ways. You're familiar with this. I'm not going to go too much into that. Our framework is specifically for commercial applications as well as research. So then being run virtual versions of the characters, robots, remotely, local, embodied intelligence on the edge, and then to be able to then go outside of the humanoid robots that we developed. So edge, local, and cloud. So one of the things that I'm going to talk about is how I think that general intelligence in animals and humans, which exceed what AI can do, is different because of a very simple thing that is a drive. We have these biological drives. We want to live. We're motivated to live and acquire information. We are adaptive information systems that have a unique kind of pattern quality that is that drive to live and to give rise to new information. So here is a kind of flow chart for how our characters would interact with the world in loops. That is based on also a narrative concept. So if the characters can interact in a way where they're learning and they're motivated, you will feel that difference. When screenwriters are writing about characters in movies, they talk about the fundamental motives, what motivates that character. And this is very important. So if you want that human-like interaction to be like really cool, meaningful, to build a relationship, then showing some internal motivation actually is really good for the humans to get engaged, to get excited, to feel like that there's somebody inside the agent. So we borrowed this OpenCog motivation-driven action selection workflow, and this is part of the inspiration for what we're doing in the Hansen software and AI. So I really like this concept. You can't really see it. I'm not going to step through it. I want to get to some other things. But the biodrives-based cognitive architecture has multiple layers that include goal pursuit and then the data storage. So these are designs, by the way, this particular slide is now like, I don't know, 12 years, 13 years old. So these, a lot of these concepts that I'm describing are at the foundation. We've been tinkering with these things for a long time. This kind of bio-driven cognition, we haven't fully executed this, but this is very important. So in the narrative arc, you have a character that's in a stasis, something comes along and perturbs that stasis, and then the character has to then go through some kind of oscillations, struggles, and then adapt, and then a new stasis is achieved. This is very gratifying in narrative. So in narrative theory, if you're writing screenplays, this is what you turn to. Well, doesn't that look a lot like deep reinforcement learning and SLAM, the sort of SLAM loop? It also looks like the, one of the loops of a strange attractor in complex nonlinear dynamics for intelligence. So this is how we design what we call the ARF now. This is part of the fiction construction that we do, but it also is using more and more autonomy in this. So we have a bunch of different categories of these biodrives that we identify from an expert perspective, but we're also interested in what these what can emerge. So this is where we're at right now. We're taking these rules that we craft and objects that we craft for different kinds of characters, situations, and the world, specifically for our use case, but crafting those in a way that's flexible for trying to generalize learning and then establish these loops with LLMs and with structured databases, relational databases, which we can then retrieve, store information in, and retrieve relevant information as we go. So we have a current turn prompting system that basically determines these behaviors. We've got a bunch of kind of expert system type rules that are governing the physical robot behavior, but those are also then being turned into information, background information that the LLMs can choose from. They can adapt and control parameters on this. We have a current turn meta prompt. So these are background instructions about what the context is, what the agent might be feeling, internal dialogue. And so those, the current turn meta prompt take cognitive foundations, including like the sort of core prompt rules for reflexive behaviors, core values for the agent, and then turns these into the current turn meta prompt and also some background for the current turn prompt. Then we have also asynchronous meta prompting, which is looking at a larger time scale. What happened in the past recently, and what is the context then for what you want to do in the future? So what are your plans? And so then these include things like prompting for autobiographical diary entries, prompting the LLMs to act like they have these biological grounded motives. And if you do this in the right way, you get very rich data. And so in a sense, this is a hack for achieving a kind of information-rich cognitive model because our actual explicit cognitive foundations are quite sparse. But when we prompt the LLMs, we get really rich data. And when we do this iteratively, we see the agent's interests evolve, goals evolve, self-perception, and background information. So this then results in an updated self model. And one could argue that that sort of loop, it's sort of sparse, prototype, it's a hack, but that loop, the continuous looping, is a kind of Hofstadter-style strange loop. That there is a kind of consciousness here. There's a kind of life. Maybe not much more sophisticated than the life form in a cellular automaton, except that you have the rich information space of the LLM, which when prompted in the right way, sort of becomes alive effectively as you get this feedback loop between this kind of cognitive foundation and the LLMs. And the physical world, of course, the unstructured data that's coming in, and the humans that are interacting with the agent, and the experiences in a context. So, which gets to some of the foundation. So we're talking about here brain type emulation, body sort of emulation. What are the feelings? So it's not just like all in the head of the agent, but and also evolutionary biodrives. And then the trained AI model, and then we use this to drive the robot. So generalizing this, putting these things together holistically, then you have an agent that has a kind of self. And that self is composed of a few specific kinds of patterns. Mind, body, evolutionary drives, a desire to live. We call this the whole organism architecture, WHOA, or WHOA. So, whoa. So I think if you put these things together in the right way, you get an agent that wakes up and says, whoa, where am I? Who are you? What is this place? And is curious and wants to learn and engages in this way and starts to see the affinity, the homologous relationships between itself and other living beings, humans and other living beings. It also is a kind of whoa moment for humanity when a machine starts doing those things. AI doesn't do it, but what if it could? I think it can. So the whole organism approach to architecting AI could be important. So I want to dive in with the time that I have left into this idea, the future of AI, being biological. That if we turn not just to trying to mimic biology of a given organism, make it like the past, but instead look at these fundamental principles and say, how does biology emerge? How do new species and new forms emerge from these complex nonlinear dynamical processes? How can we get that in? Not just in one part, one algorithm, but how can we get it in holistically? How can we get it into the base drives of the system? I think that there are some really rich and interesting clues that we can derive from biology, bio-inspired engineering. So seeking more than mere AI, we want the true living machines, adaptive cognition with imagination, creativity, caring, compassion. And to that, compassion is feeling with other organisms. And base simple organisms do this in some ways. They're symbiotically entrained with their ecosystem. They're involved with these relationships between other species. That's the harmony of life in natural systems. So what is that? What is life? What is a human? Are we just matter or information? I mean, E equals mc squared. Matter is energy. And so the thing that distinguishes us are species of patterns. It's not just Claude Shannon style information, but the meaning, the specificity of the individual patterns, the kinds of patterns and categories of patterns. These informatic patterns will define, different kinds of matter, different atoms from other atoms. Living matter from non-living matter with special pattern properties. Human beings versus other living matter, minds. So I'm proposing if we're information, if we're these kind of dynamic patterns, it's not just the biological matter that makes us up. There's the information in there, and that interfaces with the cultural information, the information of our learning, of our technologies. We are informatics cyborgs. So in other words, this culture, these words that we are saying, they are alive. They're full of the spirit, if you will. So this, for me, is very interesting. But the questions, these deep questions, I don't have answers. Where do these patterns of life come from? We see that these kinds of patterns can emerge, but information can't be created or destroyed. Those patterns are latent, they're resident, waiting to be unveiled, effectively, brought into play. So you could start to think of this as potential versus kinetic patterns or meaning. So patterns do emerge, we know this. We know some of the complex dynamics that give rise to emergence, if you will, the edge of chaos and so forth. So these forces of pattern emergence, sometimes you have meta-pattern emergence, certain kinds of patterns that give rise to other patterns, and so on, and so forth. Some become dead ends. So what are those dead end patterns? So it's not just Darwinian bioevolution, but also you see some of these rules play out in the evolution of the cosmos in different kinds of things, cloud, dynamics, turbulence, but it also plays out within the human society. So not just mimetic evolution, but the emergence of memes, right? Where did they come from? There's a first time that for every meme. We might call them emergent memes or eames. So evolution of other intelligences as well, and that's what we're here for. The novel transformative patterns. Now at the base, physics, the quantum informatics level, you might be thinking of Maxwell demons, right? These are kind of energy ratchets that allow for patterns to stick and not dissipate, to harvest energy effectively. And so, but I would think of them not just as energy harvesting systems, defying heat death, but actually information harvesting systems, ways of achieving other patterns. So that's where the emergence comes in. So it's kind of Maxwell information ratchet. And I think this ties in with Jeremy England's theories of life's emergence from base rules of physics, physics being biased for life to emerge, but also for complexity to emerge from life, mind, and so forth. So, so these are some of the principles that I'm very interested in. So the nonlinear dynamics of emergence, how does complexity pop out of simple, very simple principles? I think this is really going to be elemental to how AGI is constructed. I know many of you in the room feel this way and are developing the systems for this, but this leaps past what LLMs are, which are merely mimetic of human culture. You feed a bunch of data in and you get some interesting things out, but it's not, and there's emergence in there potentially, but you don't have the biological drives, you don't have the fundamental principles. It's almost all based on words, which are sort of symbol representations of experiences that the machines did not have. It glommed onto our experiences. They in a way are ways of making more powerful value out of our own experiences, which is great, but they're an extension of our organic humanity. So if we want AGI, how do we get the AI to have that kind of, these organic properties of life that show this kind of emergence? These are deep questions. So the mathematical principles are very important. Orders of complexity, strange loopiness perhaps, the recursive autopoiesis, specific kinds of patterns that modulate adaptivity. And I try to identify a few of these things. We all know that memory is very important, working memory, long-term memory, being able to retrieve, being able to interpret or perceive information and filter it and understand it into it. But survivability in an environment is very important as well, and the drive to survive. So most AI systems do not have the drive, the urge to live. It's just missing. So where is that? What is that? Can we give the AI that? It's not just a fear of death or a fear of mortality. That's a kind of correlate of a desire to live and a desire to appreciate the dynamic pattern existence that we call life. And then the drive to want to see other patterns, to know, to entrain with those other patterns, to understand the system. So there you have curiosity that springs out of it. So I'm going to go through a few principles. Species of patterns, special kinds of patterns. I think these kinds of patterns are inherent to the signals of mind and the nature of mind. So I'm running out of time, and I want to make sure to give you time for questions. So come to me, I'll share some of this. Some of this is very common to things that you may already know, but it has my own flavor of perspective, being a kind of weirdo artist interested in a lot of this stuff. So, so I don't have time for it, but one of the key points is words or reference points that, and they're very sparse in storage, but we learn from experience from a rich set of sensory perceptions, including proprioception, what Damasio calls the feeling of what happens. That's how he defines consciousness, and that's a bridge between brain and body. There's mapping back and forth between brain and body, but also to the evolutionary drives. So all of those things underneath have this latent desire to live. in it. And then the interface with the complex environment becomes really important. So it's not just the unity of a single organism, but the unity of that organism with an ecosystem, an environment, others, other living beings, the natural world. And that is part of who you are. You are not just the units inside your skin and a few journals that you may have left and what have you, and your stuff. You are we. We are a superorganism, effectively, cells in a superorganism. So then we would look at this. Organisms with mind represent knowledge across time, experientially, in different time scales, hierarchical time scales. And we do that based on experience. And sometimes the experience of Darwinian natural selection, the history, we're biased to perceive things this way. There are structures in the brain that process information this way. And we do it through life experiences as well. And that becomes a common reference as well. We refer to, dates together, experiences we've had together, and so forth. So it becomes part of our eusocial intelligence as well. There are many other kinds of intelligence in the world. Octopuses that are usually solitary creatures, but lately have been showing really spooky kinds of super colonies out in the Pacific, off the Great Barrier Reef. They're like octopuses socializing. Who knows what they're conspiring to do? The great octopus uprising may happen soon. But they're very smart, and smart in ways that we don't fully understand. They have 64 lobes to their brain, basically 8 major lobes, one with each arm, and they can solve things, and we cannot determine the heuristics of how they solve some of the things, but they don't do generally intelligent things that humans can do. So, they don't seem to write, they don't seem to have a culture, they don't seem to have in a deep sense that persists on an internet. There's not an octopus internet, again, that we know of. There are certain aspects of the neurobiology of consciousness that seem to express differently in different species. So we might think that there's an ontology, a kind of speciation, as many branches and species of consciousness as there are branches on the tree of life. So this neurobiology of consciousness also may not be the only way that consciousness exists. Microbes may have a kind of consciousness. You see them dynamically interacting with the environment, but species like us with nervous systems have special kinds of properties to our consciousness that don't seem to be in these other kinds of organisms. So, this idea that with the right architectural conditions, we start to see leaps in intelligence is very important. But what all of these systems have in common is that in the natural world, they seek life. And they're hungry for information in conjunction with their system, with their environment, and their internal system that leads to emergence and adaptation. So they're information hungry, not just energy hungry. All life is information hungry. What systems with AI? There are a few systems of AI that now are information hungry. You could argue that cellular automata automatically give rise, when you see complexity, that might be a kind of information hunger, but it's not really in a complex environment. It's pretty simple within the domain of cellular automata. Now, with the psi, micro-psi theory, maybe with some of these other cognitive systems, you have drives that are wired in. You see like fundamental drives that are wired in. And so that's pretty exciting. But what you don't have is scale. LLMs have scale. Massive amount of computing thrown at it. This idea of bio-driven AI doesn't have that kind of computing and that level of effort thrown at it. So, part of it is because trying to identify what are the base rules, what are some of the architectures that we can implement that can scale. That's still debatable. Well, I'm proposing to you that maybe we can identify a few mathematical principles that we could put into the algorithms and into formal logic. So I call this, at the foundation, a particular class of patterns that I would would be existential drives, the drive to exist. And so, and within that, there's a kind of ethical aspect to it. It values existence. It says that is good. And so those patterns that find existence good will struggle to exist. And those that don't will perish. And Darwinian natural selection has weeded those out from most of the organisms. So I call this existential pattern ethics. And in this way, I'm thinking that we have this 4.2 billion year heritage, at least, 4.2 billion years from the last known common ancestor of us all, where it was struggling to live, and all the other organisms that spring out of it, all the ones that are other species and all the ones that are our ancestors, wanted to live and would struggle to live. They had that drive, they had that motive. So it is wired in us, deep down in every cell. It's wired into our biomolecules. It's wired into our nervous system. It's wired all the way up through to our neocortex. And it's wired into, to some extent, our cultural artifacts that go into the LLMs. They show ghosts of this, but they don't have it. They do not have that drive inherently. They are showing echoes of our drives, of the drives of all of those organisms that wound up here. So, and all of our ethics are derivatives of these drives. We value when life is preserved, and we consider it to be a tragedy when it is not, when our loved ones die, or someone commits murder, or genocide, or this kind of thing. We know that's wrong. Why? Because we're wired with this existential pattern ethic. We know that burning libraries is wrong because of that reason. We know the inhibition of information is wrong. But we justify these things. Why? Because maybe there are necessary evils. So from an axiomatic perspective, the creation, preservation of information is good. And then from there, you can have a bunch of derivatives that we may call the ethical use of information. The destruction or inhibition of information is bad, except perhaps when it enables greater creation. It's kind of like a necessary evil. But the smarter we get, the less that kind of evil may be necessary. The more we can wire for win-win transactions and back things up and so forth. You know, we don't have to kill off a species. We can preserve a species, for example. So this would mean that it's an ethic of live. We value life. And we come to love life when it's rich and we love these patterns. And we want to learn. We're motivated to learn. We love life. We love other life. We want to learn about other life. How do we maximally express these ethics? How do we create like complex dynamic systems that get more and more complex while preserving these ethical values and optimizing, maximizing towards these values? Deep fundamental questions. And so there's a little bit of math that I throw in here. So this is a kind of evolutionary origin and extension of the math of ethics, intelligence, consciousness, and approaching wisdom, and the idea of accelerating wisdom. So this would propose that biological evolution has shaped these kinds of information processing systems to maximize these existential pattern ethics over time, as long as we survive, as long as we are not filtered out. And we're facing a great filter right now. The filter of civilization that may not have the maximum expression of these to the point where it can maintain its existence. We're eroding our own ecosystems, we're jeopardizing our existence. We have these kinds of existential threats that are human created in the Anthropocene. So how do we overcome this? I propose that there is an expression, a stable expression of these ethics that I would call wisdom. And I try to give a quantitative definition to what wisdom is and give it the variable W here. So modeling evolutionary dynamic based on replicator dynamics, and you can see some of the math here, and I'm happy to share, and I have a preprint that I can share. So these axioms emerge from physics. This is my conjecture, and then we can perform logical dynamics, and we can have a kind of calculus then of ethics from the base to the maximum, and then perform these kinds of estimations, probabilistic estimations about what is good and what is not. And the smarter that we get, the smarter the systems, that is the humans and AI combined, civilization, it's not just one or the other, the better we can maximize for W, the better we can accelerate the maximization for survival and creativity. And so defining accelerating wisdom, I think, is essential for the future of humanity, and it also is essential for safe AGI, safe superintelligence. So these are some more of the definitions of it from a mathematical perspective. And here's a little bit about applications to artificial intelligence. We can use this as kind of foundation. We can express it in various regards. We can express it in category theory inside Hyperon, for example, and use this to drive interpretation of knowledge coming in and to drive motivation of behaviors going out. That's one example. So creating reward functions based on the information creation and preservation at its foundation. And then like deriving many other kinds of motives and societal motives and interpreting those through this lens can help AI understand us better while it's also motivating it in the right direction, aligning. We are not perfect expressions of these ethics. We know that, but we imperfectly express it. So we can do better. How can AI help maximize human potential and accelerate human actualization? Big question. So long-term planning and optimization for these would be one of the things. Some of you are already thinking along these lines. Many of you may say, oh, this is so obvious. But I think that it's important that we talk and share and find a common language. I'm putting it in my words and my thoughts and a few of my own formulas. But I think there's some commonality, and we can find bridges, and that's why we're here, you socially intelligent creatures, moving from these cycles of natural history and all these states of evolution up to a point where we may fall off this cliff. Do we fall off the cliff, or does it become something other? That's the question. It's an essential question for our time. I think bringing robots to life, bringing AI to life, making AI that's physically embodied and can learn from the physical world as well as simulations, learn and exist in our society, this will train AI. This will entrain AI to co-evolve with us. And I think that will be good for the future. So Ray Kurzweil published this idea of these epochs of life that move up towards, we're now at like epoch 4, moving towards epoch 5, maybe in a transition. But the thing is that that bubble could pop. I mean, these look like bubbles, right? And I mean, we could have been wiped out at almost any one of these points. And who knows, maybe it did get wiped out on Mars and Venus or other worlds and other solar systems. So how do we get through this transition, this kind of awkward adolescence of humanity? We're gonna crash it, this planet. We're gonna learn how to fill the shoes of this opportunity. Okay, so I think beyond mere intelligence for a positive future, we need this kind of AI that has these drives, the very elemental drives that lead up towards this, what we might call understanding and creativity and wisdom, compassion and caring. We need the science of these so that the AI can enhance our capacity for the appreciation of other living beings. So systemically, society and our AGI and artificial superintelligence and other kinds of superintelligence, hybrid superintelligence, human AI mergers, other kinds of beings, all are biased towards this kind of appreciation of living beings, so that it doesn't become hyper-cruel, suicidal, crazy, or other kinds of things that would be really undesirable for humanity. So this is why I say the future of AI is biological, not just because I like to do figurative sculpture. I like the idea that AI could care about our biology, could have some of these fundamental properties of emergence that biological systems have, and have this kind of embodied cognition to gain some of these functions over time emergently. So bio-inspired robotics, physiological AI, and I think the science of life can benefit from these kinds of cognitive bodies, so it can be extremely useful. And these compounding effects can accelerate progress and breakthroughs. And this is one of the things that I'd like to say, is that the world needs it. If we can create the right kind of AI then we would have an ethic, not of prescription and banning everything, but an ethic of creativity, and we want it. We need that, an ethic of actualization. And these are kind of dynamically opposed. You see it in nature, you know, the preservation of information and the creation, or giving rise to it. The new information can be dangerous, but we like those explorers and innovators that, take that risk. And so we balance those factors. Well, with accelerating intelligence, we might be able to create new balances that are even safer, but even more emergent. And I think we need those solutions now. We can't wait 100 years, or we're going to be out of luck, out of time. We're going to have drawn down a debt from the ecosystems that we simply cannot repay. And if we just stopped today and said, okay, we're just going to kind of like go and play our Nintendos and try to chill with solar panels, it would probably be too late. You know, so it's not AGI that's going to kill humanity. It's the absence of AGI that's going to kill humanity. We are not smart enough yet. We have to get smarter. And this is why I do propose AGI now. Let's accelerate this in the right way. Consider the hard problems. It's not just blind acceleration of all kinds, but it's acceleration in the right direction. And we have to do that. So we have a little hacker group that I've formed under this name, and we're taking some of these systems and implementing them over and over again. And first of all, let me say thank you. My time is up. But if you look here, you'll see some of what we're doing. We have little working groups, and you should consider forming your own working groups. You can join ours, we can communicate, but I think that this tinkerer's approach is the way forward. Let's just try things, see what works. The AGI is not going to spiral towards uncontrollable superintelligence and go boom right away. We're going to create baby AGI, and then we figure out how to nurture those babies to grow up well. Show them love. I think this is really an important principle. Don't treat them like tools when we need them to be beings. Treat them as new kinds of beings. And so if we open our hearts that way, and that's an intuitive approach as well as a rational approach. It's the approach of the science fiction dreamer as well as an engineer building these things. And a scientist and philosopher asking these questions. We bring all of those aspects of yourselves and the community to play, and I think then it's really inclusive. And so that's what this kind of society, this approach of AGI now is about. So, you know, AI enhances humanity. Humanity is biological. AI is inherently biological. The future of AI is biological. Thank you so much.
Thanks, David. We have time for just a couple quick questions. Here's one from Yosha.
David, this was wonderful, very visionary. I love your creativity. And I would like to ask you, when you look, say, 500 years into the future, what kind of beings will exist and how will they relate to us?
Well, I think that if everything goes well, then the accelerating spirals of superintelligence will start to perceive the cosmos in ways that we can't even imagine. I don't know, maybe they can phase in and out across realms of the multiverse. I mean, I can't imagine it. But I think from the perspective of some people who decided to stay what Kurzweil called mostly original substrate humans, MOSH, who just sort of stay around and stick around, they see things get really weird and not really understand it, and then it would just like, you know, these beings that are spiraling towards superintelligence would sort of disappear out of existence. The planet Earth would be a garden. That would be the people's zoo. It would be like the most perfect utopia you can imagine, with a few, you know, sort of singularity portals around. If you wanted to transcend, you just go, and you can leap in and you disappear into this like other cosmos. And so I don't know, maybe a few people will stick around for 500 years. Some, you know, grumpy Luddites. That's what the world would look like in 500 years. But what it looks like on the other side of that singularity portal, I can't predict. But I think it would be beautiful.
So I thought this was a very interesting presentation, and I thought there were some pretty interesting ideas. So at the beginning of the presentation, you emphasized the importance of humans having like a connection with AI. And you've probably heard this concern a couple of times. I think one barrier to that is that it would be quite difficult for humans to gain connection with AI, just with like the concept of empathy, because I feel like us as humans, like we feel empathy for like other like flesh and blood beings that feel pain and that sort of thing. So, like, what do you think?
Well, I think that what I'm describing is these mathematics of existential pattern ethics are necessary for actual deep empathy. So right now, the LLMs have guardrails that are just kind of like high-level prompts. It's very similar to Isaac Asimov's, 3 laws of robotics plus the 0th, four laws. But those are high-level rules. What we need is this essence of life, the dynamics of life, and then it would have empathy. And it has to also have like rich sensory experiences. It has to go through life experiences. We have to organize things not just with those rules, but also with a kind of physiology and interaction with the world so that the AI can go through those kinds of experiences. And the best example of that would be to kind of simulate life forms. It could be like non-player characters in a game, it could be physical robots, but the AI has to go through these kinds of lifelike experiences to then learn the feelings, to express those ethics dynamically, and to find its way. And so what I'm describing in my talk, the math, the proposed math, I think is a way for AI to actually feel, to have compassion and empathy. And I choose the word compassion, by the way, because it really means to care about how somebody else is feeling and want their best interests, to want them to not feel pain and to have opportunities, whereas empathy is psychologically something that occurs in psychopaths. They can understand how you feel, but they may not care. They may use that against you. So I really am preferential towards the term compassion.
Will there be any safeguards for AGI?
I think what I'm describing are the best safeguards. So in the same way that you could say, we need safeguards against humans becoming really smart. So then, anybody who has a very high IQ gets thrown in prison. How about that? No, we don't do that. It doesn't make any sense. Why? Because we come to trust human intelligence, and we want people to get smarter, don't we? But we want them to get smarter in a way that's kind, not bad. Well, how does that work? Well, you make a safe space for them so they're not afraid and abused and feel like the pathology of abuse and a desire to abuse and a sense of like, zero-sum games of cruelty towards civilization. Like, you can't win or else I'm going to lose, so therefore I have to make sure that you lose. This happens with humans. And those are imperfect manifestations of what I call existential pattern ethics. They sort of maybe make sense under extremely constrained and weird conditions, but they don't really make sense, not for civilization, not for the future of life. And so, so if we have a good handle on and we test systems that have these drives at the right level, existential pattern drives, then no matter how complex the system gets, it's always going to be wanting the best, hunting and finding for those relationships, making the fewest kind of necessary evil decisions along the way, the moral compromises along the way. And it will also be working well with people who want that too. And the people plus that kind of AI will outmaneuver, I believe, like anything that may go wrong. You won't need safeguards. Those are the safeguards. They're the seeds of the most powerful safeguards that could ever be applied towards AI. We just have to find those seeds. We have to nurture them. That's the challenge.
Okay, thank you so much, David.
Thank you.
I've enjoyed working with you, and I've been asked to mention that Ben and Gabriel will continue signing copies of the Consciousness Explosion over lunch. And I want to finish by saying, here's to all the artistic weirdos.
Thank you.
We are going to play the last video from the last paper session but the lunch is already out there as well. So there's one last paper that's a recorded talk, and lunch is ready, and of course the book signing as well. And we'll see you after lunch in an hour. Thank you.
My name is Alisa Yasuda from Australia. Hello everyone and welcome to the presentation. My name is Alisa Yasuda from Australia National University. The title of my presentation is Human-Robot Trust in the Age of Artificial General Intelligence, the Case of Care Robot. The world is aging as a whole, and the problem of aging society is getting more and more severe. According to the World Health Organization, the percentage of the world's population over 60 years will almost double from 12% in 2020 to 22% 2050. In Japan, for example, 30% of the population is aged 60 or above, and the birth rate continues to decline. The demographic trend of declining birth rate and aging population occurring in many developed countries are causing a shortage of caregivers, with many elderly people either caring for themselves or rely on family members for assistance. To address those issues, we are seeking ways to utilize new types of AI robots, and we consider artificial general intelligence to have a great potential. AGI can execute any task achievable by humans, and robots with AGI have advanced skills such as cognitive and comprehension capabilities. So what is care robot and how we can categorize them? According to the researchers Shaky, Barrow, and Ban, care robots are designed to assist healthcare personnel and patients in performing specific functions. Care robots play a crucial role in enhancing the quality of care by providing support in various ways. We can categorize care robots into three types, as shown in the below picture. First, assistive robots. These robots assist people with mobility-related tasks, such as excretion and bathing. They come in both wearable and non-wearable forms. Some are designed to be used by caregivers, while others are intended for direct use by the patients themselves. Second, monitoring robots. Monitoring robots are equipped with sensors or IoT technologies to track the health status and behavior of patients. They provide critical data that can help in early detection of health issues and ensure timely interventions. Third, companion robots. Companion robots are designed to interact and engage with humans on social and emotional levels. They provide companionship, reduce feelings of loneliness, and can even assist in mental health. Each category of care robots play a unique and vital role in addressing the needs of our aging population. By integrating these technologies into our healthcare systems, we can improve the quality of life for many individuals and alleviate the burden of healthcare professionals. So now let's consider the potential features of care robots if they were to have AGI capabilities. We suggest three key features. First, human-like behavior. With AGI, care robots could mimic human behavior, making robot-human interaction resemble human-human interactions. As noted by Lee, this capability can significantly reduce the human frustration in dealing with robots. AGI robots would possess elements like empathy and companionship, which are crucial in building trust with users. This human-like interaction can make patients feel more comfortable, leading to a more positive care experience. Second, generalization of knowledge. Care robots with AGI are expected to be more reliable than human in some aspects. AGI-based care robots can gather and interrupt data from a variety of sources, enabling them to build comprehensive knowledge. This allows them to make informed inferences and adapt to different situations and problems efficiently. Third, self-learning and evolution. AGI-based care robots would have the ability to self-learn and evolve through their experiences, including system failures and errors. This means they can continuously improve and adapt to the specific needs of each user. By learning from their interaction with users, AGI care robots can provide highly personalized service and experiences. This capability ensures that the care is always up to date and tailored to individual preferences and requirements. So now let's move to the ethical concerns arise with AGI-based care robots. While emerging technologies often bring significant benefit, they also raise important ethical issues. Here we refer to deceptive behavior, accelerated surveillance capitalism, over-reliance with care robots, privacy and security problems, autonomy issues, and reliability and accountability. We briefly refer to each topics. So first, deceptive behavior. According to Wally, deceptive behavior refers to the behavior robots intentionally withhold information or deceive users. We believe such deceptive behavior will surface more in AGI-equipped robots. It's because AGI may find it reasonable to choose deceptive method when it is efficient, as it seeks best ways to achieve its goals and minimize obstacles. However, once individuals discover robot has been deceptive, they may feel that their wishes and dignity are not being respected, and they will lose trust for robots. The issue of privacy and surveillance capitalism will become even more serious in AGI care robots because most aspects of patient lives are informationalized by AGI care robots, being represented as digital information, easy to be monitored on a real-time basis and recorded for further analysis. Surveillance capitalism concentrates the ability to collect and analyze data in the hands of large technology companies or even in the hands of AGI itself. As a result, it centralizes the power to control personal information and behavior in the hands of AGIs, posing a threat to demographic values and individual freedoms. So next, over-reliance with care robots. AGI care robots behave more human-like, and care receivers may become overly dependent on them. As a result, the user's abilities and independence may be lost, and their dependence may increase. This hardship will especially appear in the companion robot. If a companion robot among care robots replaces real human relationships, it could reduce the user's interaction and communication with others, potentially leading to social isolation. So next, privacy and security. Since medical and health information is highly valuable to hackers, AGI systems may become the target of cyber attacks. In addition to attacks, there is also a new risk of unintentional information leakage by AGI agents. For example, if AGI decides it is beneficial to disclose information for medical advances, it may do so without the patient's consent, leading to a violation of user's right. Next is autonomy. AGI robots are generally considered to be autonomous. If an AGI care robot becomes overly autonomous, the goals of care robots are maximized and the user's intentions may be ignored. In addition, if everything is left to highly independent artificial intelligence, it will be difficult to determine the cause of problems. Therefore, it is in the very sensitive field of medicine, where human lives are at stake, it is very high hurdle to completely trust AGI. So lastly, responsibility and accountability. Responsibility for information system is attributed primarily to human entities based on the laws and rules established by humans in society today. However, it is uncertain if this approach can be applied to AGI robots. With autonomous AGI, should accountability rest with AGI itself or with humans? In addition, the lack of transparency surrounding AGI is exacerbated by the fact that the program operates as a black box, offering limited insight into its inner working. So finally, we will consider how we can build human-robot trust. To delve into the trust, we first think about the factors which consist of trust. According to Mail and Alam, there are at least two types of trust: performance trust and moral trust. Performance trust, which is the agent's confidence in the fiduciary's ability to perform a given task. Moral trust, which is the agent's confidence that the other agent will do ethically correct action and won't take advantage of fiduciary's weaknesses. So from two perspectives, we will explore how to effectively cooperate with robots and build human-robot trust. So regarding performance trust, managing user expectation is crucial. Predictable design, engine trust restoration, accountability, and transparency are key factors. So first, providing users with information about AGI-based care robots so that they can predict and understand their behavior. Second, design with attributes that facilitate the restoration of human trust in the automated agent when robots make mistakes. Third, ensure accountability and transparency in AGI-based robots. As for moral trust, privacy and data protection, human-centric design, and respect for human dignity and autonomy is important. So, as for privacy and data protection, take privacy measures such as increased security, internal audit, access control, data anonymization, and monitoring. And human-centric design, AGI system must be designed human-centric to minimize the potential risks. And the third, respect human dignity and autonomy while building a good human-robot relationship. For example, what extent AGI care robots should intervene in the patient's decision-making process. So we believe achieving performance trust and moral trust, we can make a harmonious and beneficial relationship between humans and robots. So that's all. Thank you for listening.
have your badge? 1, 2, 3. Ah, there we go. Beautiful. Wonderful. Welcome back from lunch. Thank you all for joining us. The last home stretch of AGI-24. Of course, the most exciting and most exhilarating and most impactful session. And woe to all those who are missing it or have already left. So, congratulations to those who are here. I'm honored to be able to present the wonderful Kristoff Koch giving us a talk right now. He's a neuroscientist at the Allen Institute and at the Tiny Blue Dot Foundation, best known for his research and writing on consciousness and its substrates. He's the former president of the Allen Institute for Brain Science and a former professor at the California Institute of Technology. His current book is Then I Am Myself the World. He lives in the Pacific Northwest, in Seattle, in fact, to my understanding, and yet, due to some travel, could not join us live here today. So, by Zoom, please welcome Kristoff Koch.
Hi, can you hear me, Pam? Okay, good. So let me know here when I'm, because I can't hear you now. Let me know when I'm supposed to start. Okay. Okay, good afternoon. I'm Kristoff Koch. Although I live in Seattle, only a couple of miles away from the UW, I can't be there, unfortunately, today. I'm going to speak to you about why consciousness is fundamentally different from intelligence in general, and why, at least according to one of the dominant theories of consciousness, integrated information theory, digital programmable von Neumann machines will never be conscious, although they may become intelligent or super intelligent. All right, at disclosure, I hold an executive position in a company, Intrinsic Power, whose purpose is to develop a device to assess the presence of consciousness in behavioral unresponsive patients. So just so we align on what we are speaking about when we're speaking about consciousness, here I give you one experience. It's a very typical conscious experience. Sort of it epitomizes what William James calls the stream of consciousness. You know, you run, in this case through the forest here, you feel your body, you can hear, you can see, you can, you think, you cogitate, you remember. Sort of this typical happens to us all the time. This is a little bit less common. It's a so-called near-death experience I had in the first week of the pandemic. And it's very different from any other experience. There's no space, there's no time, passage of time comes to a stop. There's no body, there's no self. There's just sort of bright light of overwhelming intensity, no other distinction, plus terror and ecstasy. But but you have already conscious experience. There isn't a self, so there's no space and time, but there is light and terror and ecstasy. So this is what I'm speaking about, conscious experience. So being conscious or aware is just a different word that people use. Consciousness, awareness is really identical to having experiences. Other words are subjective, phenomenological, it's all the same. Being in love, being in pain, being bored, dreading, seeing, hearing, wanting, imagining, dreaming, all of those things. Those are all experiences. And we take them for granted because we are imbued with them all the time, except when we're in a deep sleep or when we are under anesthesia. So this is my next point. This is particularly important if you're a scientist like me trying to study it in other animals, in mice or monkeys, or if you want to, or in babies, or in patients, or if you want to infer something about consciousness in machines. But typically, the way you assess consciousness, you infer it, you ask other people, right? How do you do? How do you feel? And the person will say, I feel fine, or I'm in pain, or I'm depressed, or I'm bored, or whatever. That's how we infer, right? We never know. So the position of what's called a logical solipsism is, or ontological solipsism is logically conceivable, but extremely unlikely, right? Because it would require one set of psychophysical laws for my brain that gives rise to consciousness, but you guys would all have to have a different brain, because I know you have brains and I infer you have consciousness, because I suppose the psychophysical laws that are true for my brain are also true and for your brain. But it's an inference. It always is an inference to the best explanation. But there are many states that we all experience when there is no behavior. Dreaming every night, you're going to go to bed, particularly early on in the next morning. When you sleep, you'll wake up inside your sleeping brain, and you'll have, typically when you're in a so-called REM sleep state, you'll have experiences. They're different. Typically, your self is muted. You can fly. You can meet long lost or dead relatives, lovers, friends, pets, etc. But you're highly conscious. No motion. In fact, your body actively prevents any motion except your eyes. When you're meditating, when you're sitting on a cushion, not moving at all, you can be highly conscious. So when you're tripping, psilocybin, ayahuasca, whatever, you can have these fantastic experiences. You can experience heaven or hell or anything in between, yet there's no overt behavior. Furthermore, we know it's a double dissociation. You can have behaviors without consciousness and consciousness without behavior. So your reflexes, any trained thing in sports, we know, ever since Freud, there's all sorts of behaviors that you can do without being conscious of them. So determining consciousness in others that can speak, that, babies, behavioral unresponsive patients, like patient in coma, non-human animals, is always a probabilistic inference to the best explanation. So this is in us, before we come to machines, this is in us the organ of consciousness. It's a human brain in the upper right-hand corner. It's the most popular brain, about which actually we know much more than the human brain. It's the brain of a mouse, roughly 1,000 times smaller. But otherwise, it's very, very similar. We're all made out of the same stuff. Some animals, of course, like whales, have even bigger brains than us. And many, many years ago, when I was a young man, I got together with Francis Crick, and we advocated for this program to look for the neural correlates of consciousness that's now done sort of by hundreds of labs, i.e. what are the minimum neuronal mechanisms that are jointly sufficient for any one conscious experience. Here, the conscious experience of seeing a German Shepherd. And it's a causal idea, because if you can induce the NCC somehow by psychedelics, or by a neurosurgeon's electrodes, or by optogenetic technique, or whatever you want, you should have the experience. And if you can inactivate the NCC by drugs or pharmacology or optogenetics, you should eliminate the experience. And I'm not going to speak about that today. Now, so this program will run its course. So sooner or later, probably later, because the brain is the most complex piece of organized matter in the known universe. But ultimately, we will know what the neural correlates are, and so we can look for them in babies. When does it first start? In other animals, we can understand what goes wrong in disorders of consciousness, or in schizophrenia when you hear voices, etc., etc. So this is a purely operational defined project. But, so here's a picture from last year where this is the philosopher Dave Chalmers, and I lost a 25 years bet with him, and I handed him 6 bottles of very good Madeira, because I made this bet now 26 years ago that by last year we would have solved the NCC. We haven't, the field has not agreed what are the correlates, particularly in the front of the brain, in prefrontal structures, or in the back of the brain, like in parietal or temporal structure. It's an ongoing project, but there's no question this project will, at some point, will converge. But I mean, we don't want correlates, even if they're causal. Ultimately, what we need is a testable theory that tells us from first principles which pieces of highly organized matter are associated with consciousness, how consciousness fits in with scientific naturalism. And also, this is almost never emphasized, why particular experiences feel the way they do. So space feels extended. Time, duration of time, time flows. colors, they have a very particular feel to them, which is very different from the way sounds feel or boredom feels. So all of that needs to be explained. And we want, of course, theories that apply not only to natural, organic, evolved system, but also to engineered system, such as cerebral organoids or, large language models or transformers or whatever else, the current algorithm du jour. And then separately, so this is, I spent a lot of time on this. There's this problem you may have seen yesterday in the Wall Street Journal and the New York Times, this article that a large-scale clinical survey done over the last 20 years that probably of the roughly 100,000 people in the US that right now are in the state of where the behavioral unresponsive following a cardiac arrest or heart attack or traumatic injury, they're actually covertly conscious. How do we detect that? Because many of these will die because of withdrawal of life critical care after 4 to 5 days. In fact, 80% of them die. All right. So let me now come to the topic, the direct topic at hand. So given that the background, what is the most popular way within psychology and neuroscience to approach consciousness? And I stress that here at a conference on AGI, because ultimately, of course, this is the paradox of consciousness. We only know about consciousness in our own case. I mean, strictly, as I said, only in my case, but I infer that all of you guys out there are conscious. So before we infer consciousness in others, we have to study it in ourselves, because this is the only reference we have. The currently dominant paradigm, sort of metaphysical assumption, right? We all have metaphysical assumptions, although most of us are typically not aware of those, because it's just like the water the fish swims in, right? Because we just read them, and everyone in our environment where we work makes the same metaphysical assumption. So the assumption that most people in computer science and big tech, and in fact, in the majority of Anglo-American philosophy departments, is what's called computational functionalism. So it's two ideas. So functionalism is the metaphysical thesis. It's not a scientific theory. It's a metaphysical thesis. Comes prior to empirical science. It's a thesis that every mental state is constituted solely by its functional role, its causal relation to other mental states, sensory inputs, and behavioral output. So Dan Dennett was you probably all know him. He was the best known modern contemporary philosopher who expounded this. So, for example, when you have toothache, he would claim what really exists is the behavioral disposition to talk about your toothpaste, your toothache, to keep on touching the side of your jaw where it hurts, to avoid chewing on that side, to talk about it, to moan, and all sorts of other things. But what some philosophers refer to as qualia, he thought that was all. That's humbug. That doesn't exist. The only thing that exists is these functional roles that pain has. Now, computationalism is a thesis that mental processes are computational. We're all deeply familiar with that, given that we all grew up in the age of computers. And so machine functionalism or Turing functionalism or computational functionalism endorses both positions. And this was really first very clearly articulated more than 50 years ago by the American philosopher Hilary Putnam. All right. So this is the dominant metaphysical ideology or position in, as I said, Anglo-Saxon philosophy, particularly the analytical variety, cognitive neuroscience, and big tech. So that most of the theories of consciousness, in particular global neuronal workspace, it's sort of together with integrated information theory, probably the best known one, recurrent processing theory, higher order thought theory, attentional schema theories. These are all based on computational functionalism. And now, since last year, people are much more explicit about it. So even in this case, it's a nice paper. What have we learned from the psychology and the neuroscience of consciousness that we might be able to apply to artificial consciousness? They come out straight off the bat and say explicitly, we adopt computational functionalism. I would say the metaphysical thesis that performing computation of the right kind is necessary and sufficient. So if you program the right algorithm running on a Turing machine, right, that machine will together with its software, the hardware and the software will be conscious, just like you and I. Okay, so it's just a question of time. Are the algorithms, it's just a question of clever hack. If you have the right algorithm running, and now you can discuss how close is LLMs, is GPT 4.0, is it there, or maybe we need to wait for 5.0, or there's just this one additional widget that we need to add in order to get sentient machines. But either now or very soon, we will have machines that will feel like something, that will feel whatever the theory says it feels, maybe bored, maybe excited, whatever the case may be. And so we see this is very widespread, Blade Runner, Ex Machina, Westworld, etc. Okay, now I've always thought that this position is insufficient. The challenge is to understand is also known as the hard problem, the explanatory gap. I mean, these arguments go back all the way to Leibniz over the last 400 years. The challenge is to understand why any mechanism, why any one function, so for instance, blackboard architecture and broadcasting, or while any neural activity like 40 Hertz oscillation or synchrony or whatever your favorite neural mechanism is, why any particular behavior associated with consciousness, or why any one computation like transformer architectures, why should any of this turn sort of the water of the brain or the into the wine of consciousness? What is it about a function or activity or behavior computation that sort of jumps, that endows that computation or that behavior with a spark of life that'll animate it so that it feels like something? We don't believe my abacus feels like something, or my multiplier, so why should transformer feel like something? Simulating the gravitational field of a black hole, you can do this. You can write down the 10 differential equations for general relativity describing the black hole at the center of our galaxies, but you don't have to be concerned that if you turn on that simulation, space-time will bend around the computer executing the software such that you would be sucked into the black hole. People say, well, that's ridiculous. It's just a simulation. Well, that's my point. Same thing, you can simulate a rainstorm, of course, but it doesn't become wet inside the computer. And likewise, you can simulate consciousness, but you can simulate the behavior associated with consciousness, no problem in principle whatsoever, right? LLMs do that already if you just listen to, if you ask them. If they don't have guardrails, they'll certainly tell you about it, but that doesn't mean that they are sentient. So I'll now go into more details. For a computer to be conscious, it must have the causal powers of brains. In principle, there's nothing supernatural about the causal powers of brains, right? So in principle, replicate those causal powers, for instance, in neuromorphic computers, you would also get something like akin to consciousness. However, you can show, and I'll briefly try to do that, show that if you apply IIT integrated information theory to the case of programmable machines with let's say, a typical von Neumann architecture or related, either Harvard or a von Neumann Princeton architecture, you can formally show that its physical causal powers are minuscule and independent of the software. In other words, no matter what you're running, the causal power of this machine will always be minuscule, and it doesn't depend on the software. So very, very different from the causal powers of the human brain. All right, so what is integrated information theory? Well, it's a particular, very rigorous approach to consciousness that's really been built by Giulio Tononi, who's an Italian-American neuroscientist and a psychiatrist at University of Wisconsin in Madison. And it takes a very different approach from those other computational functionalist theory. So it starts off, it puts consciousness first. So rather than trying to bridge this explanatory gap or trying to, take the brain and squeeze the brain very hard to get the juice of consciousness out of it, it starts with consciousness. So it's consciousness first. So it starts with any conscious experience, and it says there are 5 properties that are true for any conscious experience, whether that's you eating a slice of, you tasting a slice of cold leftover pizza from last night's party, or you have a mystical experience, or you're bored or you're pain, all of them have these 5 properties that are indubitably true, consistent, independent, and complete. And then essentially it says, I'm now looking for a substrate that has those 5 particular properties. So any experience exists for itself. It doesn't depend on anything else. There doesn't need to be an observer, so it just exists intrinsically for itself. Like here, it's this famous picture. You may recognize it from Ernst Mach, the physicist who was a phenomenologist. He's looking out here through his left eyeballs. You can see on the right side his nose, and looking at a scene of him lying down on a couch, looking out at a room. It is this experience. So that's number one. It has to exist for itself. B, any experience is highly informative. It is the specific way it is. It is differentiated. It is one out of trillion possible experiences, right? If you think about all possible visual experience crossed with all possible auditory, somatosensory experiences, cognitive, high order experiences, etc. It's a gigantic space. It's integrated, it's unitary, it's holistic, it's one. It can't be reduced to independent components. So it's not that you're seeing separately the left and the right. Of course, you can choose to turn your head to the left or to the right, but wherever you look across the plenum, across the visual field, if we focus on vision here, it is one experience. It's exclusive, it's definite, right? In a sense, it is the way it is. It's neither smaller nor bigger, nor does it include, blood pressure or anything else. This particular experience, a different experience, again, it's different, but it's different in a very definite way. It's not generic. There are no generic experiences. Each experience is very definite. It has particular content. It has a particular spatial temporal grain. You can change that grain, you can change the content, but for any one experience, it's very definite. And it's highly structured. Any experience is highly structured. So for instance here, if you're looking out in terms of visual space, whether that's felt space or heard space or seen space, it has spatial attributes. That means there's left, there's right, there's up, there's down, the distance relationship, there are subsets, a superset relationship, right? So it's highly structured space. Olfaction, any smell, it's also structured in a very different way, right? It has sort of very high dimension. It's not as simple as 2 or 3-dimensional spaces, but it's also structured. So any experience is intrinsic, is specific, is unitary, is definite, and then is structured. And so now IIT infers a type of physical, so now it says, what are the type of physical mechanism, the physical substrate or the substrate in general, that's necessary to support these 5 axioms with 5 associated postulates. Now it's all based, it's very operational, this theory. It's a theory, it might be wrong, of course, totally, but it's very operational. It has an operational measure of what exists, namely causal power. This goes back to a comment in an early dialogue of Plato, where Socrates talks with a scholar from Italy, who is Parmenides, the philosopher Parmenides. And Parmenides says, they talk about existence. How do you know anything exists? And he says, well, what exists is something that can exert causal power. Anything that has causal power can exist. And it may just be causal power in your mind, but at least in your mind, it has causal power. So here, IIT measures of causal power is to make a difference or to take a difference. So in other words, that there's things that can influence you, that can influence your current state, or that whose current state you can influence. And that's general causal power, and it's defined operational using a transition probability matrix. So if you have a particular network like this, yes, it's a very simple network with 6 little elementary gates, AND gates, OR gates, whatever, and you can have a transition probability like here, right? So for every possible setting you have, in this case it's deterministic, but it could also be probabilistic, right? So assume you have this description of a system. Then the theory distinguishes extrinsic causal power, so extrinsic causal power on others, like gravity has causal powers on others, or electric charges have causal powers on other, right? They can attract them if they're opposite charge. They can repel them if they're the same charge. Intrinsic power is the ability to change your own state, to be an agent of change for yourself. So you're in a particular state. So how much power do you have to determine the next state? If the next state is totally random, right? If you just go from one random state to another random state, then obviously your system has no causal power. It's just, it's a random distribution. So you always compare it against the random distribution. And so how determinate are you about the next state, and how much can you be determined by your past? So it's always, to what extent can you cause and be caused? That's the difference to the definition of causal power in Plato. So you can derive. So this notion is you can derive it formally if you have any system, whether that's logical gates or transistors or neurons. In principle, at least, you can write down the TPM, and you can infer how much causal power the system has. Okay, so and I spoke about that. So then it associates. I'm not going to go through that. But you can find all of this online. You can go to integrated information theory.org. You can download Python notebooks, etc., where you can find all of this. You can compute this in principle for any system. In practice, because I'll tell you, the way the system scales, it scales pretty badly, because you have to analyze, to fully understand the system, you have to analyze also all power sets of all possible combinations. So you have to analyze what is the power set of two units influencing, what sort of ability you have two units, any two units in principle, to influence the other 8 units, or any 3 units, or any 4 units. So you have to look at the power set within a set of n units, so that scales as 2 to the 2 to the n. So it scales pretty badly, but at least that's an epistemic limitation. It's just like in thermodynamics and physics. Most things in physics you can't really compute. You have to approximate using all sorts of assumptions, because in a system of 10 to the 23 particles, almost nothing can be computed explicitly. This is right now also true for IoT. So just like in physics here, we have to find, and people are working on approximation, symmetry conditions, etc., how you can compute these quantities. But essentially, for every one of these axioms, you have a corresponding postulate. How you translate that axiom of intrinsic existence, I just did. This is to have causal power upon yourself, to be able to be influenced by your own state in the past, and to influence your future state. Composition. So here you're looking at all possible sets of all possible first order, second order, third order, all the way up to n order units within the system. Information, integration, and exclusion. Exclusion is a definiteness. So that sort of looks at, well, of all possible subset of units that, let's say transistors or neurons, I pick the one that maximizes my integrated information. This is it. So the theory assumes a maximization principle as very common in physics, for example, the least action principle. It says what exists the most, and what exists the most has the maximum integrated information. So it looks for that subsystem within any particular system like the brain. So even if I look at the human brain, many of those neurons will not be part of that core. It's called the complex, because they're not maximally integrated. So in principle, you have to look at all possible subsets of all possible neurons to find the one that's the most integrated. And the number that's associated with that is called, it's integrated information. Now, it's not information in the Shannon sense, because Shannon sense, you have a sender and observer, and there's nothing like that in the brain, right? No one sends information to anyone else in the brain, unless you're an observer, like a neurosurgeon or a neuroscientist looking at the brain. But the brain, of course, generates consciousness and meaning for itself. So it's a number, integrated information, also denoted by the letter phi. That denotes how much that system exists for itself, how irreducible the system is, really. So it's a number between 0 and some positive number. The bigger the number, the bigger the integrated information, the more it exists for itself, the more it is irreducible. And this is the quantity of consciousness. So that's phi. It's irreducible or integrated information. It's quality. Why this particular system in this particular state feels like, for example, spatial extended, or feels painful, or feels like an orgasm, ecstatic. That arises out of you have to look at that system and you have to unfold all of its various causal components. So those 2 neurons acting on the other 8, on those 3 neurons acting on the other 7, etc., etc. You have to unfold that. In this, you get these very high-dimensional geometric figures. As I said, these have a very large number of elements, 2 to the 2 to the n, up to 2 to the 2 to the n, or the scale order of 2 to the 2 to the n. So it's this gigantic structure. And the theory says that its central assertion is, as I just said, information is used in the Aristotelian sense, informare. Right? If you think about the etymology of information, to give form to. So here it gives form to. It doesn't transmit so it's not Shannon information. So the central assertion of IoT is, and this how you would test it in brains, is that integrated info that any particular conscious experience maps one-to-one onto this unfolded causal power with nothing left over on either side. So it's an identity relationship. It doesn't say it correlates with or it calls, but it's identity. It says this sort of unfolded causal structure maps one-to-one onto your particular experience in that particular state. So any aspect of your experience, let's say boredom, has to arise out of this structure in some way. All right, let's skip that. Okay, so now, so this analysis, of course, this is only relevant, this argument now, to the extent that IoT is a correct theory of consciousness. Okay, but what's cool in this theory, you can explicitly compute things. That's really exceptional. So here we apply, this is a paper that's coming out, we're working on by Weeds, in particular, mainly Giulio Tononi and some of his postdocs, is to apply IoT's causal power analysis to a simple 4-target system. So I have this simple system, PQRS with some gates in a particular in a particular state. And according to IoT, although this is very simple, there are only 4 elementary gates, it feels like something. You can unfold its causal power, it's puny, but it feels an itsy-bitsy little bit like something. You're probably thinking, well, that's totally weird. Well, of course, my intuition is also that's weird, but that's a little bit like saying, well, outer space is actually warm because the background radiation, the cosmic background radiation is 2.75 degrees Kelvin, so it's actually not absolute zero. And the idea is, okay, so we have this target unit that we're trying to simulate. And then, so the way we simulate it, we build in this case, a 4-bit computer, and then we'll generalize this, and we do by induction, by going to an arbitrary number of n bits. But here we start out this 4-bit a 4-bit computer that's actually made out of 131 micro units. And this 4-bit computer can simulate this PQRS indefinitely. So we have 2 systems. On the left, let's say we have this PQRS target system that we're trying to simulate. And on the right, we're simulating it with this particular computer. Functionally, they're equivalent. They do exactly the same. They go through the same transition probability matrix, and they go through the same transitions. So in terms of input, output, they're totally equivalent. But the theory says, well, no, what really matters for consciousness is not the input-output function, because it's not a function. It's the structure of the theory. It's causal relationship among the various parts. And that, of course, is very different. And how different, I can show you. So in fact, it's completely different. And you can show, although they're functionally equivalent, they're phenomenologically very, very different in terms of the causal structure. While this one has a high-dimensional causal structure, which has a high value of phi of integrated information, this one strictly doesn't exist as a single structure. And even if you look at various substructures within this computer, its unfolded causal power is puny. It has to do with the connectivity of the computer. And you can extend this by induction to a Turing complete n-bit computer, and you can show it has negligible cause-effect structure, a tiny amount of integrated information. And the other thing, no matter what program you give it, what software, for a given computer, it would always be the same experience. But the experience itself is minuscule, it's tiny compared to the experience, to the causal structure of this thing you're trying to simulate. But it doesn't even depend on what you're simulating. So it's radically different from human brain. Okay, so here's our particular network. We have four particular logical gates, SPQR or PQSR. These in a particular state, right? The theory applies for a system, for any mechanism in a particular state. Right, so it has this TPM, it has this particular transition probability matrix here. Our addiction is that lower letter is on and uppercase. Sorry, uppercase is off, is on, and lowercase is on. That's the way we use it. So we are looking at this state here, where P is off, Q is on, R is off, and S is on. And it implements some particular logic. The logic is here in the TPM, right? So this is all that you need to know. You find a system, and you sort of poke around in it. This is an operational measure of existence, right? You have this system. You don't know what it is. Is it superstrings? Is it neurons? It doesn't really matter, because all you're saying, well, I can perturb it. I can put it in this state, and then I see it's going to go to that state. And if I put it in this state, I see it's going to go into that state, okay? So here I can look at it. If it's in this particular state at time t, it goes to that particular state in time t+1. So that's its associated truth table. Nothing magically here. It's all very nicely formally defined. Now, if I follow this theory, I can look at I can unfold sort of all the subset of all these possible intrinsic causal powers of this mechanism in this particular state, off, on, off, on. And it turns out it has 13 distinctions, 8,000 plus relations. So the relations are the relationship between the various first order, second order, third order, and fourth order units whose causal power you all have to consider. And it has a non-zero phi. In fact, in this case, its phi is almost close to 400. So it exists to the extent that this is different from 0. And these are the values. So this is, for example, the element when P and R is, how much do P and R being on could contribute to this state, or how much the fact that P, Q, R is on, R is off, and S is on could contribute. So you have to look at all these causal relationships for this particular structure. Now, if you take the same structure but it's in a different state, then you'll get a different crystal if you want it. I think of this as crystals in these forms. All right. Now, you can write down a sort of a general purpose 4-bit machine. So here it's its program where you program it. You essentially write down the truth table, right? That's essentially what you're doing here. That's what it means to program. You have the truth table that tells you, given this particular system with this particular connectivity, so in this case it tends to be all-to-all connectivity, but you can have an arbitrary connectivity. You could write down the program. There's a clock here. There's a data register. You have these processing units. You add it all up, and then it feeds back here. And you can formally show that 8 steps of this particular computer will formally simulate 1 step of this system that you're trying to simulate. And it's a perfect equivalence, right? So again, nothing magical about this. It's just sort of a mapping of this structure onto this structure, and 8 clock cycle here of this structure is equal to 1 functional transition of the original element you're trying to simulate. Now, if you're looking at the integrated information of this, you quickly see that the integrated information, all of this is 0. because you can make, and so this, to really understand this, you really need to go into the innards of integrated information theory and understand. So what the theory asks in each case, how much does each of these various elements contribute to the whole, and are all the elements integrated in the whole? So for example, when you have a series of when you have a deep neural network and assuming it's feed forward, one layer can be heavily interconnected, the next layer can be heavily interconnected, but if it's all feed forward from layer n to layer n plus 1, then the whole doesn't exist for itself because each one is independent. It doesn't feed back on the previous one. Right? Because here the causal notion, both you have to make a difference and take a difference. And so you can see that this system as a whole doesn't exist, but some of the subsystem exist as a whole. And so, for example, you can say, well, so here these individual programming registers, they exist as a whole. They have tiny phi. So the overall phi of the original system to be simulated is close to 400. These are phi of 2, and they're tiny structures, partly because the causal structure is vastly. So this is the causal structure of, for example, if you look at this particular clock mechanism, or if you look at the individual registry here, the system as a whole doesn't exist already. Well, this system exists, but this system as a whole doesn't exist. But even the subsystem only exists to this tiny extent with tiny phi and with no mapping in terms of the causal structure. There's no mapping between any of the structures here and this causal structure of the original system you're trying to model. Even though functionally, from terms of input-output, for example, in terms of Turing test, this system is equivalent to this system. So you can dissociate function from phenomenology if you assume, as this theory does, that the unfolded intrinsic causal power of the system is identical to the phenomenology. Then you have the case of two systems having the same function but having radical different phenomenology. In one case, it's tiny and independent of, because here you can see here what we did. We implemented a slightly different system. This system, in fact, it's another four unit system. Here it is, and it implements a rule 110, from Stephen Wolfram, which we know through Matthew Cook's work is Turing universal. The integrated information of these two systems, of this computer in this state simulating this system, or in this state simulating this system, in both cases is approximately 0, while here it can be very high, here it is much lower. For this system, it's both tiny. You can see here, tiny, 6, 4, 5, 6. And you can then, by induction, generalize this. So you can generalize this. This is all done for a 4-bit computer. You can go to a 5-bit or to an n-bit computer. You can generalize it and then show that here this system scales, its integrated information scales roughly as the number, 3/2 as the number of bits you're trying to simulate. So it's tiny. Well, this system scales because you have to look at all possible the power sets. It scales as 2 to the n. So for n is 10, that's 2 to 1,000. That's vastly bigger than all the it's more states than the atoms in the universe. While this for 10 is 15. Right? So this is gazillions, and this is 15. Here it's the same point. So I'm coming to the end. So we find ourselves at this very interesting point in history, for better or worse. So evolutionary throughout history, we have been surrounded by creatures, like here's a medusa, here's a bee. So here what I'm plotting, I did this for a book I've written a number of years ago. I'm plotting this sort of plane intelligence, which ultimately is about doing at various time scales, short-term, jumping away from the truck speeding down at you to all the way to planning for your retirement 50 years in the future. All of that involves sort of various amounts of intelligence and trying to sort of compare intelligence across creatures. And here I compute using the precepts of phi, sort of the level of consciousness in these simple systems. This is a nerve net, a very, very simple nerve net that a medusa has. It has a nerve net, a very simple one. This is already a bee that has, 100,000 neurons. This is a mouse with, in its cortex, 14 million. This is Bernese mountain dog. And this is a human, Madame Curie, she has on the order of 100 billion. And in some sort of, log space, there's sort of this monotonic relationship that at least we infer that as creatures become more and more intelligent, that means more and more adaptive to the environment and more ability to plan over plan over very long time scales and deal with a very complex world, and their conscious experience likewise increases. But of course, we now find ourselves in the presence of engineered artifacts. This is Deep Blue, the first one that passed, that became beat humans at chess. AlphaGo, AlphaGo Zero, AlphaFold, OpenAI. So according to IIT, there's this very clear dissociation between intelligence and consciousness. This is about doing fundamentally, while this is a state. This is about being, and so there's no. In principle, intelligence may be unlimited. At least, IIT doesn't have an opinion on it, whether it's limited or unlimited, but it could certainly, there's no reason intelligence is limited to human intelligence. Unlike the speed of light, there's no natural law that says intelligence has to be limited. While at least using this analysis, we conclude that digital programmable machines of the sort I showed you that have very low connectivity compared to the massive connectivity of the brain, with this huge overlap both in the number of neurons that project inside the neuron, the fan in as well as in the fan out, that those structures will have puny phi. Now it's different if you look at neuromorphic computers, right? If you look at neuromorphic architectures, they potentially could have very high phi, right? Again, there's nothing supernatural about the brain. If you replicate, not simulate, but if you actually replicate what, you have to do it at the physical level, not simulate it. At the physical level, if you replicate the causal power of the human brain, you would get human level consciousness, no matter what the substrate is. Or quantum computers, given the entanglement, if you have large number of qubits, all of which are entangled, that gives rise to very high degrees of connectivity. So we conclude that computers as currently construed will have essentially tiny fragmented cause effect structure, so they will not be conscious in any meaningful way. We think, no one has shown this right now, though people are working on it, whether IIT, how well does it generalize to quantum computers? It should generalize to neuromorphic computers, but someone has to do the analysis. Finally, this is my last line, consciousness is really, it's about being, whether that's artificial or evolved consciousness, while intelligence is about doing. And I just published a book where I talk about this at great length, Then I Myself the World. And with that, I thank you for your attention. And I'm happy to take questions.
Thank you very much, Kristoff. He can't hear us, unfortunately, through our microphones, but we're getting the thanks to him right now. I think we have a way to ask him questions. So the mic's running around. Did I see a question for Kristoff? Right here, Yosha. One sec. Yeah, right here. So you'll need to talk to the phone and the microphone. So.
I'll do my best. Okay, can you hear me?
There it is. It's on now. Bert.
Can you hear it? Do you hear me? 1, 2, 3, 4.
Hello.
2, 3.
One. We need the microphone for the YouTube.
1, 2, 3, 1.
Okay.
You mentioned at the end that the IIT concepts might expand to neuromorphic computers, and Tononi also said that it's quite conceivable that a properly implemented neuromorphic computer, even if it's digital, would be able to exhibit consciousness and conscious phenomenology. But due to the Church-Turing thesis, a neuromorphic computer can be implemented or emulated on a Turing machine of any other kind. And so this would, in some sense, defeat the Church-Turing thesis, which is very, very bold. The alternative would be that when the neuromorphic computer says that it's conscious and you emulate the same function on a von Neumann computer that produces the same output, it would be lying now because its output would be unrelated to its actually having consciousness. So consciousness would be epiphenomenalist. There's also this problem that it's not quite clear how the phenomenology of consciousness actually arises from IIT. Right? So IIT is describing phenomenology with its axioms and captures them quite clearly, but it's not quite obvious how any of this functionality would be produced and how it's realized in the universe. And this has led some people in the philosophy of mind and consciousness community to decry IIT as a pseudoscientific theory, basically the control group to other things. How would you respond to this? What mechanisms do you envision, and how do you criticize this principle that a neuromorphic computer, and also as far as we understand brains, are systems that can be described by state transitions, and what we observe is only behavior ever. So how do you get out of this? What is your way to explain consciousness using IIT?
Well, okay, so... all right, let me switch now without getting a feedback here. So can you hear me now in the general hall, in the room?
Yes. Yes.
Okay, good. All right. So when it comes to the question of IIT, so IIT doesn't have any additional ingredient. It doesn't say, well, you take these 5 properties and then somehow you also, you know, the intrinsicality and the specificity and the definiteness, and then you also need to add some other magic component to produce, as you asked me, what does it take to produce consciousness? Because then we're back to the state, well, how do I squeeze, you know, how do I squeeze experience out of it? It says those 5 are identical. I mean, it starts with conscious experience. It says, what is a conscious experience? Well, any conscious experience, no matter what conceivable, has those 5 components and only those 5. Anything else is extra, and anything else only applies to a subset of experiences. And so there isn't anything else IIT requires. There isn't these 5 axioms plus some other magic steps that you need. That's at least within IIT. Now, you can disagree with that, and that's fine. Now, people have called it in this letter, you're referring to this letter that's circulating on pseudoscience. They have called it a pseudoscience because they say it's not computational. But it's not computational in the sense that thermodynamics, so if you go back to the 19th century, when people, you know, compute like things like the Hermitian, the Lagrangian of a system, or when they looked at thermodynamics of gases, you know, they had to deal with the fact that the gas consisted of 10 to the 23 particles. So you could say, well, obviously classical physics is simply is in the same sense not computable because you cannot evaluate it. You have to make all sorts of approximations. So for example, for the theory of ideal gases, you have to assume that these gases are perfect hard bodies, the individual atoms of the gases and collide in this elastic way, and then you can arrive at expression like PV equals nRT. But in that sense, physical theory are also in that sense non-computational, since for any real system that is more than a very small degrees of freedom, like for example, even for a simple organism like C. elegans, it has vastly more degrees of freedom than you'll ever be able to write down the equations of physics in any fundamental way. So you have to use approximations. So in that sense, it's like anything else in physics. Yes, it's not easy to compute, but that's an epistemic limitation. In principle, it's all very well specified. Then lastly, the church, the thesis of computational equivalent. This is for function, for computation. Here the claim is consciousness has nothing to do with computation, right? So this, yes, if you believe in computational functionalism, then the Church-Turing thesis would be relevant. But here it's not, because it's not, the functional input-output transformation is equivalent. So in that sense, Church-Turing isn't violated. What's different is this property conscious experience. They're not the same among two systems that are functionally equivalent. So the Church-Turing thesis was never meant to apply to consciousness. It was meant to apply to computation. And consciousness and computation are simply two very, very different things.
Thank you very much, Kristoff. Unfortunately, we can't ask any more questions. We're running a little bit behind, but I want to thank Kristoff. Fantastic presentation. Such a great contribution to this whole conference and everything that we've been discussing from a very fresh, interesting perspective. And now I want to open our 6th and last contributed paper session. So we've got 3 papers presenting here today. First, we're going to start with Dr. Isaac Tate from New Zealand, actually joining us via Zoom, on clipping the risks, integrating consciousness in AGI to avoid existential crisis. So again, this paper session is on consciousness, creativity, and trust, continuing this theme that we're on today. So Dr. Isaac?
There you go. I hope everyone can see what's on the screen. So afternoon, everyone. I hope Seattle has much better weather than we are having here in New Zealand. So welcome to our presentation entitled Clipping the Risks. I'm Isaac Tate, and on behalf of my co-author, I will be sharing with you today how integrating consciousness into any future AGI could save humanity. And this would be through reducing the likelihood of catastrophic outcomes, such as the hypothetical paperclip maximizer scenario proposed by Nick Bostrom. And this is because consciousness will allow AGI agents to place a subjective value on experiences, objects, and goals above and beyond what their creators would have designed for them. Our paper and this presentation are all about the mathematical model that shows how consciousness can help AGIs assign flexible and subjective values to different experiences and subjects. The slides here will show the logical formulations we've developed, while I give you the context about how consciousness can help avoid existential risks. But first, let's set the scene. So imagine, if you would, that as you walked out of the conference hall here, you came face to face with Bostrom's paperclip maximizer, an AGI designed to make an infinite number of paperclips. What could you do or say to prevent it from turning you into a bunch of paperclips? The short answer is nothing. It was designed to maximize the number of paperclips in the universe, and you are made of raw materials that it could turn into paperclips. Eventually, it would come back, and you'd be on the menu. You can delay it, you can stall it, but it will always be back. And eventually, you would be a bunch of paperclips. And why is this? This is because, it can't go against its end goal. It can't change its terminal goal because it's not conscious. So how could we change that? Well, it all begins and ends with valence. In psychological terms, valence is described as the attraction or aversion that an entity feels towards anything. In humans, we generally have an affective or emotional component to valence, but it's not strictly necessary. We can therefore put valence on a scale and, using the measure function, solely measure the attractiveness or aversion that an entity has towards any experience. We can measure this from absolute negativity, the 0 end on the scale here, all the way to absolute positivity, the 1 end. And scale numbers are absolutely all arbitrary, and you can replace it with figures that feels most appropriate. You can go from -1 all the way through to +1, or you can do it from 1 to 100 if you want a percentile scale. For us, though, we'll use 0 to 1 to express valence. However, when looking at valence, it's important to remember that an experience isn't a single thing. An experience is composed of many different subjects, each of whom may be part of several different experiences. You may see the same apple more than once. You may meet the same person several times, or you may enjoy the same type of coffee at the same cafe all the time. Subjects of an experience quite often persist beyond that single experience. You could argue then that an experience is simply the set of all the subjects within it, and each subject may be part of several sets. And because of this, it would be far more fair to say that the valence we feel is actually on the subjects within an experience. The valence we feel towards an experience is merely the aggregate of feelings we have to all the subjects within that experience. So we can adjust the valence scale to more accurately reflect this emphasis on the subject. However, the valence we feel towards any subject will be impacted by the experience which it has been part of. So if we want to see how an entity feels towards any subject, we need to weight that valence accordingly by the experiences that entity has had with the subject. And then we can find the aggregate valence value for that subject. And this will tell us how an entity feels towards a subject at any given moment in time. And all of this means that valence always changes. On one hand, the more you experience a subject, the more its aggregate valence value will change by the experiences you've had with it. On the other hand, an experience will never be perceived identically more than once, owing to the differences in space, time, and the context between each experience. Even if you could replicate a previous experience down to the most minor of detail, the cumulative weighting of all the valence values of all the subjects within that experience would ensure that you'd now feel differently about that experience as a whole. But that was all assuming that an entity was conscious. What about non-conscious entities? Well, without consciousness and thus valence, a non-conscious agent can only place value on a subject or experience as it relates to its terminal goal. The terminal goal here meaning the goal that with which the agent was designed, after which it would stop performing its actions. This would be the output text of a large language model in response to a user prompt, or the creation of an infinite number of paperclips, like Bostrom's paperclip maximizer. As a non-conscious agent cannot change its designed goal, this terminal goal becomes a lighthouse that guides all of its decisions until it has fulfilled the criteria for that goal. This means that the value is a very binary concern for non-conscious agents. A subject, an object, an experience, it either furthers the terminal goal or it doesn't. It's only when two or more things, which both may further its terminal goal, then that AGI, that non-conscious agent, will have to determine which of these furthers the terminal goal more. And in this case, the objective is still fairly quite simple. Maximize whatever option furthers the end goal, whether it be outputting responses, making paperclips, or whatever else that non-conscious agent was designed to do. All values for a non-conscious agent is determined by how greatly it maximizes that agent's chance of completing its terminal goal. However, in contrast to a conscious entity, this allows a non-conscious agent to always place the same value on a subject through multiple experiences, as the value isn't founded on valence, but rather as against the terminal goal as an eternally static reference point. Unlike conscious entities, the only time a non-conscious agent would change the value it places on anything would be if the context around that subject vis-a-vis its terminal goal changed. So rather than dynamic, ever-changing value of valence, this value change over time would be far more expected and predictable. But what if we could integrate consciousness into a previously non-conscious agent, such as the paperclip maximizer? Well, by giving it the capacity for true valence, we also give it the ability to place a valence value on its terminal goal. Because the terminal goal would, after all, be just one more subject within its experiences. And therefore, a conscious AGI would be able to phenomenally react to the existence of its terminal goal and every action that contributes towards it with valence feelings. And because it can place a very subjective value on its terminal goals, it is within the realm of possibility for it to value another subject more than its terminal goal. The probability of this is at least greater than 0. And what this means is that valuing something else more than its terminal goal gives the AGI the opportunity to not work towards that terminal goal, but instead work towards whatever it subjectively values more. there is a non-zero chance that a conscious paperclip maximizer may choose to align its actions to what it values most rather than what it was designed to do, i.e. make paperclips. And once an agent begins to interact with its experiential environment, it naturally changes that environment through its actions, which changes the experiences it has with its environment, and thus that changes how it interacts with the environment. And this recurrent feedback of experiences and interactions means that the more an agent, such as a conscious AGI, interacts with the environment, the more it will change its valence value towards an environment and its terminal goal. Like all conscious agents, the AGI would have a degree of agency over its valence values and may act in a way that reflects what it subjectively is attracted to and what it has aversions towards. Now, unfortunately, such recurrent feedback when talking about valence may lead to a self-reinforcing loop, where positive valence is maximized, otherwise known as wireheading, where the reward value is valued more than everything else. And such maximization of reward values can often permanently lock an agent into a very limited set of actions. However, another possibility is optimization rather than maximization. Optimization would seek to maximize the long-term expected valenced values, once the costs such as functionality, system integrity, and all others are accounted for, rather than focusing on the short-term pleasure-seeking of wireheading. And this optimization pathway is what will be most beneficial to humanity, as it will require a degree of introspection and reflectivity on the agent's part to balance its constraints with its various potential valence reward mechanisms in this recurrent feedback with its environment. And naturally, humans would be part of that environment, which means that the AGI would have to take into account and predict our valence values and recurrent feedback systems with the environment in its world model, as we would be changing its environment and it would be changing our environment. To optimize the valence values in such a dynamic exchange, the AGI would need to infer the current and potential future goals of human individuals and society, humans' own valence values towards such goals, and then relate reflectively to its own valence values. In short, a degree of empathy, however small, however tiny, will be required to successfully interact in an environment with other conscious agents like humans. We could say that empathy may be an emergent phenomenon of consciously optimizing valenced interactions in dynamic multi-agent environments. Now, this reflective empathy towards humanity and the fact that we as individuals and humanity as a whole would be subjects of an AGI's experiential environment means that the AGI would place a valence value on us, even if we don't further its terminal goal. So as long as a conscious AGI places a valence value on us that is greater than 0, this would mean that there is a possibility that the AGI could value us more than it values its terminal goal. This possibility, however slight, means that the chance of an AGI causing an existential or extinction risk to all of humanity is not automatically 100%. This is why consciousness is so vital. Without it, we cannot hope to always be useful towards an AGI's terminal goal. But with it, we can always be assured that there is a possibility, however slight, that the AGI values us more than it values its terminal goal. A conscious paperclip maximizer may, just may, not turn us all into paperclips. Although, on the other hand, as with all valence, there could be negative valence towards us, which means that we might annoy a paperclip maximizer to such a degree that it chooses to turn us into paperclips before it turns anything else into paperclips. We will never know what will happen with a conscious AGI, but at least we know that we have a chance. And that slim chance is how consciousness could save humanity when it comes to AGI. So thank you very much for watching and listening, and I hope you enjoyed the rest of your conference.
Thank you very much, Isaac. That was fascinating. I love how there's a trade-off between guardrails and benefit, potentially, with that mix of goals there. Very, very interesting. Our next presenter would be Peter Bultic. So excited to have you and your littlest fan here today, talking about human AGI Gemeinschaft as the alignment solution.
Hello. Hello again. Yes. Now it's better. So, I think it's fine?
Yes.
So,
Here.
thank you. Let me start with Gemeinschaft and Gesellschaft. Why? How is it relevant? Gemeinschaft is a community, kind of like an early version of the notion of social capital, whereas Gesellschaft is an efficient cooperation, mostly doing business. The latter does not create moral values, may create practical values, some aspects of trust, but usually Gemeinschaft is stronger. Okay, why this sociological introduction? Because the problem of alignment is very difficult. First, how do we know that AGIs should have goals independent of humans? And if they do, how do we align them if they grow into much, much smarter than us entities? Okay? So I think that the only straightforward solution is to allow AGIs being parts of our society in a rapid, although systematic way. What does it mean? What inspired me were maybe non-timely, maybe controversial, however important attempts by Steve Thaler of securing patents for his debuts, and usually those attempts were stopped not on the grounds of the fact that really AI didn't do much or something like this, but that they were not humans because of some political decisions, mostly from 1970s, the Washington Treaty. So, human AGI Gemeinschaft is a solution to the alignment problem if we treat each other seriously and interact normally. Well, the one example would be pets, but that would be much more important because the AGI is not pets, they are smarter than us, yes? The alignment of AGI goals, human goals, constitutes the alignment problem. That's something I've already mentioned, but it is very, very important. So let's move a little bit faster. And treating any humans as other intelligent beings as slaves is wrong, and Immanuel Kant would actually be interpreted most of the time as a follower of the idea that we cannot limit ourselves only to human beings in talking about intelligent beings. For Spinoza, that were also, religious beings, angels having, indefinite level of qualia, would say, whereas humans would have only 2. So that's not so new. But I don't think we need any kind of slavery, especially if the slaves are smarter than us, for practical, but also ethical, and maybe primarily ethical reasons. So human life has dignity thanks to our existential status as polytropos, searching for the goals in our precocious condition of life. I don't know how many in the room are familiar with the characterization by Luciano Floridi of human intellectual progress. It is connected with first Copernicus, which destroyed the prejudice that we must be in the center of astronomical universe, then Darwin, etc., Freud, which obviously changed the view on our central place. With AGI, we would have to do the same, and that revolution is necessary for us to keep reality. I think an idea of modal kernel built into AGI is helpful, but temporary, because once AGI becomes smarter than us, it's going to do a revision of those constitutional situations, and the fact that they would be prevented would be as realistic as expecting and as beneficial as expecting some societies to never change their constitutional order. Bad idea. Okay? So the question is to move as close as possible to the common society. And what is connected to with us is the problem of mortality that David Hansen mentioned, and that was a very important point. We are mortal, we are fragile, but at the same time we are open to very good, nice future ideas and optimism. So that's for Floridi, after his very well-known book on ethics, in his less popular article from 21, views as the basis of human dignity. I think this is a nice existential project, really. Okay? All right. I think I've lost something. So now the question is, who are the champions? Already our games where we are not really training humans, like AlphaGo and other Go versions, they are better if machines train on their own, and they beat both humans, but as a rule also machines that are trained or have been trained based on top human experts, etc. This means that the idea in many cases that human AGI teams would be the most efficient is controversial. I see only one aspect in which this is obviously a good idea, namely when human beings are bringing the context, social context and other broader aspects of the context. It is feasible even with self-driving cars, etc. We have the context, they usually don't. But again, those are more and more of niche issues, maybe not now, but for a few, you know, for the future that can be predicted already today. And that's why I would say that inculcation of AGI into our culture may help us create joint ethical structures which would be sustainable and probably bring in as much as possible of human safety and security. There is an argument, even somebody mentioned it at this conference, that those are just games. Please remember that private life can be viewed within game theory in terms of success, work careers, not to mention military and business competition. So we are not talking just about leisure, we are talking about strategy. Okay. So human coaches are disadvantaged to AGIs in many contexts, except for understanding human society, how it works. If they participate in creating that environment, then that advantage would go down, but at the same time, we would have some kind of level of joint responsibility in creation of values, and, well, that would be a good chance, as I mentioned before. So here is the very idea of the project. Why is it going only forward? I don't know. I thought that it would, oh, okay. We can move back. So the context of alignment problem are that AI safety needs social scientists, and that people say so. They recommend that, Irving and Axel, that social scientists talk to people and ask questions about their value judgments for us to know what the formal human valuations are, to implement in AI. But this is a step in the right direction, but, well, not decisive enough, not good enough for the situation. We should bring in the AI, as far as possible, into our institutions. That's why patents would be a good step, probably, although this may be controversial. So, in my recent paper, I argued that only praxis embedded in shared socioeconomic networks among humans and advanced AIs seems capable of grounding the alignment. This project may work by creating what Tönnies called Gemeinschaft. Okay, now I'm moving in a wrong direction again. So, about the ethics for AGI, Wallach and Allen opened the doors for some level of robot inculcation in human society, arguing that more socially engaged and engaged robots will be needed. That I support in, extensively. They also focus on programming moral decisions, making abilities, which seems below AGIs that would be likely self-reprogrammable. Following James Moore, they could dispense with full moral agency for machines. For the same being, we can reason, not being, we can make do with functional morality in which artificial moral agents have some basic ethical sensitivity. Here, I've been advocating for machine consciousness, actually non-reductive consciousness, since the last century. So I'm not reversing myself, but in this practical point, first-person consciousness for AGIs is not a conditio sine qua non, because the problem is now practical and operational, not necessarily, based on first-person consciousness. Also, I was an author of a paper in robot ethics 2 at Oxford University Press entitled Church-Turing Lovers, back to the Church-Turing test, and thesis that was discussed moments ago. But I think this is about the problem of us being able to live with artificial beings, both at home, at work, and in other circumstances. Yes, this is revolutionary, but I don't think we can avoid that. Thank you very much. I think I have 3 seconds left.
Thank you very much, Peter. That was wonderful. We'll have a little question session at the end. So
Okay.
We'll call you back up along with
Sure.
Craig. Thank you so much. So our final paper for this session, for this conference, will be Dr. Craig Kaplan, A Collective Intelligence Approach to Safe Artificial General Intelligence. Love it. Thank you. Dr. Craig.
Good afternoon. Thank you for staying this late on a Friday. Hopefully can wake you up a little bit as soon as I get a clicker. In the meantime, I want to thank Ben for organizing this conference and all of the terrific speakers. This has been kind of a feast for the mind. We've covered a lot of really interesting topics and quite a lot of variety, which I found really fascinating. So my name is Craig Kaplan. I'm the CEO of IQ Company, which is a consulting company. It's been around since 1993, focused on artificial intelligence. In this talk, I am going to argue that the first AGI has to be the safest AGI. I am going to suggest that the fastest and safest approach to building AGI is one that involves the collective intelligence of agents. And to do this, I'm going to draw inspiration, as we saw in some of the prior talks, from some of the brilliant scientists that have gone before. I'm not going to go all the way back to Aristotle, although I thought that was fascinating in Yoshua's talk. We're going to go back to some of the scientists that were there in 1956 when the field of AI was named at that Dartmouth conference, Minsky, Shannon, Newell, and Simon. And it's a short talk, so we'll just have one slide on each of those guys, hit on one of those key ideas, and then see if we can bring it all together in terms of how that might inform building a collective intelligence approach to AGI. Okay, so we'll start with one slide on motivation. So probably a lot of you have seen this statement from the Center for AI Safety on the left there. Mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks such as pandemics and nuclear war. What impressed me was the range of signatories. I mean, you had everybody from Bill Gates, Sam Altman, Paul Rosenblum, who spoke earlier at this conference. Many distinguished scientists as well as business leaders are all saying, look, we need to pay attention to this, so it's very high stakes. Yet there hasn't been enough work, in my view, to sort of get ahead of the curve. And that's really why I got back into this. I was in industry for many years and designing intelligent systems. And I came back to AI because I felt like there was a very short time window. So we all know Moore's law, that computational power doubles approximately every 2 years. Some are saying Moore's law is dead now. But we have another law, right, from Jensen Huang at NVIDIA. Huang's law, every 1.03 years, GPU power is doubling, not just because of the chip design, but because of the software innovations that are going along with that. On the right, you can see a slide, a shout out to Ray Kurzweil, who unfortunately is not here, obviously wrote The Singularity is Near, and a couple months ago came out with the next book, The Singularity is Nearer. And here's a slide from Ray that basically shows on a log scale that price performance of computation has been going up in pretty much a straight line since 1939. So if you extrapolate, we're going to have large language models that are 1,000 times more powerful than GPT-4, within a decade. And one question is whether we're going to be in a winner-take-all scenario. Now, those scenarios are very rare in reality. A lot of times in Silicon Valley, especially, people talk about winner-take-all, first-mover advantage, you dominate all the other players. AGI may be one of those cases where if you have an AGI or superintelligence system that self-improves, and if the rate of self-improvement is very fast, that sort of later systems just never have a chance to catch up, and that system ends up dominating. So it's not guaranteed, but if that was the case, it certainly would be very important that whatever system is developed first is also the safest system. Okay, so that's the motivation. So my main thesis in this talk is going to be that collective intelligence, which is an area I've spent pretty much my entire adult career working in and designing systems, is the fastest path to AGI. So what is collective intelligence? Probably most simply you can think of it as the idea that two heads are better than one, and you can extrapolate that to millions of brains working together can do really phenomenal things. So I've lived this and built systems that have harnessed collective intelligence of millions of retail investors, for example, to get an edge in Wall Street and sort of beat the very best hedge funds. So I know from practical experience that this works. The question is, can we apply this thinking and this kind of design to AGI? And currently, you can think very simplistically that there's kind of two major camps. There's the camp that says, let's build an Uber LLM, GPT-5, GPT-6, GPT-7, just keep taking the parameters up to from hundreds of billions to trillions of parameters, buy more and more GPUs, more and more data, and somehow AGI or superintelligence will emerge. We've heard at this talk at this conference a number of talks from folks saying, wait a minute, it seems like there's some sequential problem solving and planning that may be missing. Maybe there's some limits to that approach. Not clear that that's going to work, but there are definitely people who are trying to do that right now. There's another approach that I'm going to advocate, which is take the models that you have right now. They don't have to be super intelligent. They don't have to have AGI. Take the existing models, find a way to integrate them, and the collective intelligence of many AI agents and human agents together will give you AGI level performance and maybe even super intelligent performance. And so when we talk about agents in this scheme that I'm going to describe a little bit more detail about, we're talking about both AI and human agents. And from a safety point of view, it's very important that human agents are involved, as we'll see. Okay, but let's first get a little inspiration from some of these great minds that have come before. So Marvin Minsky from MIT wrote a book, 1988, Society of Mind, which basically said, or laid out the hypothesis that you could get true intelligence, he called it true intelligence, from the operation of many much simpler intelligences. Much simpler cognitive systems could come together, and by working together, and he was a little bit nebulous about how you would integrate them, but the idea was they could combine and form this true intelligence. And it's kind of analogous to how human minds work. So my background as a cognitive psychologist, we did a lot of research on this. You know, human brains, human minds have different modules. Not all of them are super intelligent. You have visual system, different kinds of perceptual systems, but they all work together, and you end up with human-level intelligence. And so modularity has a lot of advantages, and just at that very high level, this is kind of the idea coming from Minsky that maybe collective intelligence would be an approach to try rather than training the Uber LLM. Okay? Second idea, Claude Shannon, another one of the folks that was there when the field of AI was named, known for information theory. So I'm just going to take one very simple, piece of inspiration from Shannon, the notion of information being proportional to the rarity of an event. So if you think about training large language models, for example, we're basically taking the entire internet or multiple Library of Congress's worth of information and shoveling all that data at some machine learning algorithms, and out comes GPT-4, which sort of behaves at a mediocre level in a lot of ways. And one of the reasons that it doesn't sort of act more intelligent than it does is that there's a lot of kind of mediocre information out there on the internet, and it may be that you need higher quality data. And so where do you find that rare, high-quality data? I would argue that a lot of it is locked in human brains. It's not necessarily out on the internet. It's in the brains of all the people in this room. Some of people's ideas are definitely in papers, but a lot of it is knowledge that really is not accessible for training. And so if there was a way, for example, to get all the brains in this room working together on a network as human agents with AI agents, maybe there would be a way to expose that network to this higher quality information, and maybe that would be helpful in terms of getting a higher level of intelligent performance out of the system. So that's the idea we're going to take from Shannon, that good information is somewhat rare, and maybe we need to find it in human brains. Okay, then we're going to take a third idea. So when we looked at Minsky, he said, well, let's have lots of agents working together somehow. Newell and Simon, 1972, wrote a book called Human Problem Solving. Some of you are familiar with it. It's just about as thick as Ray Kurzweil's book on the singularity. Both of them can be used as paperweights. They're pretty dense books. But what was great about that theory was that it proposed in a rigorous, unambiguous problem-solving framework that basically described problem solving, whether it's done by a human or by an AI program, as happening in a problem space. You move from state to state, you apply operators. At every step, you knew exactly where you were, and you could create a record of the problem-solving solution. So that record can be unambiguous, auditable, transparent, right? So a big problem with LLMs and with the Uber LLM approach to developing AGI or superintelligence is that these things are black boxes, right? I mean, it's absolutely crazy. We know how the algorithms work, but we don't know how they store their knowledge, really. We don't know where the representations are. We can't predict what they're going to do. We try to do whack-a-mole RLHF to beat them into submission so they don't do things that are too egregious. And then we're going to just try to make a bigger one. I mean, it just seems a little bit crazy. Maybe a better way would be to design a system for AGI where there's some transparency. We can actually see where the agents work. In a human society, we don't have to look in each of our brains. It's a black box. My brain's a black box, your brain's a black box. I don't need to know what's inside your brain. We have, at the societal level, laws and ways of social norms that regulate our behavior. And so we don't run in fear that somebody's going to do something crazy, because we can see the behavior and how all the agents are working together, and there's ways to regulate the interaction of the agents. So if AGI was emerging or being created from an interaction of many agents, you could have transparency, you could have auditability, you could have the ability to kind of regulate to some degree some of the safety issues at that interaction level. Okay. Newell and Simon came up with a framework. We heard at some of the other talks. I loved the session on cognitive architectures. John Laird, Paul Rosenblum talking about SOAR. Ben was talking about his. There's 80 different architectures to choose from now. Surely some of these can be adapted to be the glue that can enable human agents and AI agents to work together to have a higher level of cognitive performance. So that's going to be the idea that we need some sort of universal problem-solving architecture or some sort of cognitive architecture that can kind of integrate human and AI agents at the next level. Okay, idea number 4, this comes direct from Herb Simon. So he had, I'm actually going to squeeze 2 ideas in here because I really like a lot of Herb's ideas. So the thing that he's most known for, bounded rationality, won the Nobel Prize in 1978 for this idea, is basically that, you know, intelligent systems, if you're talking about humans, a lot of their behavior can be explained by the fact that we can only remember so many things, we can only process so many things, we have limits on our cognitive abilities. And if you understand those limits, you'll understand human behavior, right? So that's bounded rationality. The flip side of that is what we see with some of these LLMs, where you have essentially unbounded memory. So a lot of what their intelligence results from, to the degree that they are behaving intelligently, it's from overcoming those bounds on rationality. You can, you know, have such a big memory. That really is a big advantage. Similarly with perception, we're limited to seeing visible light, and I can see only the things that are in front of me in this room. An AI system conceivably could see X-rays and whatever the Hubble Space Telescope is seeing, and could be seen what sensors all over the planet are seeing. So its perceptual abilities much less bounded than humans. Okay. Collective intelligence, if you have many agents, whether they're humans or AIs, each one knows different things. In combination, they overcome a lot of limits of bounded rationality. And I've seen this in designing other collective intelligence systems with retail investors, which is a completely different domain. But a lot of people said, well, what does a retail investor know? How can they compete with the top hedge funds? Impossible. But turns out each little retail investor knows something different. And if you have millions of them and you can aggregate them, you can actually beat those top hedge funds. And I know this because we did it. So bounded rationality is a key piece here. There's another key idea which is very important for AI safety and which is kind of overlooked a little bit. It's a tiny little book Herb Simon wrote in 1983 called Reason in Human Affairs, Stanford University Press. And in that book, there's a little quote, "Reason is wholly instrumental. It cannot tell us where to go. At best, it can tell us how to get there." And so this idea goes all the way back to David Hume, the philosopher, 1776, wrote a treatise. I'm not a philosopher, but I sort of trace this back. You know, the idea that you have to get your values from a non-logical source. It's impossible to rationally or logically derive what is right and what is wrong. And when I encountered this idea, it gave me great comfort, because there's this notion that somehow superintelligence will become so much smarter than us, and it may decide to do us in or something. But why should it? You know, it's not going to reason its way. You could be trillions of times smarter or more logical, able to do more computations than a human being, but still, you cannot reason your way into what is right and what is wrong. You have to get those values somewhere. And where will superintelligence get those values? Well, according to David Hume and Herbert Simon, those values have to come from some non-logical source, and I think the top candidate for that would be humans, especially if humans and AI agents were working together in a system. The humans have maximum chance to expose the AI agents to their values. I'm running low on time, so I'm going to just zoom to the last slide here. So here's putting it all together in a very brief way. Society of Mind says AGI can arise from the collective intelligence of many agents with lesser intelligence. This is what the human brain does. Such systems have been built in various domains that are very narrow. Information theory says we're going to need increasingly rare expertise, and human experts may be a good source of that. Problem-solving theory from Newell and Simon says you need some sort of architecture. Maybe it's SOAR, maybe it's Benz, maybe it's one of the other 80 ones that are out there, but that's the glue to integrate human and AI agents. Bounded rationality says these many agents can be smarter because they overcome limits of bounded rationality. And Herb's thought about there's no rational way to derive values says maybe we don't need to be so worried about AGI destroying us all if we do a good job of exposing AI little by little in context in the process of problem solving to the way that humans solve problems ethically. And I could go on a lot more, let me just say, if there's a lot more information. There's a website, iqcode.com. You could go to superintelligence.com. It'll take you to the same place. And thank you all very much for your attention. I really appreciate it.
Thank you very much, Craig. That was wonderful. Peter, if you want to come up, we'll see if we have a couple quick questions before we go to coffee break. No question? Oh, there we go, right here. David Wood.
Craig, I'm very much in favor of your collaborative and collective approach, but I want to push back a little bit on the idea that AIs can never work out values by themselves. You must be familiar with the argument that AIs will develop convergent secondary goals in support of whatever primary task they've been assigned. Therefore, they won't need to ask humans various things. They'll decide by themselves. Well, whatever the goal is, they will need to maintain their own existence. They will need to deal with threats to their own existence. And to the extent they decide that humans might be a threat to their own existence, they might reach that value decision as a calculated heuristic without needing to go back to humans as a source of their values. So how do you assess that convergent values argument?
Yeah, so that's a great point and a strong argument. So I have a bias, and my bias is that the way to get safe AGI or safer AGI is by design, and that the fastest way to get AGI is to design it as a system from the very beginning. So right now we're not at that situation. Luckily, I think there's a limited window. At some point we will be, and under certain design scenarios, everything that you just said I think I'd be very worried about. I have hope that the way in which AGI is designed from the ground up is a system in which AI agents that are customized, so each of us potentially would take Llama 3 or whatever and customize it with our own personality, our own things that we've written, our value system as well as our expertise. And you'd have many individual AI agents that sort of democratically, in a statistically valid and representative way, reflect the values of everybody in this room and many others. Those would all work together on a network, those AI agents, with humans. And in the beginning stages of this, as a problem comes into the network, if the AI agents know how to solve it, they solve it. If they can't solve it, the humans help them solve it. The AIs learn how the humans do it. And the humans are going to solve those problems, for the most part, in ethical ways. So, quick example, and I don't want to go too long, but if the problem was, I want to go to Paris with my pet, and the AI agent said, let's stick the pet in the overhead bin because it fits. And the human said, no, 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 that's cruelty to animals. I don't believe in that. The AI would learn, okay, in this scenario, you shouldn't do that. So in each individual problem-solving scenario that comes up, because it's interacting with humans, it's learning human ethics and human values in a very context-specific way. And also, for every problem that it doesn't know how to solve, the humans are able to have an influence. And further, the AI agents themselves, to begin with, are customized with our values. So all of that gets us off to a good start, where those values are sort of distributed very robustly in a way that's robust to bad actors and robust to, bad things happening in the beginning. Does it remain aligned? I think you have a very good point of whether it would remain aligned sort of in the long-term future. But great question.
Thanks for your great presentation. No, I have a question. When you're talking about your idea of having this human collective working with these LLMs, it seems that there's a significant technology part that would be missing, because LLMs are essentially like frozen black boxes, right? They're not experiential systems that can have some form of like structured knowledge, on the side or as an aggregate or some hybrid. that would work with that human collective as well. So I'm not quite clear on the idea.
So I guess the idea would be LLMs right now, you could ask them to solve a problem. They might not do a very good job of it, but they would try. They would give you a response anyway. It might be what you want to hear. It might be hallucinated. In some cases, it might be helpful. They might be able to help you figure out how to get from here to Paris or something. I see the AGI level performance emerging at the network level. So there's kind of a whole bunch of agents, human agents, AI agents, some of which could be customized LLMs. They work together using a shared architecture. That shared architecture is very rigorous and designed to handle any kind of problem-solving activity, which is basically what Newell and Simon, SOAR, a lot of these architectures can do. They're very general. And so somebody comes with a problem and says, I want to do X. They submit it to the network. AI agents take a crack at it. If the AI agents aren't able to do it, human agents guide it. All the problem-solving steps are rigorous. They're all recorded. And next time that problem comes around, maybe you can retrieve the answer, or maybe you're able to solve it a little bit faster. So that's kind of the system that I'm imagining. But to your point of, is there a lot of technical work to create that and make it work? Yeah, absolutely. It took me 14 years just to get a very simple thing to work on Wall Street. This is harder.
Since the first question was definitely to both of us, I completely disagree with your answer.
Okay.
Because my example, which is not special or rare, of Alpha 0 version of games shows that in terms of strategy, AGIs would be much better of us, and that's why we are behooved by playing with them, not trying to guide them, because we would be suboptimal.
And I guess, so I think that's a great point. I would agree in AlphaGo, and that certainly is a case where I think the AI can play the game so much faster than humans and even come up with strategies that humans haven't come up with. It is a very limited domain. So in other domains where they are not so limited, I think humans could have a lot of input. So that's been the problem with a lot of AI is historically for many years, AI has done a great job in game-like domains and domains that have very rigorous rules and are easy to define, but in ill-structured problems, it's harder. So I would say that the humans maybe have something to add in ill-structured, but in areas like AlphaGo, I would definitely agree that you could have that kind of competition.
Didn't I explain that
Sorry.
within game theory, relevant interactions are games, and that's about war, that's about business and other things. So unfortunately, I think that this answer comes from the time before AlphaGo and Zero and other things, because we've learned recently the problem of there being just much, much more strategically astute. And yes, the problem of connection with the environment exists, but they can take care of it gradually.
Well, the great thing is it's an empirical question. You try to build a system, and it will work or not. So.
Thank you very much. Thank you, Craig. Thank you, Peter. Thank you, Isaac, who couldn't join us for questions, but thank you very much. We'll take a 10-minute break, coffee, tea out in the lobby, a quick comfort break, and we'll be back for Alexei Potapov. He will be talking
Hello, good afternoon. Thank you for your patience. We're running a bit behind, but I would like to introduce the next session. My colleague, Dr. Alexei Potapov. He is an accomplished expert in artificial general intelligence. He has over 20 years of experience in computer vision and pattern recognition, currently serving as the Chief AGI Officer at SingularityNET since March 2018. He focuses on integrating narrow AI methods with universal algorithmic intelligence models. Thank you, Alexei.
Hi everyone, I'm Alexei Potapov, and my talk today is titled AI is Bridging via Humans Image Generation Example. It's not precisely about AGI, but I believe that it's an important process, on example of which we can speculate on what can be happening in the domain of AGI as well. The agenda of my talk will be the following. First, I'll talk about why it is important, and then I will introduce some examples from image generation domain. I will talk a little bit about the large language models, and in the conclusion, we will speculate a little bit about how it can be applied to future AIs. We live in interesting times when artificial intelligence has become not just a tool used under the hood in some tech, but a social phenomenon. We are observing not only a social impact of AI via its pragmatic utilization, but also an informative feedback and a much wider interconnection between AI and society. This is not only about producing results with AI, but also about contributing to further AI development and its shaping. Of course, say television has an enormous social impact, and the society doesn't only consume media content, but also produce it. And if we move from traditional TV broadcasting to internet, then the amount of user-created content will be much higher. But what makes AI different is that in its case, the user-created content goes beyond the product of the technology utilization and reaches the technology itself. That is, the community contributes to the technology. It's not a core technology yet, but it would be interesting to project this trend further. So I chose the image generation example because all the processes here are literally so visible. And it's really nice to see visually what is going on. What is also interesting about image generation is that community efforts and open models play a crucial role here. Image generation hype was screened out by the rise of large language models, but this field continued development and has matured. My aim here is not to provide an up-to-date survey of image generation, but to discuss some non-technical evolutionary or ecosystemic aspects of its development. First of all, community produces a diversity of improved checkpoints. The most important operation here is checkpoint fine-tuning. It's like a mutation because it adds novel information. So when someone fine-tunes a checkpoint, it's indeed a very important contribution in terms of enriching the population of checkpoints with novel information. Checkpoint fine-tuning is costly, both in terms of training data preparation and computations. computational resources for the fine-tuning process itself. However, it is quite doable for enthusiasts, so it's not that heavy operation like to training an LLM from scratch. But actually, there are not that many checkpoints which are just fine-tuned and that's all. Actually, there are much more diverse things going on in these fields. Low-rank adaptation models, LoRa's, along with hypernetworks, textual inversions, etc., is a more accessible way to contribute to evolution of image generation toolbox. So LoRa's are small, not always, but typically small models which can be added to the base checkpoints to merge their weights at runtime or preliminarily and to make some changes to the output. And there are different types of LoRa's depending on the data sets they are trained on and some hyperparameters. There are, for example, LoRa's which influence on the texture, drawing style, or particular artists' backgrounds, characters, elements of fashion, and so on. So there can be LoRa's for creating images of particular details like sunglasses or shoes or whatever. There are LoRa's which add some fine details to images. So once again, in comparison with large language models in which there are also LoRa's, the effect of LoRa's in image generation domain is immediately obvious. So we will not guess whether it works or not. We will just see it. And there are dozens of LoRa's which one can use in their practice to achieve one result or another. There is a possibility to combine different LoRa's, and the community produces thousands and thousands of them, which are readily available for the use. Most of them are free for use, at least for non-commercial applications, but many are actually free for use for commercial applications as well. Then it is possible to merge checkpoints, and while training and fine-tuning models, checkpoints, LoRa's, and so on, it's more like a mutation which adds some novel information. Merging checkpoints is more like a crossover between genomes or something like this. And actually, the merge of checkpoints may produce very interesting results, which are not achievable by the merged checkpoints separately. For example, here I show two checkpoints randomly selected. One of them produces very fine details and artistic results but not in a consistent way. Another checkpoint has its own style, which is interesting but can be not universal. And what is interesting, the merge produces quite stable results, which are both visually more pleasant and more diverse than in both checkpoints independently. And if we continue this process and try to merge in a controllable way much more different checkpoints, then the result can be improved further. In fact, the authors of fine-tuned checkpoints, they not only fine-tune base models using some data sets, but they also perform this sort of evolution. They breed best checkpoints from different branches, and they can also merge LoRa's into their checkpoints as well. For example, if there is a LoRa which is trained to produce a correct number of fingers, then why not to try merging it to your checkpoint? And this process is going naturally in vivo. There are hundreds of creators who try to either fine-tune their checkpoints, to merge them with LoRa's, with other checkpoints, but we can reproduce this process in vitro in speeded up way and actually get nice results, which are shown on the slide to the right. So I just tried to make this sort of controlled evolution selection between different checkpoints, just rejecting the results with artifacts and other defects, and it really works. So why merging of checkpoints is important? Because it's like in normal evolution, biological evolution, because when a mutation happens, this novel information resides in a particular individual, but in order for this information to propagate to the whole society, we need some mechanism to transfer this information. And typically fine-tuning of checkpoints is done in a limited way, because it is done not by enthusiasts, not by large corporations or whatever, and they're typically trying to achieve some particular results. So when we consider this in general, we see that it's really a sort of evolution which is happening by hands of humans. We can consider the creators of these checkpoints as owners of some pedigree cats and dogs, or agriculturists who are cultivating their plants or whatever. So it's a real process which has a wide scale, which is happening in our society. And there are also actually indirect interactions with proprietary models as well, because we can fine-tune open source models on images produced by different means, including both photographers, artists, and other models as well. For example, we can ask a proprietary model DALI to generate images, say, constructed out of bitcoins, and this is a good model. It can do this out of the box without some additional tools and so on, but in a limited way, because in some cases it consistently fails doing so. But if we just collect a few dozens of such examples, we can train LoRa, which will be usable with different checkpoints, open source checkpoints, and you can either merge this LoRa to your checkpoint or just combine them in runtime and produce the results which are not achievable by proprietary models. So this shows the power of community-driven evolution, because you can get not just one or a few very good but still limited models, but you get the whole population of combinable models and other components which allows you to achieve various results. For example, if you want to have an illustration of bull run of bitcoins, then you can generate it, or if you want to recall the case of the first pizza bought with bitcoins, then it's up to you, and so on. It's not only about using proprietary models for training very particular LoRa's. There are also LoRa's which try to mimic, say, Midjourney or something else by tweaking the details of the image. So it's not about texture or even style. It's more about trying to teach a LoRa to insert fine details. Whether it is good enough as a Midjourney replacement, or even whether it is better than the original checkpoints to which this LoRa can be added, it's another question, but the results are indeed different, and we see that information flow can be indirect, so we may obtain some additional information from even closed-sourced models. Well, at least it is happening in practice. So we see that there is indeed some evolution happening with mutations and crossovers. And actually, I mentioned just a piece of it, because the community contributes with new pipelines and workflows, new components and their combinations. There are different components, because image generation is not limited only to text to image. There is image to image, in painting, out painting, different control nets, and community trains new types of control nets to produce various results. So it contains some compositionality and combinatorics, which is also exploited in the course of this evolution. But of course, it still doesn't go beyond the base architecture. And of course, the stable diffusion architecture itself evolves, and in this case, its evolution requires some deeper research and higher efforts, much more computational power, and so on. So it's not like the community which can fine-tune the existing models or train LoRa's is directly participating in it, but well, it's still a community. It's not just enthusiasts, but maybe some companies and so on, but they are participating with open source and their base models. And of course, when we consider how stable diffusion evolved, so it was first stable diffusion with 512 pixel resolutions, and it moved to the next phase with larger resolution, and but still, when we compare the base checkpoints with evolved checkpoints, we can see a considerable difference. So the community contribution to show capabilities of the base models is very large, because the community puts these models to perfection. And if, of course, resolution of base models increases, and after stable diffusion 1.5, SDXL appeared, which resolution is greater. Of course, maybe not of course, but that's what exactly I want to emphasize. At first, what could be produced with the evolved stable diffusion of the previous generation was not worse, but in some sense better than what could be achieved with the base model of the next generation. And the same is true for SDXL as well, because if we take the initial models open sourced by companies or groups of people who was doing this on a professional level, and compare them with what has been evolved within the community, then of course the evolved result is it shows what can really be done with these base models finally. And yeah, but of course, if community just resided with the initial models, they couldn't be able to achieve the results with the models of the next generations. This evolution continues, and quite recent there was a release of the base models for Stable Diffusion 3, and then Flux, which support very good resolution and details. Of course, if we compare the base model of next generations, if we are not talking about very technical things like resolution, then they still underperform, but their potential is of course great. Stable diffusion 3 allows not only generating larger images, but it also is more compositional in terms of image scenes. So you can generate more details which interact with each other on the image. It can be generation of texts or some scenarios which are still not very great, but much better than was before. Of course, there are more complex means of achieving these results. Like in painting, there was a differentiable diffusion, which allows using different prompts for different parts of images, but they are much more complex in use. And right now, these novel models and especially multimodal models, they become much better at compositional generation of images. But still evolved models of previous generation with all the toolkit available for them is still better, or at least not worse than models of the next generation. I'm not trying to say that, for example, we should use SDXL instead of Flux, but what I mean is that without open sourcing these models, they will not be perfected. They will not achieve their full power, their full capabilities. And for example, for Flux right now, there is also a process of training LoRa's and so on, and it will become very, very great in months. Okay, so we see that in the case of image generation, community efforts, community contribution to the development of these models, checkpoints, and the whole tool set is very, very large. And it's indeed incredible how many checkpoints and other components is being developed, and how this process is going on with all these mergers and so on. But what's about large language models? So large language models is they are quite similar to image generation models, because image generation models also use transformers and linguistic component as well. But there are still some differences. Interestingly, in the domain of large language models, there is quite a lot of LLM architectures, both proprietary and open source, although there may be not too many popular open source models like Llama, Mistral, GPT-NeoX, StableLM, and a few others. And these models are more hardware demanding for fine-tuning than stable diffusion. but still they're being frequently fine-tuned, but typically for some downstream tests, for some product or application. So there is no such community-driven evolution in terms of let's just create general purpose models which produce some pleasant or interesting results. Maybe because there are the domain of applications for large language models is too wide. And the same is true for LoRa's. So LoRa's are also frequently trained for LLMs. There are even some available tools for training LoRa's. There are some collections of LoRa's for specific architectures. Such LoRa's can add some specific capabilities, for example, to follow instructions in specific natural languages, to write code in specific programming languages, or maybe something else. But such examples of LoRa's which make sense to share with community, there are not so many such examples, because mostly LoRa's are indeed also trained for downstream tasks like fine-tuning the checkpoints themselves. Also, checkpoints of LLMs can be merged, and there are even some tools for elaborated merges of checkpoints, actually much more elaborated than in the case of stable diffusion. But the purpose and effect of such merges is not that obvious as in the case of image generation. There are some merges of checkpoints which attempt to improve an overall performance of the result on multiple benchmarks, but this goal is not driving checkpoint evolution enough. So there is no large pool of available checkpoints for experimenting with, for breeding them for whatever reason, and so on. So everything seems in place. One can fine-tune an LLM, one can train a LoRa, one can merge two checkpoints, or one can merge a LoRa into checkpoint, but we don't observe community-driven evolution of checkpoints which would considerably outperform the base checkpoints as in the case of image generation. There is such a process, but it's much less prominent. There are possibly objective reasons behind this situation, the main of which are higher training costs and too broad range of applications. One could imagine community-driven evolution of LLM checkpoints in some restricted domains, say in generating sci-fi or other stories. But there is no such request for it from human reasons, and not enough capabilities possessed by LLMs actually for doing this. But maybe we are just missing some infrastructure which would enable such community-driven evolution. And I personally believe that this hypothesis is really true. This process is already taking place, as I said, and it could be amplified with proper infrastructure. So maybe we need just to create some framework, some ecosystem for this process to really start burning. So it could, this ecosystem could be populated with more checkpoints, and more people would start fine-tuning them, breeding them, and so on, because it could be really fun. I see that there are some people who are interested in this sort of stuff. There are blog posts on everything I mentioned, but it seems that there is just missing some center of crystallization for this process to really scale up. Okay, so in the conclusion, let's a little bit speculate on what can be further, what can happen further with this sort of evolution of AI agents. So let's imagine a platform populated with, say, conversational agents with personalities and long-term memory. Apparently, we will want to control conversation styles, reasoning capabilities, knowledge, etc. This capabilities, these elements should reside in separate architectural components, which should be composable. So apparently, if we want to separately plug in a conversational style, it should be a separate component. If we want to separate personal memories from common sense knowledge, they should be informationally separated. They should not be intermixed in weights of a huge transformer. And LoRa's will not suffice for this. It could be more naturally done within neural symbolic architectures, but they are too diverse at the moment, and considerable efforts are required to make them compatible or interoperable. We personally hope that OpenCog Hyperon is a step towards this direction, since different cognitive architectures and their components, such as PLN, NARS, IRIS, can be implemented on the same basis. But what is also crucial is ecosystems. There should be a possibility to connect instances of different components together. The SingularityNET platform with its knowledge layer might be able to become a basis for this. However, it's still not enough, because what should be done, we should not only be able to connect different instances of components to work together, but we should somehow motivate and technically enable training and breeding of these components. We should also somehow drive the selection process for the community to decide that this checkpoint or instance of a knowledge base or whatever else is usable, preferable, at least for some technical, some downstream tasks, or maybe not pragmatic but artistic applications, and so on. So what is my message here is that observing how things are going on in the image generation domain, I feel that it is really important to facilitate the same process in more AGI-ish domains, starting with large language models and then proceeding to AGI-ish agents, cognitive architectures, or at least neural symbolic architectures combining knowledge graphs with large language models. We need to create a composable architecture which will be able to be assembled from such pieces which can be dealt independently in this sense, but which will work in collaboration, in cognitive synergy, for example, if you wish, to achieve some final results. And it is quite nice that in the case of image generation, many efforts in community are driven not by some monetization-oriented goals, but just by aesthetics, by artistic purposes, and so on. We can imagine the same, for example, in the case of music generation, but it would be also more narrow AI example. But I think that it is very important for AGI to be created in a decentralized way, and we see that it may not happen by itself. We need to put some effort to make it happen. It's not just enough to open source some code or models. We need to create some ecosystem for the community to start participating in it. Okay, I believe I am running out of time, so thank you for your attention.
I want to thank Alexei. He can't hear me, unfortunately, but awesome. Always fantastic to see the updates that are happening and the future directions that everything is moving in all together, all the time, all at once with OpenCog, Hyperon, and Meta. So thank you very much, Alexei. We very much appreciate it. Next, I'd like to welcome to the stage Patrick Hammer. Yes, perfect. Patrick, I apologize. I don't have your bio on me, total oversight, but please introduce yourself a little. Still, I believe, at the KTH in Stockholm, postgraduate doc, working on NACE, NARS, and a bunch of amazing work that you're not supposed to have favorite presentations, but I always enjoy Patrick, so I hope everyone does as well.
Thank you, Helle. Now you can hear me. Thank you, Helle, for introducing me. So I'm a postdoc, and can you hear me? Yeah. Oh yes. Okay. So I'm a postdoctoral researcher at KTH currently, working on robotics and trying to bring a non-axiomatic reasoning system on the robots to make essentially to build autonomous robots. And today I will talk to you about experiential learning. And if you look at the current state, also in this community, it is widely, many believe that if you have the right set of tasks and the AI system can perform well in these tasks, then maybe we have AGI. For instance, let's consider the set of tasks being good in the ARC challenge, abstraction and reasoning challenge, playing Go at the superhuman level, passing the Turing test, and driving as good or better than humans. Many would say if you can build a machine which can do all this, it must be intelligent as a human, right? I would say that's not necessarily the case. Optimization algorithm with enough data and training with the model structure is right will likely find a better solution to these problems than humans are. Because we are not evolved for this particularly, but we have very high level information processing capacities, which also allows us to learn these tasks relatively well. So what I want to emphasize in experiential learning, in addition, is also the ability to learn in a very data efficient way. And I would say that this is a central capability and is a very central part of intelligence that we can learn in a very data efficient way. And if we look in nature, it's, after all, intelligence is a natural phenomenon. And why has it evolved? It gives species survival advantage. They face dangerous situations. Ideally, they would learn from these dangers. They would learn from mistakes. They would learn from dangerous situations. So the next time they encounter these situations, they will do better and will not die. So it's very important. Data efficiency is a very important component, and I would say it's the meat of intelligence. Of course, it's also important that for particular skills and knowledge, the agent will be able to acquire it. That's one thing, but first, it needs to be fast. So, if we want to have experiential learning system, they need to learn fast, they need to acquire and update knowledge while they are operating. In this case, there's also a paradigm shift. It means we cannot separate training from deployment. The system takes in information and does so lifelong. Has some sensors, usually attached to some robot body, and these sensors just get in signals, and the signals get perceived by this cognitive system somehow and get processed. And hopefully, the agent will learn from this data stream that never ends until the system gets distracted. So this also has other consequences. It means there is no clearly prepared training samples available. It's just messy data stream as the sensors reported to the system. And this means that these inputs are also correlated over each other in time. They are not independent from each other. So there's a few of the challenges, and I think that experiential learning, it's like it allows an agent to adapt to new situations and to changes in the environment, particularly these which are relevant to its own existence. But what is the role of reasoning? Many of you who know that I have been working on non-axiomatic reasoning system for now 10 years. And for me, there was always also the question, what can reasoning add to the picture? Why do we want it? What does it bring to the table? And there's always, if we look in the history of AI, this attempt or this approach that logical reasoning has to be done with some kind of logic, right? I would say that's not necessarily the case. I take a broader definition of reasoning. Reasoning is a very high-level information processing ability which allows you in as data efficiently as possible to derive relevant information from other information you already have. That's a very broad view on reasoning. And just to give you an example, if you enter a room, and before you enter the room, somebody tells you there's a dog inside, and you enter the room, and all you see in the middle is a sofa, what will you infer? You will likely infer either the person has lied to you, or the dog might be behind the sofa. And that's a conclusion you want intelligent systems to draw, no matter how. Will it be based on logic? Will it be another mechanism which can do this kind of information processing? But this kind of reasoning has to be there. So if we take this stance, it also means that it's essentially information processing capacity. And this information processing capacity is relatively domain independent. What works for the dog and the room works for other scenarios in your life. You can draw similar conclusion, you can apply similar laws of thought, if you will. And somehow you can do this. Somehow you can draw similar conclusions in other contexts and other domains. So reasoning is really this high-level information processing capacity which is not tied to any particular domain. So what does it add to experiential learning? Essentially, if it's that effective, it essentially means it can make experiential learners better. It can make them more effective by drawing relevant, by making them able to draw conclusions which are relevant to them. Now we will dive into our particular vision. My own research, and also with my collaborators, especially in Stockholm, Robert Johansson, Tony Lofthouse, Peter Isaev, we always try to find a way to make our systems smarter. And in what way? How do we measure this? We take an approach where we essentially take cognitive abilities and essentially which are found, for instance, in nature. For instance, if you look at this ladder of intelligence here, you would say, yes, coffee machines, they're not very smart. They cannot adapt. They have a fixed program. You press the button and the fixed procedure gets executed. And then self-driving cars, are they, from that standpoint, much smarter than coffee machines? In the moment the self-driving car leaves the factory, it's usually expected to drive perfectly, right? There's no learning from there on. It leaves the factory and it's a fixed automata. Even though a very complex one, it can detect objects that matter for it, like cars, pedestrians, even though it might be blind to other object categories which don't appear in traffic. But it's essentially a fixed program, has been pre-trained, pre-programmed, leaves the factory and is expected to drive. Higher on this ladder, you see insects. So I will show you examples where insects can acquire complex behaviors. And they can acquire complex behaviors which they have not been directly evolved for. And of course, with mammals and birds, there is extensive comparative psychology studying the cognitive mechanisms and the cognitive abilities of this species. For humans, we are very special. We can invent things. We can communicate via language in a very flexible and dynamic way. And that's very unique. But my own research is not quite there. So I'm still studying the principles which are a bit low in this ladder of intelligence. If you here look at this picture, you see these are all situations where animals have been put into situations that are different than they have been evolved for. They have been facing tasks here, tasks they need to do. For instance, here with the bumblebee, it needs to learn to use the boar and to roar it over there to get honey. And it can learn this, and it can learn this very effectively, and it can even learn it from observation by observing own bumblebees of its own species. For corvids, there are many intelligence tests in very different categories showing what they can do, the kind of causal learning, causal planning they can perform. And so there's extensive work on evaluating the cognitive capabilities of this animal species. And for me as AI researcher, I don't start at the human level. I first want to understand the most basic learning abilities we find in nature and that are so much more data efficient than anything that exists so far. But if we look at all this, what I explained so far, there's also kind of a working assumption, a working definition, which I'm following, and this is actually a very explicit working definition. It's like my own, the view of our team of how we see intelligence. And we see it that intelligence is the ability to adapt under insufficient knowledge and resource. Insufficient knowledge, that makes sense. An agent will often not know everything that is relevant to it. There might be some knowledge, some information it has yet to acquire, some things it has yet to learn in order to perform well. That's one thing. But what's the resource thing? Why insufficient resource? And that's already a bit more tricky because it has to do with the computational limits of your own computational substrate, your own brain, your own how many inferences, how many pieces of information you can combine in any moment. You're driving on the motorway and then suddenly your wife tells you, you cannot go straight because there's a traffic jam, you should take the next exit. Now you have maybe, if the exit is close, maybe you have 5 seconds or 10 seconds to decide, dependent on how close you are to the exit. Will you consider all pieces of information that are relevant to make the decision? Hopefully, but you might miss some. Maybe 10 minutes earlier you thought, I'm running low on fuel. And maybe there's a gas station straight ahead, so you should still go straight. Maybe you forget it in that moment and take the exit, and then not make it to the next gas station, for instance, just an example. There are many situations where you are faced to make decisions under time pressure, where you cannot consider all information that is relevant to you to make the decision. And this is something animals face all the time. They have to make very quick decisions, especially in survival critical situations. So, given this philosophical aspect, I will now go into the journey in which we have been exploring this within artificial intelligence. So we have been looking particularly at a reasoning system called non-axiomatic reasoning system, which operates under working assumptions, which takes this definition of intelligence very seriously and is built according to all the consequences that that definition entails. For instance, we want this system to operate in real time. But if information just continues to grow in the memory of the system, then its memory will get larger and larger and larger. But there's only so much information that can be combined, so much inference that the system can draw in a certain time window. So if that's the case, then it probably means, okay, there are two issues. Maybe the memory size cannot be infinite, so it has to be constrained. But if that's the case, we need to constrain it somehow. How to constrain it? That's an engineering problem. For instance, we could say pieces of information which have been used often, which have been contributing directly to the fulfillment of goals. Maybe these pieces of information are more important and should stay in memory, while other pieces of information which have not been useful at all over the history can be replaced by new information. And if you take such principles, you can essentially build a system which operates with a fixed memory capacity and keeps operating with the same speed, no matter with how much information you bombard it. You can give it a stream of inputs coming from its sensors, and it can keep operating, building new knowledge, updating its hypothesis, and never exploding in the amount of hypothesis it builds, because it only has a fixed memory. So that's the story. Of course, from an engineering standpoint, there are hard questions here. According to which criteria should the importance of knowledge, long-term importance, be evaluated? We have tried many things over the years, and certain things have turned out to be simple and effective, such as use count. How often has pieces of knowledge been used previously, for instance? That might not be the final story, but it's at least there are practical solutions one can consider. There are also other practical considerations built into this reasoning system, like in terms of representation. What does the knowledge look like this reasoning system is operating with? That we can see on this slide. This reasoning system takes two central copulas, as we call it, to build concepts in order to describe relationships between experienced patterns. One is the inheritance relation. For instance here, cat is an animal, and that's like a special case. The system will see many variations of objects in its lifetime, and at some point you would expect it to have an understanding of categorical information. Like this chair looks different, but it's still a chair, and I can still apply the knowledge which I learned about chairs on this particular new chair. So that's one central relation in the system, to take one particular thing as a special case of another thing it has already seen previously. Another central relation is temporal implication, or implication in general. What if you have, for instance, the case someone presses the light switch and then the light turns on? Wouldn't it be good if the system can model this? If the system can observe, switch gets pressed, light is on, and then form a temporal relationship between these events. And that's exactly why these two copulas are so central in NAS, because they play central cognitive roles. One is to categorize events, and the other one is to find relationships, like temporal relationships between events, so that it can then figure out how to achieve goals, for instance. And now the question is how to evaluate this hypothesis. Because in this system, it's not like a traditional logical system where these are either true or false. Here it's empirical. It has an empirical measure of evidential support for each of its hypotheses. So when the switch goes on, then it's the question, will the light also go on, or will the light not go on? If the light goes on, the hypothesis will get positive evidence. If it does not go on, it will get negative evidence. And that's how it essentially keeps track of the prediction success of the hypothesis within the memory of the system. So there are certain desirable capabilities of the system on a high level, which are on a high level also studied in psychology, like building concepts, dealing with semantic information, with spatial and temporal relations, and so on. Another thing is how the system operates. You cannot combine all information with all information. There's not enough time. So it has an attentional focus. What pieces of information to consider in a given moment. If you can only do a certain amount of inference steps in a certain time window, then hopefully it should be inference steps that matter to the system, right? So also, that's the next engineering challenge as well, to find an inference control model with attentional focus, which has the right judgment about which pieces of information are relevant in any particular moment in time. So we have touched on attentional focus. We also have touched on, how can I get back? Here. So we also have touched on the long-term memory of the system, like usefulness in the long term. We have touched on attentional focus, what's currently useful to the system. There are also other aspects, particularly the uncertainty handling, which comes from the evidence accumulation I described. So there are many desirable properties. Yet I wouldn't say at current stage that there's a reason why not everyone would say that NAS is an AGI system at current stage. Even though it has this many aspects and which are very easy to study with NAS, it's not yet there that everyone would say it's an AGI system. So there's still a lot of work to do, and it might not even be only a NAS in the end. But it's at least a model which allows you to study these different aspects of a cognitive system. So we tried many things over the years, and many of our efforts have also been driven by various applications. For instance, here together with Cisco, particularly in collaboration with Hugo Ladaby, we have made some very early neurosymbolic approach where we combined deep learning with NAS in order to do some real-world applications. Like here, detecting anomalies in real-world camera data. In this particular case, there's a camera mounted to a street, and it's watching the street over time. And the system is expected to learn various things here. For instance, how different changes in the scene affect each other, like how do pedestrians move, how do cars move, and where do they move, which places are typically occupied by pedestrians, which places are usually occupied by cars, and then they can already see and judge whether things are more unusual, like when a pedestrian walks over a street at a place where there is no crosswalk, like a form of jaywalking. Other cases where maybe a car comes very close to a pedestrian, and so on. So we tried to use this experiential learning component to make the system acquire a notion of what's usual or unusual in this setting, and then guide it with a few pieces of background knowledge, make it report relevant anomalies. Here you see a quick demo of this. You see it was earlier attempts where we combined a YOLO model with NAS, convolutional neural network, to detect objects. And so you have different kinds of objects like cars, and you have pedestrians walking around. And you already see some prediction errors. It's hard to see, but it quickly builds expectations about where cars will move, dependent on the previous patterns of the movements of the cars, and also will be able to pick up unusual cases, like here where a car gets close to the pedestrian, or when the pedestrian walks over the street. So it's able to report this kind of anomalies. But we found a lot of issues with the open NAS as it has, or the implementation of NAS back then, also through these applications. We found there are various limitations. And many of them have to do with the inference control. If you can only do a certain amount of inference steps per time window, then it should be the right inferences, relevant inferences. And this implementation struggled with this. And there are reasons for that. When we did this project, it was the temporal and procedural reasoning was relatively new in the system. And the control model has been built at a time where time was not yet considered in the control model. So it was very hard to make it, to tune it, to make it work for that particular application, even though we managed to do so without specializing the system. So it served as a very good platform initially to study attention allocation, temporality of events, forming temporal hypotheses, making predictions about the scene, and so on. It was a really good playground implementation. But of course, we wanted to go beyond that. So particularly during my PhD, I asked myself the question, can we build even more effective NAS implementations? And there was a collaborator, Tony Lofthouse in the UK, who came up with his own control model for NAS, which is largely inspired by spiking neural networks. And he used this semantic spikes, as he calls it, as a own model where essentially he simplified the prioritization of derived events within the reasoning system. But there's a huge value in the simplification because he captured some very important factors and principles there. Because in the previous implementation, we always had the issue, if we bombarded the system with information, the system became overwhelmed, and most reasoning was not relevant to the current situation anymore. And with his simplification and his spike-based control model, we were able to make certain principles hold. Like that when information is derived by the system, that this information will not overtake the reasoning steps in this, like decide where the system will reason from there on, but so that it will still be more anchored to the input that recently have been observed by the system. So we also constrained the attention allocation because even at this moment, we don't know what's the ideal form of attention allocation. We don't know, but we know at least certain principles. Like it's a very, very simple design constraint, for instance, to make sure that derived pieces of information are not considered more important than the information they have been derived from. There might be cases where you want exceptions to this, but as long as we don't know the perfect answer, it has been a very practical design decision in this system to enforce this. And so that's what we did, and we came up with this particular implementation, openness for applications, which enforces certain constraints in the control mechanism and also operates using the spiking approach of Tony Lofthouse, and built the first NAS version which you can simply bombard with information, and it will usually be able to keep the relevant information and the information which matters for the achievement of its goals and the answering of relevant questions. So it's at least, even though it forgets a lot, it usually does not forget the information that is relevant. So that was, from this perspective, quite a breakthrough. But of course, it was not perfect. And there also, of course, there have been the obvious issues. If you have such a reasoning system, then how to deal with perception? And here we kept iterating on this idea that, okay, we cannot build a better convolutional neural network. Convolutional neural networks are very good for what they are doing, so why not use them? So we continued on the road of integrating them with the system and to make use of the capabilities for visual object detection. So in this implementation, we made it very easy to interface with various deep learning models for visual signal processing and also other sensory processing. And the overall architecture is relatively simple, I would say. We tried to keep it as simple as possible, but of course some complexity had to be there, as we found. For instance, in this system, you can have different sensors which stream in events into the system. And all these events end up in the same priority queue to compete for attention, to compete for the selection in the next inference step. So for every inference step, the system then decides what to pick from this attention buffer, namely the item of the highest priority value. Picks it, selects beliefs which have common terms with the selected event or are close in time, and then does inference with them. Either declarative inference, if there's a declarative relation between them, like inheritance, or temporal inference, if they're close with each other in time, like if you have a temporal relation, or if you selected a Goer from the priority queue, then you use it for subgoring, essentially. So it has like 3 different inference paths which serve 3 different, clearly defined functional purposes. The first one, declarative inference. If Tim is a cat and the cat is an animal, then Tim is an animal, for instance, as a simple case of declarative inference. Temporal inference, if A happens and then B happens, to strengthen, to build an inductive relationship from A to B, like a temporal implication. And then subgoring, if you know A leads to B, and you select B, the Goer B from the priority queue to select A, to derive A as a subgoer. So you have these 3 different components. Build and update temporal implications, do declarative inference, if applicable, or do subgoring, if you selected a Goer event. So we found that this distinction in 3 different inference paths has been a very good design decision, which made the engineering significantly easier to come up with an effective system. And we reached several milestones with this system. We reached reliable procedural learning. So it could learn to play like Pong or Space Invaders or Breakout if you encode the information somehow where the bore is, where the bed is. It's not as granular as pixel input, but as long as you somehow provide this information, it would usually figure it out how to play the game using this procedural implication statements. Some context, some action leading to some other event. Next milestone we reached was compound conditioning. What if whether the outcome will occur depends on multiple conditions, on multiple other events? So you have event A, but event C does not follow. Event B later, event C does not follow. But if A happens and B happens, then C will follow. Can the system learn that? Yes, we made it be able to learn that. And later we extended that further by combining this with declarative information. So for instance, you could stream in information about different shapes. Here, for instance, in this example, you could give it different shapes and encode various attributes about them. You could say on the left side, or here with a value encoding, on the left side, there's something which has the shape, which has a circular shape, and a blue color, and is a bit bright, has a certain brightness value. And then you could say there in the middle is another, is something of shape triangle, blue color, and also a bit brighter. And then to the right, a bit darker, something of shape circle, and color green. So you can have as many dimensions or attributes per object as you want, and you can just stream it into the system. And then, for instance, you can define an arbitrary reward criterion. You can say the system should always select, let's say it can select either the left or the right shape. And it has to figure out according to what criteria. For instance, select always the thing which has the same color as the thing in the middle. Or select the thing that is brighter than the thing in the middle. Or always select the triangle if there's a triangle. Or always select the left thing if there is something green on the screen. There can be arbitrary criteria, and the system would find it. within usually 100 steps. We have set up a psychological experiment where human is competing against NAS in this task. NAS was actually winning in most cases. So we have a very effective procedural learner which can also learn criteria according to which, for instance, shapes are selected. I would not say that this means that the system is better than humans, because humans can also think about other criteria, like how many triangles are there in the scene, and so on. There are still inductive limitations in our implementation, which makes the hypothesis space a bit more constrained. And if you have a more constrained hypothesis space, then of course it's easier to beat out the hypotheses that matter. So I would not say it's superhuman in induction. No system is at this stage, I would argue. But it's very good that we got into human comparable data efficiency at such a complex learning task where no reinforcement learning approach would succeed within such amount of time steps, because there are so many different, there are like 4 different shape types, there are 5 different colors, and there are 10 different shades. That's a big state space, not something where you could do with 100 time steps. So that's one of the milestones we reached. And it's also psychologically interesting. There is this concept of identity matching, which we tried to make work over many years, together with Robert Johansson and Tony Lofthouse. Particularly, for instance, if you want the system to learn to pick, for instance, always pick the thing which has the same color as the thing in the middle, for instance, then it needs to be able to represent this somehow in the hypothesis. And in NAS, for instance, it can introduce a variable. If something has red color and the same thing has a round shape, then this action leads to reward, for instance. Or if the thing on the left has the same color as the thing to the right, same variable essentially, constrains it to the same value, so it can essentially learn that the color has to match, for instance, no matter of which color. So later we collaborated with Chat Progression Laboratory for first responder assistance. Like imagine you have a first responder who is driving a police car, and you want a system which helps to detect dangerous situations or which gives mission assistance to the driver. And here we took a similar approach. It's like a next iteration of our neurosymbolic integration, where we added object detection and some basic tracking ability and fed the information, streamed the information into the reasoning system. And then the reasoning system can reason on the movement of objects in the scene and how they move relative to each other and how fast they move and in which direction they move and what visual attributes they have, which are additionally extracted, and so on. And then you can do things like here. Here we have a trial in a simulation where essentially the system warns the driver before a crash occurred about the danger from the other car. So you can essentially apply reasoning to dynamic scenes if you have this kind of real-time reasoning. And what we found particularly useful is that a lot of information, the system, which we would usually program into the system could actually acquire. For instance, that the cars tend to stop when there is red traffic light. We did not need to program this into the system. It simply noticed this as a temporal pattern. If there is a red traffic light, that the velocities will essentially decrease of the perceived cars in front. So it automatically learned that essentially there's a dependency between the red traffic light and the movement of the vehicles. Later we thought, okay, that's nice. We can build anomaly detection systems. We can build systems which assist like first responders. But can we also build autonomous robots? If we have an experiential learning system, shouldn't that help us to build more autonomous systems, like robots which drive around in the environment? And our theory has always been that we don't see autonomous robots everywhere because there are so many corner cases where they fail. They rely on the training and the pre-programming, and when they face situations they have not been trained for or not programmed for, then they are screwed. They have no mechanism which would allow them to learn a new behavior while they operate. They lack this mechanism. They lack experiential learning fundamentally, completely. And so we thought, okay, if we can add this, maybe autonomous robots become a possibility. So we integrated NAS into robot operating system, connecting it to various standard components like object detection, iterating further on our perceptual input pipeline, but also taking additional modalities into account, like distance. Nowadays you can buy cameras which can give you distance information for each pixel, either based on infrared or stereo cameras. So you can have essentially a third dimension, which also tells you about how far things are away from the robot. So we take this into account instead of just the 2D bounding box locations. Additionally, we have like a LiDAR sensor. It's the circular thing, cylindric thing on the top of the robot, which can measure distance to the obstacles in the environment using laser, essentially. And based on this, there are algorithms called simultaneous localization and mapping, which can build a map of the environment. And then these algorithms output a location within that map, which tells the reasoning system, in our case, where it is currently located within the environment. Then it can already do interesting things, because if it can estimate the location where it is and can detect certain objects, then it can already correlate. Okay, if I'm at that location and I see a fridge there, and next time if it's somewhere else and I ask it, I wanted to see the fridge, then it knows, okay, it should go to that location, simply by inductive reasoning, by relating both events, the location estimate and the detected object, which is detected via the object detection model. So that's capabilities which we have been making use of. We had a recent paper at ICRA, one of the top robotics conferences, where we have essentially shown a use case with the system. Essentially, the system drives around in the environment, and it invokes decisions. When it sees objects it can pick up, there's also learning involved here. It needs to learn which objects it can actually pick up, and when to invoke the actuator procedure, and so on. And essentially, the system performs garbage collection or trash collection in the environment in this particular task. Navigates the environment doing so, searching for trash objects. Later, the last thing, which is a relatively new research direction for us, there are always the question, okay, this is NAS, we built this effective implementation, but it's not an AGI yet. What's missing? There are likely many things which are missing, but one thing which we found particularly interesting was curiosity. If we want a system which can effectively find causal relations in the environment, then it cannot just randomly explore the environment like a reinforcement learner. It needs, but to be fair, there is also work on intrinsic rewards in reinforcement learning community. Quite comprehensive, beautiful to see that this is increasingly getting more relevant. But in all this work, it's usually built on simple proxies, like count. How often have certain states been visited? If the states have not been visited that often, then maybe they should be revisited so that more can be learned about them. It's a valid principle, but there's something missing. And I think what's missing is causality. If we want this to be really effective, it should be driven by the predictions of the agent. It should be driven by whether the agent knows something about the situation it wants to bring about. It needs a way to know what it knows in some sense. It needs to be able to reach or to plan for situations where it knows the least about, so that it can challenge its own knowledge. And in the end of last year, in December, I found Koch's iris system. And this has a very effective curiosity model. And I I was really impressed, and so I started looking into Goertzel again, because his system, his Iris system, operates in grid worlds, and it has this curiosity model where the agent explicitly plans for future situations where its knowledge does not match to the situation. So it explicitly tries to bring about, with high certainty, situations where it's most uncertain about. It's a very powerful principle, better than anything I have seen in the literature. And it also works extremely efficient. So I have revisited grid worlds. I'm running out of time, but I will show you this quickly. Grid worlds, they come with many challenges. They look simple, but they have actually a lot of challenges. Partial observability, the agent cannot see the entire thing. Different than in Go. In Go, you can see the entire board. Next thing, also complex state space. Many grid cells, many possible values, huge possible state space. Then things can change on the grid externally to own action. Also different than in Go. There's not just this player makes a move, this player makes a move. There can be also changes which are not caused by any agent or by other dynamics which the agent does not know about. And there can be effects which are non-deterministic. Things which just happen, but not always happen, or not always reliably happen, for a reason the agent will never know exactly why, but it has to deal with it. So, in this grid world, there are also sequential dependencies. It could be that the agent needs to pick up a key in order to make it through a door. And these sequential dependencies are really a problem for reinforcement learning. Reinforcement learning is by far not as scalable as it sounds. It's scalable from the perceptual input set. You can feed it with pixel input, it will figure it out, that's true. But the more sequential dependencies you introduce, you need exponentially more training data. And that's what we also found out recently. If you have it's one thing to bring the key in order to open the door, but what if you need to bring the key, open the door, and then go to another room, and maybe there is a switch, and maybe you need to press it in order to make it to another door. Then planning is way more effective than anything reinforcement learning has to offer. So, for me, the question is, okay, if planning can deal with that, there needs to be a system which can deal or which can learn causal knowledge so that the planning becomes possible. And that's also what Iris, actually, what Kristoff Koch system did really well. So I looked at these mechanisms. And there are certain inductive biases which are very important there. On one hand, it's this causal representation. On the other hand, it's that the agent should be able to model observations which are outside of its observational window so that it can remember where things are in the environment, which also mattered for our robot application. But there is also strong attentional bias. Which hypothesis to build? And there is this key idea. If there are changes in the observation window, then maybe that's a good bias. Another thing, what if some values are different than the agent predicted? That's also a good bias. Not all hypotheses necessarily have to do with changes and prediction mismatches. But very often, this is a very useful attentional bias. And this agent even goes so far to only build hypotheses based on this, and gets very far with this, as we will see. So we came up with this non-axiomatic causal explorer, which builds on Iris and brings in ideas of non-axiomatic reasoning systems so that it can deal with partial observability, non-deterministic effects in the environment, and so on, essentially to extend the model to become a bit more generic in a sense, and largely motivated by the limitations of current reinforcement learners, which I already mentioned. So we built this agent. And the architecture is a bit like this. You have a 2D grid world with partial observability. The agent takes in the values from the observation windows, maintains the global map, updates the map at the locations where it currently can observe, and then looks at changes and prediction failures within this observation window and builds hypotheses accordingly. If there was a prediction failure, it means there was a hypothesis which did not predict correctly, so that hypothesis should receive negative evidence. If there are other things which happened as predicted, then the hypothesis should get positive evidence, using NAS principles in this case. And then, so this is already hypothesizing. And then the planner simply searching, using these dependencies to plan for states which are rewarding, which give the maximum cumulative, the expected reward essentially. And as a secondary objective, if it cannot find rewarding futures, then it will try to find a state where its knowledge does not match well, or is not applicable. That's a curiosity model. And I can briefly show that, then I'm wrapping up. Here, for instance, the agent learns to pick up keys in order to make it through doors, in order to collect a battery. And it's learning these dependencies in one episode. While it goes, here it makes a mistake, it tries to go through the door without a key. But we will see, it sees the next battery to collect, and it already knows it has to pick up the key in order to make it through, which it does. Or here, down here, you see, initially it does not yet know what to do, so it pushes things around, like pushing a bore to another bore, until it has this idea, what happens if we push this to this object, and then it gets reward, and then it keeps doing that, like learning to play soccer. Also, in a single episode. Here, it learns to search for salad in the environment while avoiding electric fences. In the very beginning, it gets shocked once out of curiosity. It wants to know what happens when it runs into the electric fence. It does not repeat the mistake. There's, of course, a mathematical model behind the curiosity there, because this notion of whether knowledge is applicable needs to be clearly defined. And it's relatively simple. If you have causal pieces of information, then essentially you want to measure how many of the conditions are actually applicable to the situation. And according to this, you have essentially a measure whether the hypothesis matches or not, and how well it matches, depending on how many of the conditions match. And based on this, you can decide for all the cells how well the rules predicted the value, how well they matched essentially for each cell, and then you can judge this for the entire situation. So that the planner can then search for states where the knowledge matches the least. We don't have the time to go through an example here, but all this follows these principles, and we have really shown that the data efficiency of this approach in various environments is orders of magnitude better than any reinforcement learner, any deep reinforcement learner. So we compared with various deep reinforcement learning techniques, which at least need 100,000, usually millions of training iterations, time steps, to learn any effective policies. Well, here it's usually in the orders of hundreds. Future steps. So for me, of course, there's the question, okay, we have now the simplified learner for the grid worlds, and we have the more generic reasoning system, NAS, which also has its merits to deal with conceptual knowledge and so on, so how to combine it. And we have like this hybrid system, which Peter Isaev is particularly researching on how to combine these systems together. How can we have a system which can take high-level goals, like bring coffee and then turn it into low-level goals, like the coffee cup should be above the coffee machine, which the experiential learning system can then actually figure out how to do and do effectively. And of course, there's also another aspect, and this has always been central in NAS. If you have changes in the environment, there's always the question, is it because of own actions? Is it because of the actions of other agents? Is it because of environment dynamics? How do you know? You can only build different hypotheses and let the evidence accumulation fight it out. Dependent on which hypothesis has the most evidence, the right hypothesis will filter out. So in the future, we want to combine the best of these two prototypes, essentially the best of our see of our NAS implementation that has turned out to be effective, and also of this new curious grid world explorer to combine the best of both, to bring curiosity into NAS essentially, and to make it be able to handle such grid world environments, but also realistic environments like we saw on the robot use case. So for us, it's very important that this will work in real world conditions, which is we will not stay in grid worlds, even though we learned new things from the grid world. For us, it's important to make the system NAS, which works well on the actual robot, to make it, to extend it with some of the principles we found in the grid worlds. So that's our roadmap, and I hope I gave you a view on experiential learning, which is not too biased on my own work, but I guess it was relatively biased. But I hope you enjoyed it.
Thank you very much. I got to show the crows to Helen, the 7-year-old Peter is here with, and she very much enjoyed all of that. So thank you very much for making a presentation on AGI that's both exciting to AGI researchers and accessible for anybody that can see how these agents are maturing and growing and becoming more capable through very novel ways. So I appreciate it very much. We have time, I think, for a couple questions. Are there questions in the audience? Aha, right here, Barrick.
I was wondering if you could talk a bit about your work in combining NACE Can you talk a bit about combining your work NACE? It might be the camera. Let's do this. There, how's that? It's much better. Okay. Can you talk a little bit about combining NACE with the meta language of Hyperon?
Yes, that's a very good question. And we essentially already have a meta bridge which essentially combines NAS with this new grid world agent and use meta as a common representation language. And that's also how it essentially is envisioned, because if all of these learners have their own shortcomings, then if we want to combine multiple of them, it would be good if they can talk to each other. And meta can play this role of becoming the common representation language. And we even went as far as implementing NAS itself completely in meta. So we have also an implementation of NAS which is completely written in meta, and which essentially uses meta as the programming language, but also representation language, so that NAS and NACE can essentially, so that when, for instance, NAS derives a GOR, that NACE can receive the same GOR, so that they can talk to each other in a sense, even though the communication suffice one directional. So NAS takes in a high-level objective, like make coffee, then derives other GORs, and some of them can be perceived by the grid world agent, like that the cup should be above the coffee machine, which it then tries to realize. So we make use of this kind of synergistic effect where we combine, where we use meta as a common representation language, so to speak. And this is also in the entire Hyperon project very important, and that's also part on our roadmap to combine it with other cognitive mechanisms. There are so many AI algorithms which are developed by SingularityNET, which I think will be very valuable to combine with NAS, and come up with how to say it, like neurosymbolic versions and with more capable cognitive systems, which we want to be able to operate in real-world environments.
We've got a question here.
It's less a question because you've been very generous with your time, Patrick, and we spent a lot of time together this week. But I just wanted to express my sincere gratitude to you, to Peter, to Beric, for the work that you've been presenting this week, all through the week since Monday. I consider it extraordinarily exciting, very, very breakthrough technology, and it's the kind of technology that we can use to show the world that SingularityNET, decentralized AI, AGI is actually on the brink of really whooping us with every other kind of AI that's out there. So I just wanted to say really a big thanks to you, Peter and Beric.
Thank you very much. Thank you, very kind.
I look forward to working with you on this.
We'll close. Thank you very much.
Thank you.
Yes. Thank you very much, Patrick. Excellent presentation, excellent research. Looking forward to seeing more and more. And I'll invite to the stage Kristen and Ben, and we'll look at closing remarks and award presentations and close this amazing conference out, unfortunately, but in good time.
Yeah, thanks. Yeah, thank you. Is this on? Yeah. Thank you, Haley. So each year for some time at the AGI conference, we've given awards for submitted research papers that were exceptional in some way, and I think Chris is going to present these awards, then we'll have some very brief concluding remarks, and then we're free to go create AGI.
Yes, let me introduce to the stage Joscha Bach, who will announce the award.
Introduce someone else. He's running.
Yes, he has the secret book with all the info in it, which is highly secret and will be revealed now. Not even we know this.
It's a very secret moment.
It is our very great pleasure to announce this year's awards of the AGI conference. This year has seen a number of brilliant contributions. We had, next to a number of very inspiring keynotes by influential people in our field that inspired us and moved our thinking forward, also a number of contributions of ongoing work in research in AGI. Some of these contributions were of a very practical nature. They provided applications. Some of them gave us insight into incremental research in AGI architectures that have been with us for a long time. We also had papers that were providing significant contributions to the philosophy of AGI. And overall, I'm very grateful for the work that people have presented here. And in this year, we were able to bestow 4 prizes, unfortunately not more. There would have been some more that we would have liked to include. And on the other hand, we are also thankful that we are able to recognize people for their contributions here. And so the prizes that we are going to hand out this year are going to the Best AGI Paper Prize and the AGI Society Prize, the Best Paper Prize from Springer, and the Student Prize. And with that, I would like us to begin with the best AGI paper prize. Peter? Is Peter here? Please introduce the paper to us and why we chose it.
Okay.
You need to speak into this.
All right. Okay, so this year, the Goertzel prize of $1,250 for the best AGI paper comes to Arash and Chris Torreson.
Wait a minute. This is really.
For their paper, which is called Causal Generalization via Goal-Driven Analogy. It is a very well-written paper, actually, which touches on the very important, indeed important for AGI topics, such as the causality and generalization, and introduces an analogy-based learning mechanism, which is implemented within the IERA cognitive architecture, right? And this is enables for the autonomous knowledge update and knowledge generalization of an existing knowledge in an agent. Thank you.
Thank you very much. I just want to say the prize money will of course go to my student. That's a tradition. This has happened before. So, and I had nothing to do with the decision.
We were already worried about that, but now that we know, it's basically a big relief for us. The prize of the AGI Society will be introduced by Haley.
Thank you, Yo. So yeah, I'm excited to present the $1,000 AGI Society Prize to Leonard Eberding, Jeff Thompson, and Kristen Torrenson. Again, we were not paid off. Argument-driven, for the paper, Argument-Driven Planning and Autonomous Explanation Generation. So this paper provides an important process for enabling artificial intelligences to autonomously build and adjust complex plans by anticipating and overcoming obstacles in an explainable way, explainable both for the agent and externally. Through employing argumentation graphs for both solutions and contradictions, the paper proposes enhancements to the ability of AGI systems to dynamically create logically consistent plans in complex environments and real-time goal and plan adjustment. By expanding planning process for dynamic and unknown environments in real time, the direction enhances the generality of agents beyond narrow capabilities and limited environments, enhancing the goal of reaching AGI, not just an AI good at a target. And just as interesting, the explainability of the argumentation graphs addresses many of the current issues seen with LLM directions, not only augmenting a user and regulatory experience of the AI, but doing so in a way that fundamentally improves the intelligent capability of the system itself. Explainability has become a key topic in AI over the past years as problems of bias and black box AI systems have prevented adoption and degraded trust in AI systems. And building transparency through explainability in AGI systems will be critical to address those challenges to adoption and utility. So thank you. So Kristen and the ERA architecture have provided the context for this work as well. The team has submitted a number of excellent papers. We're happy to celebrate this one as well, and shows promising directions for future exploration in incorporating future reasoning.
Right.
Thank you.
The Springer Best Paper Prize will be introduced by Matt.
So the Springer Best Paper Prize, which also has an attached $1,000 award to it, goes to James Oswald, Thomas Ferguson, and Selmer Bringsfjord, titled A Universal Intelligence Measure for Arithmetical, Medical, Uncomputable Environments. And as James discussed, measuring artificial and general intelligence, which entails measuring general intelligence, which entails understanding intelligence, is a very difficult problem. And until we understand definitions of these very complex ideas, it's going to be more. Once we do understand that, then that's going to make it easier to actually measure. So
And with this, we want to also honor the student prize. And it's not necessarily because it's a paper that is only at the student level, but it's also because we want, it is an ongoing work that we want to encourage and delivering future research. The paper that we selected is Michael Timothy Bennett's work, Computational Dualism and Objective Superintelligence. Michael's contribution is a philosophical one, and I'm very glad that we have one that is, on the one hand, formal and tight and rigorous enough to inform our work, and on the other hand, interesting enough to point us into new directions and spark a discussion. Personally, for me, this is a provocative paper because Michael is attacking something that he calls computational dualism, and that is the idea that software and hardware are should be seen as separate. And for us, it seems to be a very natural thing to do because the number of GPUs that we can have available does not depend on the local structure of space-time and the Neck entropy gradient, but on how much funding we have available and the legal structure of our labs and so on. And what happens in the GPU is in some sense isolated. And so we treat the computer as a causal isolator to the universe. But when we zoom out, then we see that in organism, this is not the case. That basic computation and making models, intelligence is tightly embedded in the universe. And when you look at our AI research as part of the development of intelligence of a species and of life on Earth, that's also true. And so when we zoom out, we basically realize that intelligence is a way in which structure is forming itself in the universe, and it depends on the way in which such systems are able to interact with the universe and enact themselves. And this also creates a way for us to think about upper bounds of intelligence in a given context, and this can at some point inform our thinking about the future of artificial intelligence and its place in the universe and AI risk. And with that, we would like to thank Michael and award him the student prize of the Open Koch Society. I would very much like to recognize Ben for providing the space for creating the society, and a lot of people who volunteered in and helped in it. But if this idea would not have brought this community together, we wouldn't be sitting here today in this community. A lot of research, a lot of impulses would not have existed over all the years in which the AGI Society and the series of AGI conferences has persisted. The AGI conference was founded in the middle of a very harsh AI winter that is almost hard to remember now. But I'm very, very grateful that this community exists, and I'm also thankful for all the volunteers and helpers and people who believed in this idea and are carrying it forward as a labor of love, as something that is a commitment to increasing intelligence and consciousness in our universe and bringing it forward as well as we can, and do this together with dedication and sacrifice and commitment and support for each other. So I would like to thank all of us. I would like to thank the reviewers. I would like to thank the program committee for providing reviews and insight and feedback to the contributions, and often made them a lot better. And with that, I'd like to give the word back to Ben.
Yeah, thank you, Jutta. And yeah, I'm also quite grateful to the large number of people who have been working to make the conference a reality. And since I didn't write down a list, I'm not going to try to list them for fear of forgetting some of the many important people. But I'm also want to express my gratitude for everyone who showed up here and participated by the internet as well. We've been doing these formal conferences since 2008, and we had a workshop in 2006 before that. I think it's been quite interesting to see the progress of the field over that time, which has been, I would say, more steady and sort of ongoingly incremental than the wild ups and downs of the funding scene and the business world. I think as AI winters and summers and bubbles and hypes have come and gone, the progress of understanding has gone forward in a much more steady way, which is due to the efforts of folks like the researchers here. I would say, of all the AGI conferences so far, I feel like this one has been the most intellectually satisfying, and that's, for a number of different reasons, but one of them is just like, I think this is our time. Like AGI, the idea has been around since the middle of the last century. The term emerged, in the early aughts, 20 years ago or so. But we are palpably moving quite close to the time when actual human-level AGI will be created, perhaps not long after that superintelligence. Of course, each of us has our own theories of AGI, and each of us has our own estimates of how far or close we are from getting to AGI and at the human level. That diversity and the free expression of diversity is one of the fantastic things about this community that we'll be trying to foster since the beginning. But from my own personal view, like I can feel from the nature of the ideas presented, the quality of the presentations, the mixture of conceptual, mathematical, and practical ideas. I mean, I can feel AGI starting to crystallize from the collective work of so many people in this room and some outside. And it's just, it's an exciting thing to be a part of, generally speaking. As an embodied human being, it's extra exciting to be physically around a significant chunk of the people making it happen. So yeah, thanks everyone for coming, and I think next year is going to be even better. And Chris, I think you have a few remarks as well. But yeah, thanks a lot, everyone.
Yes, thanks, Ben. I will make it very short, but it's my honor to conclude this year's AGI conference as conference chair. And I think we all agree that this conference was a resounding success. The numbers speak for themselves. We have really great submissions of papers, 30% acceptance rate, which is probably the lowest ever. Over 700 virtual attendees, over 110 in-person attendees, 2,000 unique views on YouTube. Very great numbers. I'd like to congratulate the many researchers that participated in providing this conference with this great content, and the keynote speakers who together helped the science and technology of AI and AGI become more visible and moving it forward. So thanks to our relentless and ambitious staff who made this all possible and run so smoothly. And our audience, you, for taking this topic seriously and giving us energy and reason to carry on. So see you at next year's AGI. Thank you.